What if I told you that the wires inside your high-speed electronics are basically lying to you?
That is a great way to put it.
Right. Like we all think a wire is just a pipe for electrons. A resistor just slows them down and, a capacitor stores them. But if you crank up the frequency of the electricity running through them, suddenly those simple components start acting like entirely different objects.
They really do. I mean, they undergo a complete identity crisis. And that's exactly what we are getting into today. We're pulling from Chapter 23 of the Feynman Lectures on Physics, Volume 2, focusing on cavity resonators.
Okay, let's unpack this. Because before we get to this magical box, I really want to understand this identity crisis. Like, why do our normal tools just fail when things get fast?
Well, our mission for this deep dive is to trace how a basic, everyday electrical circuit morphs into a self-sustaining box of pure electromagnetic energy. But to start, it really comes down to the equivalent circuit concept. So let's say you're looking at a standard resistor on a circuit board. On a diagram, it's just, a jagged little line.
Yeah, standard symbol.
But physically, when current flows through that tiny piece of carbon or film, it actually generates magnetic field around itself.
Because moving charge always creates a magnetic field. So the resistor is what? Accidentally acting a bit like an electromagnet.
Precisely. We call that parasitic inductance. And to build on that, producing an electric field across that resistor requires charges to accumulate at its ends. As the voltage changes, those charges shift, which means the resistor is also storing and releasing energy.
Like a capacitor.
Exactly. Parasitic capacitance.
Wow. So even the simplest component has these hidden extra properties just clinging to it. But I mean, for the electronics we use every day, they don't seem to ruin anything. My toaster works fine.
Right, because at low frequencies, they're essentially negligible.
Yeah.
The energy changes so slowly that these parasitic effects are minuscule. But if you take that same resistor and push a high-frequency alternating current through it, where the voltage is reversing, say, millions of times a second, those tiny magnetic fields and shifting charges suddenly become the dominant forces.
Okay, so let's apply this to something that's actually meant to have a magnetic field, like a coil of wire, an inductor. The source text has these detailed diagrams of a simple coil. I just picture the current looping around the wire racetrack, right?
Sure, but think about the physical shape. Between every adjacent turn of that coiled wire, there is a tiny gap. And a gap between two conductors is essentially...
The capacitor.
You got it.
Yeah.
At low frequencies, the current just ignores the gap. It takes the long way around the wire because crossing the gap requires too much energy. But as the frequency climbs, the current faces increasing resistance from the coil's own changing magnetic field. It creates this massive back voltage.
I'm trying to picture this. If the current is getting pushed back by the coil, does it just stop?
No, it finds an alternate route. A capacitor, even a tiny accidental parasitic one, actually allows high-frequency current to pass more easily than low-frequency current.
Oh, interesting.
So the current looks at the long, difficult path around the wire loop, looks at the tiny gap between the turns, and takes the path of least resistance. It just jumps the gap.
Wait, so it completely bypasses the loops? It's like trying to drive a sports car on a bumpy dirt road. It's not that there's a speed barrier on the dirt road, it's just that the car wasn't designed for it, so the current literally takes a shortcut.
That's a perfect analogy. What's fascinating here is that engineers historically referred to this phenomenon as the high-frequency barrier. It sounds like this impenetrable wall of physics, but your analogy captures the reality.
It's just off-roading.
Yeah, the component is simply being used outside its design limits. This isn't a failure of physics. It's a failure of our idealized models. To operate at high frequencies, we have to rethink the geometry entirely.
Okay, so if coiled wires are literally short-circuiting themselves, let's look at a simpler shape. The sources highlight the parallel plate capacitor, so that's just two flat metal discs separated by a small gap. What happens to the fields in there when we really crank up the speed?
Well, at low frequencies, if you connect those disks to a power source, the electric field between them is beautifully uniform. It points straight up or straight down, depending on the charge, and it's evenly distributed across the entire area of the disks.
If you're visualizing this at home, it's like a perfectly flat sheet of water moving up and down between the plates, right?
Exactly. But as we increase the frequency, that electric field starts reversing direction incredibly fast. And according to Maxwell's equations, a changing electric field generates a magnetic field.
Right.
When the change is rapid, this induced magnetic field becomes quite strong, circulating in these concentric rings around the center axis of the plates.
Hold on, I thought moving physical charges, like actual electrons, moving through a copper wire created magnetic fields. Are you saying an electric field just changing out in the open, empty space between the plates creates a magnetic field all by itself?
That is a core, fundamental principle of electromagnetism. The changing electric field in the empty space acts just like a physical current.
Wow, okay.
Now, here is where the feedback loop begins. A changing magnetic field induces its own electric field, and this new secondary electric field actually opposes the original one that created it.
Wait, so the main electric field creates a magnetic field, which then creates a new electric field that fights the first one. That sounds like an absolute mathematical nightmare.
Oh, it triggers an infinite cascade.
Of course it does.
Yeah, the secondary electric field creates a secondary magnetic field, which creates a tertiary electric field, and so on. The final actual electric field between those plates is the mathematical sum of all these interacting fields.
So how does that change the shape? We started with that nice, uniform, flat sheet. What does it look like after all this cascading interference?
The primary field remains strongest at the center, but as you move outward toward the edges of the disks, those opposing secondary fields start dragging the total field strength down. The uniform sheet basically becomes a parabolic curve, drooping toward the outer edges.
Okay, I'm with you. It droops. But the text gets heavily into something called the Bessel function of zero order. Why do we need a complex mathematical function just to describe a drooping field?
Because of the cylindrical geometry. If this were happening on an infinitely long, flat plane, the wave would just behave like a standard sine or cosine wave.
Hmm.
But we are working with circular plates.
Right.
Think about dropping a pebble in the center of a circular pool. The ripples expand outward, but their intensity changes as they spread over a larger and larger circumference. The Bessel function mathematically describes how waves behave when they are constrained by that cylindrical symmetry.
I'm looking at a graph of this Bessel function from the source, and it does something completely counterintuitive. It doesn't just curve down and gently fade to zero. It actually crosses the axis into negative territory.
Yes, it does.
Are you saying the electric field at the edge of the capacitor points in the exact opposite direction from the center?
Mind-bending, isn't it? But yes, if you drive the frequency high enough, the center of the capacitor might have an electric field pointing straight up, while simultaneously, the outer edge of those exact same plates has an electric field pointing straight down.
That's wild.
The entire concept of a simple capacitor storing charge uniformly has completely broken down. It is now this complex arena of oscillating, conflicting electric and magnetic fields.
But wait, if the field starts positive in the center and goes negative at the edges, it has to cross zero, somewhere in between.
And that zero crossing is the key to everything. Because the Bessel function is so well understood, we can calculate exactly where that happens. It occurs at a very specific mathematical parameter.
Okay, what's the number?
2.405.
2.405. So at a specific radius from the center, corresponding to that number, the electric field is absolutely zero. Like nothing is happening there.
Correct. Now, consider what happens if we take a thin sheet of metal, form it into a cylinder, and place it between the top and bottom plates exactly at that 2.405 radius.
Wait, you're losing me. If I stick a piece of metal across a capacitor, connecting the positive and negative plates, I create a massive short circuit. Sparks fly, the circuit dies.
Under normal circumstances, absolutely, because an electric field would drive electrons through that metal wall, creating a massive current. But, and this is the crucial part, what is the strength of the electric field at the specific radius we just chose?
Oh wow, it's zero.
Exactly.
There's no field there to push the electrons.
The metal wall sits perfectly invisible to the fields inside. No current flows through it. The complex dance of electric and magnetic fields just continues inside that cylindrical boundary, completely undisturbed.
Here's where it gets really interesting. It's like finding the exact eye of the hurricane where the wind is zero and building a wall right there. The storm keeps raging inside, totally undisturbed, and you can just detach the whole room and walk away with it.
That is the pivotal leap. We cut away everything outside our new wall, we disconnect the outside wires entirely, and what remains is a completely closed, standalone metal can. Inside that can, without any external connections, we have trapped a self-sustaining oscillation of electric and magnetic fields.
We've created the resonant cavity.
Yes.
But if it's completely sealed off, how long do those fields keep oscillating? Do they just bounce around forever?
Well, not forever. The metal walls aren't perfect conductors. As the magnetic fields sweep across the metal, they induce tiny currents in the walls, which dissipate energy as heat. So eventually the internal oscillation would die out. But the concept is undeniably real. The fields are entirely contained and defined by the physical geometry of the can itself.
Okay, so we have this magic can full of electromagnetic energy, but if we have this sealed metal cylinder, how do we actually prove there are fields inside? We can't exactly just pop the lid off to check.
We have to introduce a very small breach. We drill a tiny hole in the side of the can and insert a small loop of wire. If we pass a high-frequency alternating current through that wire loop, its magnetic field kind of bleeds into the cavity.
Okay.
And if our driving frequency perfectly matches the natural resonant frequency of the can, the fields inside will synchronize and absorb the energy, building in intensity.
So we're basically pumping energy through a keyhole. And I guess if we put another loop on the other side, we could measure what comes out.
Yes, exactly. And when physicists do this, they discover something remarkable about the precision of these cavities. We measure resonance quality using something called a Q factor. A higher number means a sharper, more precise resonance.
What's a normal number for that?
Well, a typical radio circuit might have a Q factor of, say, 100. But if you build this cavity with highly conductive silver walls, the Q factor can reach 100,000.
100,000. So if your input frequency is off by even a tiny, tiny fraction, the cavity completely ignores it. It's incredibly selective.
Highly selective. But this selectivity actually led to a pretty fascinating historical misunderstanding.
Oh.
Yeah, the math we've discussed so far assumed one specific arrangement of fields, the electric field going up and down, and the magnetic field circling horizontally.
Right, the classic Bessel function shape we just mapped out.
Right. So to test this, researchers built a specific cylinder. It had a diameter of 3 inches and a height of 2.5 inches. Based on that 2.405 parameter, they predicted the cavity would resonate at 3,010 megacycles.
Let me just pause there for a second. The text uses megacycles, but for anyone listening who works with modern electronics, are we basically just talking about megahertz?
Yes, megacycles per second is just the older term for what we now universally call megahertz.
Yeah.
So 3,010 megahertz.
Yes.
When they tested the physical can, the primary resonance actually peaked at 3,050 megahertz. Very close. The slight deviation was easily accounted for by the minor disruptions caused by those little wire loops we mentioned. But, and this is where it gets weird, as they continued to sweep their signal generator to even higher frequencies, they encountered massive, unexpected resonance spikes at 3,300 megahertz and again at 3,820 megahertz.
Right, but we designed the can specifically for the 3050 frequency based on that 0-point radius. Where are these higher frequencies coming from? Are there other 0 points?
It turns out our initial assumption was flawed. We assumed the fields only wanted to bounce vertically between the flat end plates, but the electromagnetic fields inside the can can simply seek any stable geometric arrangement that satisfies Maxwell's equations and intersects the metal walls at right angles.
They don't know which way is up. If they can find a stable pattern bouncing side to side, they'll just do it.
Exactly. We call these different patterns resonant modes. The vertical pattern is one mode, but at a higher frequency, the fields might arrange themselves transversely, bouncing from one curved wall to the other. Each unique geometric arrangement creates a distinct resonant frequency.
I'm picturing this sealed metal cylinder. It's completely opaque, and inside there are these invisible, complex 3D structures of energy just sloshing around. How did scientists ever figure out what those specific patterns look like? I mean, you can't see them.
The experimental method they used was incredibly clever. They used those tiny holes in the cavity again, but instead of a loop, they inserted a short, straight piece of wire mounted on a little pivoting base.
Like a little spinning antenna.
Exactly like an antenna.
Yeah.
Think about how an antenna interacts with an electric field. If the wire is parallel to the electric field, the field pushes electrons up and down the wire, creating a current. This current actually saps energy from the cavity, destroying the resonance.
So if you poke the wire in and the resonance suddenly dies, you know the electric field is pointing in the exact same direction as your wire.
Right. But if you rotate that wire 90 degrees, so it sits perpendicular to the electric field, it absorbs almost no energy. The resonance remains strong.
Oh, wow.
By systematically inserting this tiny pivoting wire into different parts of the cavity and rotating it while monitoring the resonance strength, researchers could physically feel the invisible field lines.
That is brilliant detective work. They literally mapped the 3D geometry of an invisible force field inside a dark metal can just by sweeping a tiny bent wire around and watching a dial.
It's a beautiful piece of experimental physics.
It really is. Now, we've gone deep into this isolated metal can, but I want to tie this back to where we started. We set out to see how an everyday circuit morphs into this box of energy. How does a normal circuit board evolve into a resonant cavity?
The progression is beautifully continuous. Let's construct it step by step. We start with a standard low-frequency resonant circuit, a parallel plate capacitor wired to a typical coiled inductor, an LC circuit.
Right. Capacitor stores charge, inductor stores magnetic energy, and they trade it back and forth.
To increase the resonant frequency of this circuit, we must decrease the inductance. The simplest way to do that is to uncoil the wire. We reduce the inductor to just a single loop of wire connecting the top plate to the bottom plate.
Okay, so we go from a spring shape to just a single C connecting the plates.
Now we need an even higher frequency, which means lowering the inductance further. In electronics, putting components in parallel reduces their total value. So we place a second single-loop wire on the opposite side of the plates, then a third, then a fourth.
If you're picturing this at home, it starts to look like a little metal birdcage surrounding the capacitor plates.
Exactly. And to push the frequency to the absolute limit, we continue adding parallel wires. Eventually, the wires become so numerous that they physically touch each other.
And a cage of touching vertical wires is just a solid cylindrical wall.
Yes. If we connect this to the bigger picture, a resonant cavity is not some bizarre departure from classical electronics. It is the logical extreme conclusion of an LC circuit. The distinct physical components, the capacitor and the inductor, have essentially merged into a single, continuous, enclosed space.
So what does this all mean? It means the can isn't a new invention at all. It's just a traditional circuit that has physically mutated to survive the chaotic environment of high frequencies. The underlying physics never changed, only the geometry did.
That is the most profound takeaway from this chapter of Feynman's lectures. When the rules of your system appear to break down, when current jumps across gaps or electric fields reverse themselves, it rarely means the universe is broken. It usually just means you need a wider perspective. You must stop looking at the rigid, idealized blueprints of wires and components and start examining the fields themselves.
It completely shifts how you see the technology around you. I mean, think about the devices you rely on every single day, your smartphone, your Wi-Fi router. We spend all our time looking at the physical objects, right? The intricate copper traces on a green circuit board. But the resonant cavity proves that the real action, the actual transfer of energy and information, is happening in the invisible space between the metals.
All in its fields.
Exactly. What if the physical components we obsess over are really just the scaffolding, and the empty space is where the real universe is happening? Something to think about the next time you hold your phone. You know, what if I told you that the absolute best way to send massive amounts of electrical energy isn't with a wire at all,
Right.
but instead through a completely empty, hollow metal pipe?
It sounds like a trick question, honestly.
It really does. But today we are taking you on a deep dive into Chapter 24 of the legendary Feynman Lectures on Physics. We're specifically looking at waveguides.
Well, this is such a great topic.
Yeah, our mission today is to unpack this totally mind-bending concept. We're going to see how we can shoot electromagnetic energy through an absolute void, relying purely on the geometry of empty space.
And we really are going to break down the text, the math, and the underlying reality of how this empty pipe magic actually works.
Exactly. Because, I mean, it really does feel like magic the first time you encounter it.
Oh, absolutely. Because instinctively, we all treat electricity like plumbing.
Right?
You connect a copper wire from a battery to a light bulb, and the current flows. And, that mental model works perfectly well for the kind of low-frequency electricity we use every day.
Like the stuff in our walls.
Exactly. The power lines running into your home are oscillating at a really sluggish 50 or 60 cycles per second. At that leisurely pace, the electrical energy stays neatly bound right to the wire.
But the text points out a huge problem that arises when you crank up that frequency.
A very big problem.
Yeah, when you get into the radio frequencies, like the kilocycles and megacycles that power your Wi-Fi or airport radar systems, those ordinary wires rebel.
They really do. They stop acting like pipes guiding water.
Right, and they start acting like antennas. They just start bleeding your energy out into space. You're trying to send a private signal to a specific destination, and instead your wire is indiscriminately broadcasting it to the entire neighborhood.
Yeah, the fields simply spread out too fast for the wire to hold on to them.
Yeah.
So historically, engineers needed a way to, well, cage that energy. And the first major solution to this was the coaxial cable.
Which I always picture as a garden hose for electricity.
That's a good way to look at it.
Yeah, you have your inner wire, which carries the actual current. But to stop that current from radiating its energy outward, you completely surround it with a hollow outer conducting shield.
Right.
The energy is perfectly trapped in the empty space between the inner wire and the outer shield.
And what's fascinating here is the basic math of how that trapped energy travels. Feynman shows that if you calculate the inductance, which is how it stores magnetic energy, and the capacity per unit length.
Which is essentially just how much electrical charge a section of that cable can hold.
Exactly. If you calculate those, they balance each other out perfectly.
Yeah.
And because of that exact mathematical balance, the electromagnetic wave travels down the length of the cable at exactly the speed of light.
Which is incredibly elegant. But here's where it gets really interesting.
Oh, yes.
What happens if you take that coaxial cable, that electrical garden hose, and you just yank the inner wire right out?
You're left with a literal pipe.
Right. You are left with nothing but a hollow metal tube. And the central mystery of this deep dive is that at high enough frequencies, that completely empty tube still works.
It does.
It still transmits energy. But how? I mean, how in the world do you guide an electrical current without a wire for it to flow on?
Well, to understand that, it forces us to completely abandon our everyday intuition.
Yeah.
We have to stop thinking about a physical current flowing through a piece of metal and start thinking about invisible, oscillating electromagnetic fields propagating through space.
Okay.
By using a hollow tube, we're basically boxing those fields in. We can find them in two dimensions, the width and height of the pipe, but we let them run completely free in the third dimension, straight down the length of the pipe.
Okay, let's unpack this. Because to help us visualize it, Feynman uses the example of a rectangular pipe.
Right.
So picture a long metal box like a rectangular air conditioning duct stretching out into the distance. Now, electromagnetic waves, like light or microwaves, have a transverse electric field. That means if the wave is moving forward down the pipe, the electric field is oscillating up and down or side to side, perpendicular to the direction it's traveling.
Exactly.
So how does that sideways field fit inside this empty metal box?
That is the crucial question.
Mm-hmm.
Because the metal walls of the pipe impose a very strict, non-negotiable rule.
Okay.
The electric field must drop to absolute zero the moment it touches those conductive metal walls.
Wait, why? Why can't the electric field just push right up against the metal?
Well, think about what a metal conductor actually is. It's a sea of free electrons just waiting to be pushed around.
Right.
If there were any electric field parallel to the surface of that perfect conductor, it would instantly grab those free electrons and slam them into motion.
Oh, and moving electrons create a current.
Right. And those moving electrons immediately create their own opposing field, which perfectly and instantly cancels out the original field.
Oh, wow.
So the moment you hit the wall, the net electric field is strictly zero.
Oh, that makes total sense. The wall fights back.
It really does.
Okay, so the field is forced to be zero at the left and right edges of the pipe. But it has to exist in the middle, otherwise we wouldn't be transmitting any energy at all.
Correct.
The text describes this field as arching across the inside of the guide. It's zero at the left wall, it swells up to a massive peak right in the exact center of the empty space, and then gracefully drops back down to zero at the right wall.
Forming a perfect half cycle of a sine wave across the width of the pipe.
You know, it reminds me of a jump rope being swung by two people.
Oh, that's good.
Yeah, the two people holding the ends, those are the solid walls of the waveguide. Their hands aren't moving. The rope is perfectly still at those two boundary points, just like our field is zero at the walls.
Right.
But in the center, between them, the rope is swinging in this massive, wide arc. That's our electric field.
I love that analogy. It captures the geometry perfectly. And just like a jump rope, that arching field doesn't just sit there frozen.
It moves.
Exactly. It propagates down the length of the tube, alternating positive and negative as it goes. One moment, the arch is pointing up toward the ceiling of the pipe. The next moment, it's pointing down toward the floor, traveling forward like a wave on an ocean.
And we can't forget the magnetic field.
No, we definitely can't.
Feynman details these invisible loops of magnetic energy swirling around inside the pipe. They always circle around the areas where the electric field is changing the most rapidly.
Where they're intrinsically linked.
So as this jump rope wave travels down the pipe, it's dragging these swirling tornadoes of magnetic energy along with it.
Yeah, and if we step back, you've just described a fully functioning guided wave, no inner wire required whatsoever.
It's just empty space?
Just empty space. The pipe itself is just acting as a boundary, a strict set of rules to keep the wave structured as it flies through the inside. But there is a catch.
There is always a catch. Let me guess. It doesn't work for everything.
Exactly. This empty pipe trick only works based on a very rigid relationship between the physical size of the pipe and the wavelengths of the energy you were trying to send through it.
Right, which brings us to a really counterintuitive concept from the text. The cutoff frequency.
Yes.
So our jump rope wave is arching across the pipe and traveling down, but Feynman introduces a mathematical threshold.
The cutoff frequency, yeah.
Right, which is basically pi times the speed of light divided by the physical width of the pipe. If you try to send a frequency that is lower than that threshold, the math gets incredibly weird.
It does.
The wave number, which is the variable in the equation that describes how the wave oscillates through space, suddenly becomes an imaginary number.
Yes, the term sitting under the square root in the wave equation suddenly turns negative, and that leaves us with an imaginary wave number.
Now, I have to admit, this confused me at first.
Oh, it confuses a lot of people.
Because usually, when an imaginary number pops up in a physics equation, it means we've broken reality or made a terrible mistake in our math. Like, if I'm calculating the speed of my car and the answer is an imaginary number, I haven't discovered a new state of matter, I just have a broken calculator.
Exactly.
So what does an imaginary wave number actually look like in the real world of this metal pipe?
Well, it's a very common misunderstanding to think the math has just failed us there. In wave mechanics, an imaginary number is deeply physically meaningful.
Really?
Yeah. It doesn't mean the universe broke. It simply means the wave stops oscillating. It changes its fundamental form.
Okay.
Instead of a repeating sine wave that travels indefinitely down the pipe, the imaginary number translates mathematically into an exponential decay.
So it ceases to be a wave at all. It just dies.
Exactly. If you hook up a generator and try to pump a low-frequency signal into this pipe, the fields penetrate a very short distance into the opening, and then they rapidly die off. They just fade to zero.
Wow.
The pipe literally refuses to let the wave pass. It acts as a perfect, impenetrable barrier.
That is wild to think about. The exact same empty brass pipe will act as a wide-open superhighway for a high-frequency wave, but it acts like a solid brick wall for a low-frequency wave.
Yeah.
And all because the physical width of the pipe doesn't give the low-frequency wave enough room to form that jump rope arch, so it just decays exponentially.
And this isn't just a quirky feature of waveguides. Any time in wave physics where you encounter an imaginary wave number, whether in acoustics, optics, or quantum mechanics, it signifies this exact thing.
An abrupt transition from a wave to a dying field.
Precisely.
Okay, so now that we know when the waves actually propagate, which is when they are above that cutoff frequency, we need to look at how fast they are going.
This is where it gets really weird.
Yeah, here the text throws a massive curveball that seems to violate the fundamental laws of the universe.
It really does. This is one of those moments that forces you to pay attention to what the equations are actually saying. The math clearly shows that the phase velocity of the guided wave, which is the speed at which the ripples or the crests of the wave are traveling down the pipe,
is actually greater than the speed of light.
Wait, hold on. Didn't Einstein explicitly outlaw anything moving faster than light?
He did.
Like, that is the ultimate cosmic speed limit. If I'm sending a signal through a hollow pipe, how can it be breaking the laws of relativity?
Well, it looks exactly like a paradox on paper. But we have to make a very careful distinction here.
Okay.
We have to distinguish between the phase velocity, which is merely the speed of the geometric shape of the wave, and the group velocity, which is the speed of the actual physical energy.
I was trying to wrap my head around this, and I think I have an analogy. Let me know if this works.
Let's hear it.
Imagine you are standing on a beach looking at a long, perfectly straight concrete seawall. Now imagine a long ocean wave coming in. But it's not perfectly parallel to the wall, it's hitting it at a very slight angle.
Okay, I'm picturing it.
The moment the long wave touches the wall, it creates a splash. As the rest of the wave continues to roll in, that point of intersection, that splash travels all the way down the seawall.
Right. I see where you're going with this.
If the incoming angle of that wave is incredibly shallow, almost parallel, that splash will travel down the wall unbelievably fast.
Yep.
In fact, the splash will travel down the wall much, much faster than the actual wave is moving through the water. That point of intersection, that's the phase velocity.
Spot on.
It's just a geometric intersection moving. It's not actual physical stuff or water molecules moving down the wall at that speed. So no laws of physics are being broken because you couldn't attach a message or a physical object to that splash.
That is a phenomenal analogy. The phase velocity in our waveguide is exactly like that splash. It's just the nodes of the wave moving, not the underlying energy.
Got it.
The actual physical stuff, the electromagnetic energy, and any information you were trying to send travels at what we call the group velocity. And if you do the math for the group velocity, as Feynman does, it always comes out to be less than the speed of light.
Okay, so Einstein is safe.
Einstein is safe. The cosmic speed limit still holds.
Phew. Good. I was worried we were going to get a speeding ticket from the physics police. But, you know, there's a mathematical relationship between those two speeds that just blew my mind.
Ah, yes, the quantum connection.
Yeah.
This raises such an important question about the fundamental nature of reality. If you take that faster than light phase velocity and you multiply it by the slower than light group velocity, you get exactly the speed of light squared, c squared.
Which is a beautiful, symmetrical mathematical trick on its own.
But the rabbit hole goes deeper.
Tell me.
To frame this conceptually, Feynman introduces an equation that relates energy to momentum for a solid particle. What's crazy is that the exact mathematical signature, the variables he uses to describe how a radio wave behaves inside a macroscopic empty metal pipe, is identical to the fundamental quantum mechanical equation for a particle.
That's insane.
It is. The equation u squared equals p squared c squared plus m squared c to the fourth. The behavior of a microwave in a brass tube uses the exact same mathematical structure as the fundamental building blocks of matter.
That is just... It's almost eerie. It's like the universe only has a few really good magic tricks, and it just reuses them at completely different scales.
It really highlights the deep underlying unity in physics. The rules governing a massive radar installation are mathematically mirrored in the rules governing an electron.
Wow. So, okay, we've established that this empty pipe can break seemingly impossible physical limits, and it mirrors the quantum nature of the universe.
Yes.
But theory is one thing. How do you actually build a real-world circuit out of empty brass pipes?
That's tricky.
Because we started this deep dive by saying coaxial cables work up to certain frequencies. Why bother with the incredible hassle of engineering waveguides?
It ultimately comes down to power, efficiency, and heat.
Heat.
Yeah, for extremely high power applications, think of a massive radar array at a busy airport, or even the intense magnetron inside your kitchen. Microwave coaxial cables fail catastrophically.
Because of the power.
Right. The physical plastic insulation inside the cable literally breaks down and arcs under the immense voltage. Furthermore, the high current density concentrated on that tiny, fragile inner wire creates massive heat loss.
So if you pushed airport radar levels of power through a coax cable, the inner wire would basically just melt itself into slag.
Precisely. Waveguides, however, are just empty pipes with massive surface areas on their inner walls. They can handle absolutely huge amounts of power with far lower losses.
Especially if you pleat the inside of the pipe with a highly conductive material like silver.
Exactly. Silver-plated empty pipes are incredibly efficient.
But building circuits out of these things, I mean, the text introduces this amazing, almost funny term, microwave plumbing.
That's a great term.
Because it's literally just a network of metal pipes. But you can't just solder them together with a blowtorch like regular copper pipes in your bathroom.
Yeah, you certainly can't. At these high frequencies, the currents are incredibly sensitive. Any tiny physical imperfection, any slight gap or microscopic blob of solder on the inside of the pipe will cause the delicate surface currents to reflect backward.
That sounds like a nightmare.
It is. You would lose massive amounts of energy at every single joint. So engineers had to come up with truly ingenious solutions to connect these pipes.
Yeah, the low-loss flange connection is brilliant. Instead of trying to make the perfect, flawless, perfectly smooth physical connection between two pipes, they do the exact opposite.
They do.
They deliberately leave a tiny physical gap between the two pipes, but they cut a very precise groove into the face of the connecting flange.
A resonant cavity groove.
Right. And because of the exact dimensions of that specific groove, it acts as a massive barrier, what engineers call a high impedance, basically an invisible electrical roadblock. to the current that is trying to leak out of the pipe. So the incredibly high currents of the wave just charge and discharge across the physical gap, almost like a capacitor, without actually needing physical metal-on-metal contact, and without leaking any energy out of the joint.
It's so clever.
They solve the problem of an imperfect connection by simply not connecting them at all.
It's a masterful application of the physics we've been discussing.
Mm.
But perhaps my absolute favorite device in this entire subject is the unidirectional coupler.
Oh, this thing is straight up engineering magic.
It really is.
Okay, so imagine you have the sealed solid metal pipe and massive amounts of invisible microwave energy are blasting through it. How do you even measure what's going on inside?
Right.
Like, how do you know which direction the wave is traveling without cutting the pipe open and ruining the whole system?
Well, the solution is remarkably elegant. You take a secondary, much smaller piece of waveguide, and you weld it to the side of your main pipe.
Okay.
Then you drill 2 tiny holes between them, allowing some of the electromagnetic fields from the main pipe to leak into the secondary one.
But wait, if you just drilled one hole, that leaking wave would spread out and travel in both directions in the new pipe. You still wouldn't know which way the original wave was going.
And that's the key. This is where the magic of wave interference comes in. You don't just drill one hole. You drill 2 holes, and you space them exactly 1/4 of a wavelength apart.
Oh, let me work this out. Because of that specific spacing, a wave traveling forward hits the first hole and a little bit leaks through.
Yep.
Then the main wave travels a 1/4 wavelength further and hits the second hole, leaking a bit more. But if that second leak tries to travel backward through the secondary pipe to meet the first leak...
It has to travel that 1/4 wavelength again.
Right. So it's been delayed by a 1/4 wavelength going forward and a 1/4 wavelength going backward. That's a total delay of a 1/2 wavelength.
And what happens when 2 identical waves meet, but one is delayed by exactly 1/2 a wavelength?
The peak of one wave perfectly aligns with the trough of the other. It's total perfect cancellation. They completely destroy each other. So in the backward direction, absolutely zero energy flows. But in the forward direction, they add together perfectly.
Because there's no relative delay in that direction.
Wow. By simply measuring the energy at the end of that secondary pipe, you know, with absolute certainty which direction the invisible wave in the main sealed pipe is traveling, it is pure interference magic applied to heavy metal plumbing.
It's a true testament to what happens when you deeply understand the wave nature of these fields. You can manipulate them with nothing but empty space and clever geometry.
Amazing.
Which actually brings us to the final perspective Feynman offers us.
Yes, the mirror perspective. We've spent a lot of time talking about transverse fields, equations, phase velocities, and directional couplers.
A lot of heavy concepts.
Yes, but the text gives us one final, beautifully visual way to understand why waveguides work, stripping away almost all the complex math.
It's a technique based entirely on how electromagnetic waves interact with perfect conductors. Imagine the source of your radio wave is just a single vertical wire transmitting a signal, and you place that wire halfway between 2 perfectly parallel conductive metal walls.
Okay, I have the picture in my head. A broadcasting wire sandwiched between 2 walls.
Now, to a radio wave, a perfect metal conductor acts exactly like a mirror does to visible light.
Oh, interesting.
So when that central wire broadcasts its wave toward the wall reflects it back. But mathematically and practically, it's as if that reflection is coming from an entirely separate image wire standing behind the wall.
Just like when you stand in front of a mirror, it looks like there is a perfectly real 3D clone of you standing behind the glass.
Precisely. But here's the trick. Because we have 2 walls facing each other, that image wire reflects in the opposite wall, and the original wire reflects again, and so on. Just like standing in a dressing room with mirrors on opposite walls, you don't just see one reflection. You see an infinite repeating line of images stretching out to infinity in both directions.
An infinite line of ghost wires broadcasting through the pipe.
Exactly.
And because we established earlier that the electric field has to be 0 at the metal walls, each successive ghost wire has to have the opposite polarity of the one before it to make the math work.
Right.
Positive, negative, stretching forever.
Now, using this Hall of Mirrors model, we can perfectly explain that mysterious cutoff frequency we talked about earlier without using any complicated calculus.
Okay, let's test this. How do infinite ghost wires explain why a low-frequency wave acts like it hits a brick wall and just dies?
Well, think about what low frequency actually means physically. It means a very long wavelength.
Right.
The waves are stretched out so much that from a distance, This infinite alternating line of positive and negative sources essentially just blurs together.
Oh, I see.
The positive sources pull the field in one direction, the negative sources pull it in the exact opposite direction, and statically they just perfectly cancel each other out.
Leaving nothing.
The net result is nothing. The field just rapidly decays to zero as you move away from the source.
That makes incredible sense. At low frequencies, the static cancellation dominates the entire space. But what happens at high frequencies? Why does the wave suddenly break through that invisible barrier and propagate?
At high frequencies, the wavelength is much, much shorter. And because it takes actual time for the waves from all those infinite ghost sources to travel across the physical space.
That's a concept physicists call retardation, right? Or just time delay.
Exactly. Because of that time delay, there are specific geometric angles where the crests of the waves from all those different distant sources line up perfectly.
Constructive interference.
Yes.
It's like looking at the chaotic ripples from 100 different pebbles dropped in a pond, but finding the exact angle where all the ripples randomly merge into one giant unified wave.
You hit the nail on the head. When the frequency is high enough, these specific angles of constructive interference appear. And if you look closely at the resulting pattern, the field inside the waveguide is literally just two separate trains of perfectly flat waves.
Bouncing back and forth.
Exactly, reflecting off the walls and zigzagging their way down the pipe together.
So instead of a weird jump rope arch mysteriously moving forward, we can just picture two normal waves ricocheting off the walls like billiard balls, traveling down the tube.
It's so much easier to visualize.
It really is. Both perspectives, the strict mathematical equations we started with, and this highly visual infinite hall of mirrors describe the exact same physical reality. They just give us entirely different mental models to grasp it.
Which is such a classic Feynman way to look at the physical world.
It really is. Well, that brings us to the end of our journey today. We started with a wire stuck inside a tube, realizing we could just throw the wire away and still send power. We uncovered the strange reality of imaginary wave numbers blocking low frequencies like a brick wall. We explored the ingenuity of microwave plumbing, where a literal gap in the pipe makes a better connection than solid metal.
That was amazing.
And finally, we saw the whole system as a beautiful, infinite hall of mirrors.
If we connect this to the bigger picture, I want to leave you with a final thought to mull over.
Oh, please do.
Earlier, we talked about how the wave equation for this hollow, macroscopic metal pipe perfectly matched the quantum mechanical equation for a fundamental particle. The math is identical.
Yeah, that equation mapping energy to momentum.
So consider this. What if that is more than just a neat mathematical coincidence?
What do you mean?
Could it be that the fundamental particles making up our universe, the electrons, the quarks, the literal stuff that makes up you and me, are themselves just localized waves?
Oh, wow.
Waves trapped in the waveguides of some higher dimensional space, appearing to us as solid particles with mass, simply because they're bouncing back and forth below their own cosmic cutoff frequency.
That completely empty metal pipe. Maybe the empty space around us isn't so empty after all.
Maybe not.
Maybe we're all just trapped waves in the cosmic plumbing. I love that. Thank you so much for joining us on this deep dive. Keep questioning the seemingly empty spaces around you, and we will catch you next time.
Imagine trying to write down, like, the entire behavior of light, electricity, and magnetism, but fitting it all into a space the size of a postage stamp.
Right, which just sounds completely impossible when you first hear it.
Totally impossible. I mean, you were talking about these sprawling, chaotic laws that govern everything. Everything from that tiny spark of static electricity on your sweater to the massive magnetic fields that literally shield our whole planet from solar radiation.
It's a lot of physics to compress, yeah.
Exactly.
Yeah.
But what if I told you that by simply changing how we view the universe, by looking at it through the lens of four-dimensional space-time, all those complex rules just compress down into a single elegant line of math?
And you know, the real kicker is figuring out if this is just some cheap parlor trick to save ink, or if it's a profound revelation about how reality actually works.
Right. And today's deep dive tackles exactly that. We're getting into the fascinating world of relativistic electrodynamics.
Specifically, we're looking at Chapter 25 of the famous Feynman Lectures on Physics.
Which is just a brilliant source text for this.
Oh, absolutely. And our mission today is to explore how taking these complex laws of electromagnetism and viewing them through this four-dimensional lens doesn't just make the math look pretty. It actually reveals a fundamental truth about the universe.
Okay, let's unpack this. Because to simplify the math of the cosmos, Feynman tells us we first have to fundamentally change how we measure it.
Yeah, exactly. We have to take our everyday three-dimensional space and somehow fuse it with time, which is easier said than done.
I mean, I am definitely struggling a bit with the practicality of that. Space is measured in distance, meters, miles, whatever, and time is measured in seconds.
Right.
You can't just toss them into the same mathematical bucket and add them up. It feels like trying to add apples on Tuesday. It just doesn't compute.
Well, let's start with something you can easily visualize. Think about a standard three-dimensional vector.
Okay, like an arrow.
Exactly. Imagine an arrow pointing somewhere in the room you are in right now. You can describe that arrow's position using three numbers, right?
Right, like how far left or right, up or down, forward or backward?
Yes. Now, if you tilt your head or walk to the other side of the room, those three numbers will change, simply because your perspective changed.
Makes sense.
But the actual physical arrow hasn't altered at all. The laws of physics governing that arrow remain completely unchanged regardless of how you rotate your coordinate system.
So the arrow simply doesn't care how I'm tilting my head. It just exists independently of my measurement grid.
That is the core idea we want to preserve. But special relativity throws a massive wrench into this simple 3D picture. Einstein showed us that space and time are inextricably linked.
Right, the whole space-time continuum thing.
Yeah. When you start moving at very high uniform velocities, shifting into a different frame of reference, which physicists call a Lorentz transformation, your measurement of space actually compresses.
And your measurement of time stretches out. Right?
Yeah.
Time dilation.
Precisely. So to write physical laws that remain absolutely true no matter how fast you're moving, three dimensions simply are not enough. You have to create what we call a four-vector.
A four-vector. Okay.
You combine time with your three spatial dimensions into a single unified group of four numbers that transform together.
But wait, going back to my apples and Tuesday problem, how do we actually combine meters and seconds mathematically without it being a total mess?
That is the exact hurdle that stops people in their tracks. And this is where physicists use a brilliant conceptual tool. They set the speed of light, the constant we usually call sigma, to equal exactly 1.
Oh, wow. I found this part of the source is just mind-bending. By setting the speed of light to 1, you are essentially measuring time in meters.
Yes, you define a meter of time.
Which is just the time it takes light to travel 1 meter in a vacuum.
Right.
Which is incredibly fast, right? About 3 billionths of a second.
Exactly. And mathematically, it cleans everything up beautifully. All those messy variables that clutter up the complex equations of relativity, they just vanish from the page.
It makes me think of like standardizing a global currency before you try to compare international bank accounts.
Oh, that's a great way to put it.
Yeah, like if you have accounts scattered across the world in yen, euros, and dollars, adding them up is a nightmare of constantly shifting exchange rates.
Right, the math gets so tedious.
But if you invent a universal currency in this case, setting the speed of light to 1, it visually and mathematically cleans up those exchange rates between space and time.
Suddenly, meters of distance and seconds of time are speaking the exact same geometric language. We have our universal currency.
Okay, so we've got our four-vector. It treats time and space as components of the exact same geometric object. So I'm assuming we just upgrade all our normal, everyday physics concepts by slapping this new time component onto them.
You'd think so, wouldn't you?
Well, yeah, take velocity, for example. Normally, velocity is just the change in distance over the change in time. dx over dt miles per hour.
Mm-hmm.
So if we're upgrading to a four-dimensional velocity, instinct tells me that the time component of that new velocity would just be the change in time divided by the change in time. dt over dt.
Which is just 1.
Right. A number divided by itself is 1. That seems perfectly clean.
What's fascinating here is that you just fell into the exact mathematical trap that ruins the entire symmetry of relativity.
Wait, really? But how? How can a change in time divided by a change in time be anything but 1? That's just basic math.
The raw algebra of a number divided by itself is 1? Sure. But remember, the whole point of building a four-vector, it has to transform correctly when you move between different frames of reference.
Oh, right. It has to survive that Lorentz transformation.
Exactly. And in relativity, the time interval you are measuring that dt in your denominator is not an invariant absolute thing. It changes when you shift to a moving system. Time stretches.
Oh, I see. So if you put a shifting time interval in the denominator of your velocity equation, you're essentially dividing by a moving target.
Yes. You can't use a changing denominator to build an invariant vector.
That would be like trying to calculate your miles per hour using a clock on your dashboard that starts ticking slower and slower the harder you press the gas pedal.
That's exactly it. Your velocity calculation would be completely warped. It spoils the symmetry.
So instinct totally fails us there.
It does. Relativity demands that we hunt for invariants, things that absolutely do not change no matter who is looking at them or how fast they are moving. Failing to do so breaks the whole system.
Okay, so how do we fix this velocity trap? We need a denominator that doesn't melt when we go fast.
We look at something we already know works in relativity: momentum. The sources point out that the momentum 4 vector includes both a particle's energy and its regular momentum.
Right.
So if we take that entire unbroken momentum 4 vector and divide it by the particle's rest mass, we get our true 4 velocity.
Because rest mass is a true invariant scalar.
Yeah.
Like a proton's rest mass is the exact same number, whether it is sitting motionless on a desk or rocketing through a particle accelerator at near light speed.
Precisely. Dividing by that invariant scalar doesn't ruin the vector, but it does introduce a specific necessary factor into all the components.
What kind of factor?
To get a true 4 velocity, you end up having to multiply every component by 1 over the square root of 1 minus v squared. It's the Lorentz factor. It acts like a cosmic scaling adjustment.
Got it. So finding those invariants really is the whole game here. We had to find things that all observers can agree on.
Exactly, which leads to one of the most fascinating concepts in this whole chapter: finding an invariant length in 4 dimensions.
Okay, length. Measuring length in 3D is pretty straightforward, right? We all learned the Pythagorean theorem in school.
Right, x squared plus y squared equals z squared.
Yeah, or if you're in a 3D box, you square the x distance, square the a distance, and square the z distance, and add them all up. That total length doesn't change if you rotate the box.
Exactly.
But how do we find an invariant length when we add time to the mix? Do we just add a square time component to the end of that?
Nope. That instinct fails us again. To find this, we use what is called a scalar product, or a dot product. But space-time geometry has a very counterintuitive quirk.
A quirk? What kind of quirk?
You don't just add all the squares together. In 4 dimensions, the invariant length involves a sign twist. You take the square of the time component, but then you subtract the square of the x distance, subtract the a distance squared, and subtract the z distance squared.
That feels incredibly strange. Why are all the spatial dimensions suddenly negative?
Because that specific combination, e squared minus x squared minus y squared minus z squared, is the magic formula of spacetime.
Wow.
It is the only quantity that remains absolutely identical whether you are sitting perfectly still on Earth or flying past in a rocket ship at 99% the speed of light. It's our invariant.
Here's where it is really interesting, because this isn't just abstract chalkboard geometry. The sources give this fascinating concrete example with figure 25-1.
Ah, yes, the Bevatron.
Right. It shows how this exact mathematical quirk, this 4D length calculation with the minus signs, literally dictated the physical engineering specs of a massive real-world particle accelerator. We are talking about making antimatter.
The antiproton experiment at Berkeley, it really is a beautiful application of everything we've been discussing.
So let's set the stage for the listener. Imagine you are a physicist in the 1950s, and you want to create an antiproton. The physics requires firing a highly energetic, fast-moving proton into a completely stationary target proton.
Right. And if you hit it with just the right amount of violent energy, the collision produces 3 regular protons and 1 antiproton.
But the multi-million-dollar engineering question is, exactly how much energy do you need to give that initial moving proton to make this specific reaction happen?
Right. And if you try to calculate that from the perspective of the laboratory watching one incredibly fast proton slam into a stationary target, the math is just a nightmare. The kinetic energies, the shifting momentums, it's a huge mess.
But if we use our invariant 4-vector math, it becomes almost like solving a middle school algebra problem.
Exactly, because instead of standing in the lab, you mentally look at the reaction from what physicists call the center of mass system.
Okay, so imagine riding along right in the middle of the collision. From that specific vantage point, after the impact happens, the resulting glob of 3 protons and 1 antiproton are just sitting there. They are perfectly at rest relative to you.
And because nothing is moving in that center of mass system, the total spatial momentum is exactly 0.
So those negative spatial squares in our formula just vanish.
Yes. The only thing you have left to measure is the raw rest mass of those 4 particles. We know the antiproton has the exact same mass as a regular proton. So the total length of the four-momentum vector here is simply 4 times the mass of a proton.
Okay, so you square that and you get 16 times the mass squared.
And here's the magic of the invariant. Because that 16 mass squared is an invariant scalar product, it must be the exact same number in every coordinate system.
Even back in the complicated, messy laboratory system.
You've got it. So you set up the equation for the initial state in the lab, one moving proton, one stationary proton, and you set their total scalar product equal to that same 16 mass squared number.
And when you solve that, the tangled web of kinetic energy and momentum just unravels cleanly. The math easily spits out the required energy.
What does the calculation come out to?
It tells us the initial moving proton must have a total energy equal to 7 proton masses, which, when you do the conversion, is a kinetic energy of about 5.6 giga-electron volts.
And that 5.6 GeV is the hard physical threshold. If you hit it with even a tiny bit less energy, the antimatter reaction simply will not happen.
And that number dictated reality. That abstract geometric concept literally dictated the budget and specs of the Bevatron. They designed it to reach 6.2 GeV, just comfortably above that 5.6 threshold, precisely to guarantee they could make this reaction happen.
It really proves that this mathematical structure isn't just a mental exercise, it's the architectural blueprint of reality.
It's amazing. Okay, so we have a way to measure a static length or a specific state in 4D spacetime. But the universe isn't static. Things move, fields fluctuate. How do we track change across 4 dimensions?
Well, we need to scale up our calculus. We need 4-dimensional operators like the gradient.
Okay, in 3D space, a gradient is pretty simple. It just tells you how a field, like the temperature in a room, changes as you move in the X, Y, and Z directions.
Yeah.
So naturally, I'm going to guess that the 4-dimensional gradient is just the 3D gradient with a simple time derivative slapped onto the front.
And once again, instinct leads us astray. If you just add a straightforward time derivative, it doesn't transform correctly.
Let me guess it's that shifting target problem again.
Exactly. Because of how coordinates transform, you have to adjust for the mixing of space and time. To make the 4 gradient behave like a true 4 vector, you have to introduce another twist.
More minus signs.
More minus signs. The time derivative remains positive, but you must add minus signs to all the spatial derivatives, the changes in x, y, and z.
I have to admit, having those minus signs stubbornly hanging around everywhere feels so clumsy. Why does the universe insist on them?
If we connect this to the bigger picture, those minus signs aren't clumsy mistakes at all. They are the fingerprint of space-time's geometry.
What do you mean?
Well, they ensure everything stays consistent. The minus signs are the mechanism that ensures cause and effect happen in the right order, no matter your vantage point. If you didn't have them, a moving observer might see an effect happen before its cause.
Oh, wow. So they preserve the literal structure of reality.
Exactly. And when you use this properly constructed 4 gradient, things start falling perfectly into place. For instance, the sources introduce the 4 divergence.
Right, which you apply to charge, density, and current.
Yes. And when you do, it beautifully gives us the law of conservation of charge in a single equation. It proves that if charge is conserved in one frame, it's identically conserved in all uniformly moving frames.
You can't just create or destroy charge by flying a spaceship really fast past a wire.
Exactly. The math enforces the physics. The chapter also introduces the D'Alembertian operator, which is like the 4D equivalent of the 3D Laplacian. It measures second derivatives across space and time.
Okay, so armed with these tools, the 4-vector, the scalar product, the D'Alembertian, we can finally apply this to actual electromagnetic fields.
Which requires us to look at potentials. In classical electromagnetism, we had a scalar potential, which is related to static electricity, and we had a vector potential, related to magnetic fields and moving currents.
But Feynman shows us that in relativity, we combine them. We merge the scalar and vector potentials into a single unified 4-vector. The 4 potential.
Because they are different aspects of the same physical thing. Figure 25-2 illustrates this perfectly. Imagine a charge moving along the x-axis.
Okay.
In a coordinate system moving exactly with that charge, the charge is sitting still, right?
Right. So it only has a simple scalar potential. There's no vector potential because, from that perspective, it isn't moving.
Exactly. But transform that back to a stationary system, and suddenly that single scalar potential transforms into both a scalar and a vector potential.
The single reality splits into 2 phenomena just depending on who is looking. It's like having a 3D object, let's say a solid cylinder casting a shadow on a wall.
Oh, I like that analogy.
Yeah, like if the sun is shining straight down its axis, the shadow looks like a perfect flat circle. That's your observer seeing only a scalar potential.
Right.
But if the sun moves to a completely different angle, the shadow stretches out, and it looks like a long rectangle. You might think a circle and a rectangle are two completely different things, but they're both just different shadows of the exact same 3D cylinder.
The 4 potential is the cylinder. And when we use the 4 potential with our new operators, we arrive at the ultimate payoff.
We can write all of Maxwell's equations in one tiny line. Using the D'Alembertian of the 4 potential equals the flow of charge over epsilon naught. It's stunning.
It is. But this raises an important question. Is this just a cheap trick?
Feynman addresses this with his unworldliness joke, right? The U equals 0 trick.
Yes. He points out that you can fake simplicity. You can take any physical law, rewrite it so it equals 0, like force minus mass times acceleration equals 0, square it, add every law in physics together, and call the sum U.
And then you just declare the supreme law of nature is U equals 0.
Yeah.
Which is technically true, because the only way a sum of squares equals 0 is if every piece is 0.
But it's completely useless. It hides complexity without adding physical insight. When you unwrap it, you are right back where you started.
So is our beautiful one-line 4-vector equation also just a trick?
No. The true simplicity of 4-vector notation is that it wasn't just invented to hide variables. It was designed for the geometry of Lorentz transformations. It mirrors an actual fundamental symmetry of nature. It proves electromagnetism is perfectly invariant under the principle of relativity.
It's simple because nature is simple at that level.
Exactly.
So what does this all mean? We journeyed from redefining time in meters to dodging mathematical traps in velocity, to designing particle accelerators with scalar invariance, and finally seeing how potentials are just different shadows of the same reality.
The takeaway is that learning to speak the universe's native mathematical language ensures that no matter how fast you are moving, the laws of nature will always hold together perfectly.
Which leaves you with a pretty wild thought to ponder on your own. If every true physical law must fit perfectly into this invariant 4D notation to be valid, what entirely undiscovered theories of the universe might be hiding in plain sight right now, just waiting for the right notation to reveal their underlying simplicity?
Have you ever considered that the fundamental rules of the universe, like the deeply ingrained laws we assume are just absolutely carved in stone, might actually be, well, little more than optical illusions, illusions entirely dictated by your current speed?
Yeah, it's an incredibly unsettling thought when you really dig into it.
It is, because, we tend to experience electricity and magnetism as two totally distinct forces. Like you get a static shock from a doorknob, that's electricity. You stick a note to your fridge, that's magnetism.
Right, standard everyday experience.
Exactly. But what if I told you that moving at extremely high speeds literally squashes an electric field into, well, the shape of a flat pancake? Or, and this is even stranger, that magnetism isn't even a unique force at all, that it's essentially just a perspective trick created by an electric field in motion.
We are definitely stripping away the everyday illusions we rely on today. Because when you push objects to velocities approaching the speed of light, those neat little boundaries we draw between these phenomena, they dissolve completely.
They really do. So welcome to today's deep dive. We are taking on a brilliant, famously mind-bending chapter of physics today. Specifically, Volume 2, Chapter 26 of the Feynman Lectures on Physics.
A classic.
Truly. Yeah. And our mission here is to understand the mechanics of what happens to the rules of electromagnetism when things move incredibly fast. Now, for you listening, just a heads up, we are dealing with some heavy relativity math in the source material today.
Oh yeah, lots of equations.
But don't worry, our goal is to dissect the why and the how behind the math. We really want to focus on the visual concepts and those massive paradigm shifts in our understanding of reality.
And, building this from the ground up requires us to confront a surprisingly frustrating problem right out of the gate. Before we can even calculate how a moving electric field behaves, we have to definitively answer one question. Where is the moving object that's creating the field?
Which sounds easy, but it's not, right? Because we're bound by the universal speed limit.
Exactly. Information about a charged particle's location, which propagates as an electric and magnetic 4 potential, can only travel toward us at the speed of light, which we denote as c.
Right, so the information is always essentially lagging.
Precisely. If a charged particle is just flying through space, the field you are physically feeling right this exact instant isn't coming from where the particle is right now. It's coming from where the particle was when it originally emitted that signal.
Okay, wow.
Yeah, the Feynman text actually refers to this path location as the the retarded position.
Okay, I picture it kind of like watching a massive firework explode from a
Oh,
distance.
that's a good analogy.
Right, like you see the visual flash instantly, but the concussive boom of the sound wave takes, several seconds to actually roll over you.
Yeah, the sound is lagging.
Exactly. So if you attempt to locate the fireworks shell in the sky based solely on when the sound hits your ears, you're looking in completely the wrong place. The shell is gone, the ashes have already drifted away. You're basically experiencing a delayed echo of a past event.
That is exactly it. But here is where the math gets, well, it becomes a recursive nightmare.
Oh boy.
Because you're trying to determine a field based on a charge's retarded position in the past, right?
Yeah.
But to know how far in the past to look, you need to know the delay time.
Makes sense.
But the delay time depends on the distance to that past position, which is the very thing you are still trying to figure out.
Wait, so the variables are just constantly chasing each other?
Exactly. It's a loop. But thankfully, the source material outlines this really clever mathematical workaround to bypass that whole recursive loop.
Let's hear it.
If we know the position and the velocity of the charge back at that retarded position, we can just project its path forward. We assume the charge simply kept moving at that exact same constant velocity during the entire time the signal was traveling toward us.
Okay, that is pretty clever.
The elegance of that trick is just staggering. You basically calculate an entirely imaginary coordinate, the projected position, which represents where the charge would be right now if it never accelerated or changed direction, and the math miraculously aligns.
Wait, really? It just lines up perfectly.
Perfectly. If you calculate the fields as if the charge were currently sitting at that imaginary projected position, the formulas spit out the exact correct electromagnetic field you are experiencing in reality.
That is wild. We're essentially using a ghost position to map a real field.
Yes, a ghost position.
Though I assume, since this relies on constant velocity, if the charge, hits the brakes or swerves during that signal delay, our whole phantom projection trick kind of falls apart.
Oh, completely. Yeah, acceleration introduces entirely new complexities, specifically radiation, which absolutely ruins the neatness of the projection. But as long as it's constant velocity, it gives us this flawless anchor point to locate the source of the potential.
Okay, so having anchored the moving charge, we then have to figure out what its electric field actually looks like. And a stationary charge is, well, it's highly intuitive.
Very. It radiates field lines outwards symmetrically in all directions, like a perfect sphere.
Right, a classic Coulomb field. But when you accelerate that charge to, say, 90% of the speed of light, that spherical symmetry, it has to break, right?
It absolutely breaks. The mathematics in the text, specifically when you include the 1 minus v squared over c squared factors, it shows a dramatic geometric distortion.
How so?
Well, as the velocity approaches the speed of light, the denominator in these transverse equations shrinks, and that causes the field strength out to the sides to blow up exponentially. Conversely, the field straight ahead and straight behind the charge becomes significantly weaker.
Okay, so looking at figure 26 of 4 in the text, the visual is just striking. The perfect sphere compresses along the line of motion until it literally resembles a flat pancake of electric force just flying through space.
The pancake field, yes.
Yeah. But I want to pause on this visual for you listening, though, because it invites a major conceptual trap.
Oh, definitely.
Because looking at the squished lines in the diagram, it's incredibly tempting to imagine these field lines as, tangible physical wires stretching through space that are getting physically crushed by the pressure of relativity.
Yeah, we have to be really careful there. The distinction between a physical object and a mathematical model is vital. Field lines are merely visualization tools.
Like contour lines on a map.
Exactly, much like contour lines on a topographic map.
Yeah.
They aren't physical struts. What is actually happening is a profound demonstration of Lorentz contraction.
Walk us through that.
Okay, so imagine you drew the perfectly spherical field of a resting charge on a piece of paper, right? And then I shot that piece of paper past you at near light speed. Relativity dictates that the entire piece of paper and the drawing on it would appear contracted along the direction of motion from your perspective.
So the ink itself would look squished together on the sides and stretched out in the front and back.
Exactly. And the revelation here is that this squished, contracted drawing perfectly matches the real, measured, physical electric field of the moving charge.
Wow.
Yeah, the visualization tool obeys the rules of relativity just as the physical forces do. It's purely a memory trick, but applying Lorentz contraction to a stationary drawing gives you the flawlessly correct relativistic pancake.
That's incredible. So you've got this flattened disk of electricity cutting through the vacuum,
Hmm.
and if that moving pancaked field encounters another moving charge, we kind of cross a threshold.
We absolutely do.
The interaction of those two moving fields basically gives birth to magnetism, and in the process shatters some pretty foundational laws of classical mechanics.
Right, so the source material provides the foundational equation defining the magnetic field, B. It says the magnetic field is equal to the cross product of the velocity, v, and the radioelectric field, E, divided by the speed of light squared.
Okay, that's a bit of math, but what does it mean fundamentally?
Fundamentally, this equation strips magnetism of its mystical, standalone status. Magnetism is purely a relativistic side effect of a moving electric field.
Wait, hold on. So if I am holding a stationary charge and you run past me holding your own charge, from my perspective, your electric field is distorted into that pancake shape. Is that geometric distortion what I am physically feeling as a magnetic pull?
It is the entirety of the phenomena. What you experience as a magnetic force is literally just the relativistic transformation of the other person's electric field.
That is wild. And it sets up one of the most unsettling thought experiments in the entire chapter, I think.
Oh, the crossing proton.
Yes, let's walk through figure 26-6. So we have two protons moving at right angles to each other. Proton 1 is moving straight up the y-axis. Proton 2 is moving straight to the right along the x-axis, and they are perfectly timed to cross paths without physically colliding.
Okay, so let's freeze the frame at the exact moment they cross. Proton 2, which is moving horizontally to the right, is sitting squarely inside the electric field of proton 1. Now, proton 1, moving vertically, does not generate a magnetic field along its own forward line of motion. Therefore, proton 2 experiences only a standard electric repulsive force pushing it away.
Right, so proton 2 just feels an electric shove.
Yes.
But proton 1's experience is completely different, isn't it?
Completely, because proton 1 is moving vertically up the y-axis, right? It is sitting in the electric field of proton 2, so it definitely feels an electric shove.
Sure.
But proton 2 is moving horizontally across proton 1's field of view. And according to the equation we just discussed, that perpendicular motion creates a magnetic field.
Right.
Because proton 1 is moving through that newly established magnetic field, it gets hit with an additional magnetic force. It literally gets pushed sideways.
Okay, the discrepancy there is glaring. Proton 2 feels only an electric force.
Yep.
But proton 1 feels an electric force and a sideways magnetic force.
Exactly.
We've just broken Newton's third law. I mean, every classical physics textbook says that for every action, there is an equal and opposite reaction. If I push you, you push me back with the exact same amount of force.
Right, that's day 1 of Physics 101.
But here, in this specific relativistic cross-section, the forces are entirely unbalanced. Action does not equal reaction.
It doesn't. And the breakdown of Newton's third law creates an immediate crisis regarding the conservation of momentum. Because if the forces are unbalanced, the momentum of the two protons won't add up correctly after they pass each other.
So the math is just broken.
Well, to rescue the laws of physics from complete collapse, we are forced to basically reconceptualize the space between the particles.
Because the momentum has to go somewhere, right? If it's not in the particles, the field itself must be absorbing the hit. We have to treat the invisible electromagnetic field as a physical entity capable of carrying its own momentum.
Yes, the field is acting as a reservoir. The missing momentum from our unbalanced protons is temporarily stored in the electromagnetic field oscillating between them. It proves the field is not just a mathematical concept. It has actual mechanical reality.
That is mind-blowing. So we have electric fields flattening out, fundamental laws of motion cracking, and invisible fields soaking up physical momentum.
It gets messy really fast.
It does. Because our perspective completely alters the forces we measure, we desperately need a reliable mathematical translator. Like, we need a way to seamlessly convert electric and magnetic measurements from one moving frame of reference to another.
And the hurdle there is the sheer amount of data. An electric field has 3 directional components, right? X, Y, and Z.
Right.
A magnetic field also has 3 components. That is 6 distinct pieces of information that define the electromagnetic state at any given point.
And we are operating in 4-dimensional space-time, 3 dimensions of space, 1 of time. In standard 3D math, it's pretty easy to group 3 pieces of information into a single vector, like velocity or angular momentum.
Very easy.
But here we have 6 components and only 4 dimensions to work with.
The math simply has no room for a 6-component vector in 4 dimensions. We have totally exceeded the structural capacity of standard vectors.
It's basically the classic problem of trying to pack a 6-pack of soda into a 4-cup holder. You simply can't force it to fit without dropping something. You have to engineer an entirely new, larger carrying case to hold all 6 components safely as you maneuver through space-time.
That's a great way to put it. And the engineering solution the text introduces is a tensor, specifically the F-mu-nu tensor. It is formally described as an anti-symmetric tensor of the second rank in 4 dimensions.
Okay, that string of terminology is incredibly dense. Let's unspool the geometry of this new carrying case. What does that actually look like?
Well, think of this tensor as a 4x4 grid, a matrix.
Hmm.
We take our 4 dimensions, time, x, y, and z, and cross-match them against each other.
Okay, so 4x4 grid gives us 16 available slots.
Right.
But we only have 6 pieces of data, 3 electric, 3 magnetic. How do we reduce a 16-slot grid down to exactly 6?
That reduction comes from the word antisymmetric. First, what happens if you combine a dimension with itself, time with time, or x with x? In an antisymmetric tensor, anything paired with itself equals 0.
Oh, so that instantly wipes out the 4 diagonal slots on our grid. We're down to 12.
We just cleared out the deadweight. Next, the antisymmetry rule also states that if you reverse the order of a pair, you get the same value, but with a flipped sign.
Wait, explain that.
So if slot row 2, column 3 represents the combination of x and y, and let's say that slot holds a specific magnetic component, then row 3, column 2, which is y and x, holds the exact same magnetic component, just negative.
Okay, so they aren't independent pieces of information. They are just mirror images of each other.
Exactly. So if you clear out the 4 zeros and group the remaining 12 slots into their mirrored pairs, you are left with exactly 6 independent, unique slots.
Wow.
3 perfectly hold the components of the electric field, and 3 perfectly hold the components of the magnetic field. It is just a stunning piece of mathematical efficiency.
It really is.
Yeah.
And it effectively proves that electricity and magnetism are fundamentally inseparable, doesn't it? They aren't separate phenomena awkwardly taped together. They are just different faces of this single, cohesive, 6-component master object, the F-mu-nu tensor.
Exactly.
So what registers as a pure electric field in my frame of reference effortlessly translates into a mixture of electric and magnetic fields in your moving frame of reference, all mapped perfectly by the grid.
And, translating between those frames isn't just a chalkboard exercise either. Physicists actually attempted to take this exact 6-dimensional tensor math and use it to solve a terrifying, intensely practical engineering problem in aviation.
Oh, yeah. The text mentions this historical attempt to fly an airplane blind.
Right.
Because before the advent of modern GPS or advanced radar, pilots flying in heavy fog or thick clouds, they lost all visual reference to the ground. They had absolutely no reliable way to know their actual ground speed, which is a highly dangerous situation.
Incredibly dangerous.
But physicists, armed with the precise transformation equations we've been discussing, believed they had a flawlessly elegant theoretical solution.
Because the theory is impenetrable. We know the Earth projects a natural static magnetic field, which is predominantly vertical, and the airplane is flying horizontally through it.
Right.
The tensor math explicitly states that if you move perpendicularly through a pure magnetic field, your moving frame of reference will experience a brand new transverse electric field. This is the V cross B effect we talked about earlier.
So from the airplane's perspective, the Earth's magnetic field transforms into an electric field.
Precisely. And the proposed instrument design for this was remarkably simple. Engineers would string a long insulated wire horizontally across the plane, basically from wingtip to wingtip.
Okay.
As the plane cut through the Earth's magnetic field, the resulting relativistic electric field would force negative charges to gather at one end of the wire, leaving positive charges at the other.
So all the pilot would need is a voltmeter hooked up to the wire. The faster the plane flies, the stronger the relativistic electric field, and the higher the voltage reading. You literally have a speedometer driven entirely by the fundamental mechanics of relativity.
It's brilliant. The physics is absolutely bulletproof.
Good.
But the execution was a complete failure.
Oh no, why?
Because it completely ignored the chaotic scale of the real world. The electric field generated by a plane moving at standard aviation speeds through the relatively weak magnetic field of the Earth is microscopic. The instrument would be trying to measure a signal on the order of millivolts per meter.
Okay, which works beautifully in a sterilized vacuum chamber in a lab. But the Earth's atmosphere is a messy, highly charged environment.
Exactly. The planet maintains its own natural atmospheric background electricity, continuously driven by global thunderstorms and electrostatic charges in the clouds.
Right, the stat.
This ambient background noise hums along at roughly 100 volts per meter, and it fluctuates unpredictably. So the tiny, elegant millivolt signal generated by the plane's relativity speedometer is just instantly and violently drowned out by the atmospheric noise.
It's basically the equivalent of trying to isolate the sound of a pin dropping while standing in the front row of a heavy metal concert. The signal is there technically, but it's completely imperceptible.
Yeah, that's exactly it. And, the failure of the airplane speedometer really highlights why theoretical physics requires incredibly robust, mathematically airtight foundations. Because when you strip away the atmospheric noise and look at the raw mechanics of a particle in a vacuum, the classical equations we rely on simply stop working.
Right.
We established earlier that moving charges warp fields and break Newton's third law. This means we have to rewrite the most fundamental equation of motion. Force equals mass times acceleration, or F equals ma.
Because time dilation infects the acceleration variable, right? I mean, acceleration is the change in velocity over time. But Einstein proved that if I am observing a particle moving at high speeds, my clock ticks at a fundamentally different rate than a clock moving alongside the particle.
Yes.
So if time is relative, F equals ma falls apart because we literally can't agree on which clock to use to measure the acceleration.
You hit the nail on the head. The relativistic upgrade to classical mechanics requires us to find a clock that all observers can agree on. And the solution is an invariant variable called proper time, which we denote by the letters as.
Okay, so proper time is essentially a hypothetical stopwatch that is permanently glued to the moving particle itself.
Yes, exactly.
Because the clock travels with the particle, it experiences the exact same relativistic stretching and warping. So it measures the pure invariant interval in space-time that the particle experiences, completely regardless of who is watching from the outside.
And by utilizing proper time, we upgrade standard three-dimensional force into the force, or FUMO. The new equation defines force as the rest mass of the particle multiplied by the rate of change of its forward velocity, measured strictly against the proper time, s.
It is a much heavier, far more complex piece of machinery than F equals ma, for sure. But it is universally reliable. It essentially translates classical mechanics into the language of relativity, allowing us to perfectly predict how a particle will carve its path through pancaked electric fields and perspective-shifted magnetic fields without, breaking the universe.
We have basically traded the comfortable, intuitive illusions of our slow-moving daily lives for the raw mathematical operating system of the universe.
It is a massive perspective shift to absorb. Let's recap what we've covered today. We began by realizing that the fields we interact with right now are merely delayed echoes radiating from a retarded position in the past.
Yeah.
We discovered that pushing a charge toward the speed limit of a universe physically flattens its electric field into a disk. We watched as the simple act of two protons crossing paths obliterated Newton's law of action and reaction, forcing the invisible space between them to absorb physical momentum.
A lot of broken laws today.
Indeed. And then we unpacked the brilliant 16-slot geometry of the F-mu-nu tensor, proving definitively that electricity and magnetism are just two mirrored faces of a single, deeper reality.
And the architecture of that reality is strange, no doubt, but it is mathematically flawless, even if our attempts to build airplane speedometers out of it get ruined by the weather.
Right. Which actually leaves us with a rather profound thread to pull on for you listening as we wrap up today. If our perception of a fundamental physical force like magnetism is entirely dependent on the specific frame of reference we happen to be observing it from, it begs a massive question about the nature of reality itself.
It really does.
Does a purely objective, base reality frame of reference even exist in this universe? Or is absolutely everything we experience, measure, and feel entirely subjective to our trajectory through space-time? Something to chew on. Thank you for taking the plunge into the deep dive with us today. Keep questioning your perspective.
You walk into a dark room, right? You reach out, you flip a switch on the wall, and instantly the room just fills with light.
Yeah, it's instantaneous.
Exactly. Or, like, you plug your phone into the wall, and that little battery icon turns green immediately. It feels entirely instantaneous. And to most of us, it feels like a very simple mechanical cause and effect.
Right. Flip switch, get light.
Yeah. But if you actually stop to think about the physical reality for a second, where exactly is that energy? And how physically does it get from the power plant miles away, or even just the wall outlet, into your device?
Well, we rely entirely on a very comforting mental model for this. We imagine the power plant generates the electricity, the copper wire carries it exactly like a pipe carrying water, and the bulb just glows at the end of the line.
Right, the plumbing analogy.
Exactly. It's a beautifully linear, simple pipeline. We picture energy as this neat little substance that just travels quietly down the track we built for it.
But then you open up today's source material, which is chapter 27 of the legendary Feynman lectures on physics, and suddenly that comforting linear pipeline model it shatters completely.
Oh, completely. It's gone.
We are looking at a theoretical landscape here, complete with detailed diagrams, that fundamentally challenges our baseline intuition about how the universe actually works.
Yeah. Today's deep dive takes us into a chapter titled Field Energy and Field Momentum. And our primary mission here is to basically rewire how you, the listener, understand empty space.
Which is quite the mission.
It really is. We are going to explore the ideas, the terminology, and the profound common misunderstandings we all hold about electricity. By the time we finish unpacking this, you will never look at a simple power cord or a magnet on your fridge the same way again.
Because we all know the golden rule of science, right? Energy is conserved. It cannot be created or destroyed.
Right. Physics 101.
Exactly. But the way it is conserved, the incredibly strict rules the universe imposes on how energy actually moves from place to place is so much wilder than just saying, like, it exists here and now it exists over there.
Oh, absolutely.
So let's start with that fundamental rule.
Uh-huh.
What is the difference between energy just existing in perfect balance versus the strict laws governing its movement?
Well, the best way to understand this is to look at what Richard Feynman calls worldwide conservation versus local conservation. Let's imagine you have a pocket of energy or an electrical charge sitting right in front of you at point A.
Okay, I'm picturing it.
And suddenly it starts to fade away. At the exact same millisecond, a brand new pocket of energy appears at point B, which is, say, 100 miles away.
Right.
In a worldwide conservation model, the books are perfectly balanced. The total amount of energy in the universe stayed exactly the same at every single moment. The energy essentially teleported.
It's like checking your bank account. If I use an app to transfer $100 to you, my balance goes down by 100 and yours goes up by 100 at the exact same time.
Exactly.
The money essentially teleported through the digital ether. The ledger balances perfectly without any physical cash moving down the street.
Right, but the universe absolutely forbids magical bank transfers. It demands the armored truck.
The armored truck. Okay, I love that visual. That's perfect.
Yeah, the universe insists on what we call local conservation. If energy disappears from point A and appears at point B, it cannot just digitally teleport. It must physically, tangibly flow through the actual physical space in between those 2 points.
So it actually has to cross the distance.
Yes. There has to be a continuous, measurable flow of energy across the boundaries of any imaginary box you draw around your starting point.
But wait, why? I mean, if the total amount of energy in the whole universe is exactly the same, why is the universe such a stickler for the armored truck?
Right.
Why can't it just balance the overall ledger universally and save the physical trip?
Because of the theory of relativity.
Oh, wow. Okay, bringing Einstein into it.
Have to. Think about that worldwide bank transfer model for a second. It requires the energy to disappear at point A and appear at point B simultaneously. But Albert Einstein proved that simultaneous moments don't actually exist. They are an illusion based on your perspective.
Ah, because the speed of light is the absolute speed limit of the universe.
Right.
So if I am, like, flying past the Earth in a spaceship at a massive fraction of the speed of light, my definition of what happens at the same time is entirely different from your definition standing still on the ground.
Exactly, which creates a massive problem for teleporting energy. To an observer flying past in that spaceship, their perception of time is skewed. It might look to them like the energy appeared at point B a few seconds before it actually disappeared from point A, or vice versa.
Wait, so from their perspective, for a few seconds, the universe had extra energy that was magically created out of nothing.
Yep. Or energy was destroyed entirely, depending on the direction.
And that breaks everything.
It breaks the fundamental rule of relativity, yeah. That the absolute laws of physics must look the exact same to everyone, no matter how fast they are moving. You cannot have a universe where one person sees energy perfectly conserved and someone else sees energy magically doubling or disappearing.
Okay, I see.
So the only way to ensure the laws of physics survive, the only way everyone, everywhere, perfectly agrees that energy is conserved is if the conservation is strictly local. The energy has to pack up and physically drive the armored truck through the physical space in between point A and point B.
That makes so much sense. Okay, so if the energy has to physically drive the armored truck through the empty space in our living rooms, we need a way to track that truck, right? We need to map its route through the invisible air.
Precisely. And in the study of electromagnetism, we track that flow using two specific tools. First is energy density, which physicists usually represent with the letter U. Yeah, and that just means the sheer amount of electric and magnetic energy sitting inside a specific volume of space at any given snapshot in time. Second is a concept called the pointing vector.
Which I have to say is an incredibly convenient name because it literally points to where the energy is going.
It does.
Even though it's actually named after a British physicist, John Henry Poynting, who developed it back in the 1880s.
It is a very happy historical coincidence for sure. So the pointing vector is a way to calculate the exact direction and the rate that electromagnetic energy is flowing through physical space.
And how do you find it?
You find it by looking at how the electric field and the magnetic field interact. In math, when two distinct fields push against each other at a right angle, the resulting force shoots out perfectly perpendicular to both of them.
Okay, so if we visualize that if the electric field is pushing straight up from the floor to the ceiling, and the magnetic field is pushing left to right across the room.
It are hitting each other at a 90-degree angle.
Right.
The resulting energy flow, the pointing vector, is pushed straight forward. It shoots straight ahead, perpendicular to both of them. It is very similar to how water is squeezed out of a sponge when you apply pressure from two different sides, or how a ship is pushed forward by the interaction of wind and a rudder at different angles.
But wait, I have to challenge this premise, because Feynman himself drops a massive caveat in the text right around here.
He does, yeah.
We're treating this mathematical formula, this pointing vector, like it is the absolute gospel truth of where energy lives.
Mm-hmm.
But Feynman admits we don't actually know if this specific formula is the only right way to locate energy in space.
We don't. Mathematically speaking, you could invent an infinite number of different highly complex formulas for energy density and flow that would still perfectly balance the books of conservation.
Really? Infinite?
Yeah, I mean, you could add all sorts of complex derivatives and hidden variables, and the math would still technically work out at the end of the day.
So why do we use this specific one? Why is John Henry Poynting's vector the one the entire scientific community agreed to build their foundation on?
Mostly because it is the simplest possible mathematical form, and nobody has ever found a real-world experiment where it fails to perfectly describe reality.
If it ain't broke, don't fix it.
Exactly. But more deeply, we know that electromagnetic energy must have a precise, singular physical location in space because of gravity.
Wait, gravity? What does gravity have to do with the magnetic field around my phone charger?
It comes back to Einstein again. Think about how the sun's immense gravity physically bends the light from distant stars passing behind it.
Right, the famous eclipse experiment.
Yes. If gravity can pull on a beam of light, that means the light and the electromagnetic energy it carries must have physical mass. And if it has mass, it must exert its own gravitational pull on the universe, however infinitesimally tiny. According to the theory of general relativity, all energy is a source of gravity.
Oh, wow. Okay, so if field energy exerts a gravitational pull, it can't just be an abstract mathematical concept. It has to exist at a very specific set of x, y, z coordinates so the universe knows exactly where that gravity is pulling from.
Precisely. We just don't have scientific instruments sensitive enough yet to physically weigh an electromagnetic field in a laboratory to prove its exact, precise location down to the millimeter.
Right.
But we know it has to be there. And the pointing vector is the model that perfectly balances the books and describes reality without fail.
Okay, if we trust the formula, let's see what happens when we actually apply it to everyday things. Because this is where the textbook forces us to abandon our intuition completely. Let's look at a few scenarios. I mean, a beam of light is an easy baseline, right?
Yeah, in a light wave, you have an electric field and a magnetic field oscillating at right angles to each other. Because they are perpendicular to the direction the light is traveling, the math dictates that the energy flows straight ahead.
So the energy flows exactly where you point the flashlight.
Exactly. The formula perfectly matches our everyday intuition there.
The flashlight makes total sense because the energy is moving forward. But what happens when the energy hits a dead end?
Like what?
Like when you plug in your phone and charge a battery, or say, charge a capacitor. Imagine a simple capacitor, two flat, circular metal plates sitting parallel to each other with a small gap of empty air in between them.
Okay, got it.
We hook the plates up to copper wires on the outside and pump electrical current in. Our mental pipeline model says the energy flows straight down the physical wires, hits the metal plates, and builds up there.
But if you look at the physical mechanics of the fields, detailed in figures 27.3 and 27.4 of the text, the physical reality is entirely different.
How so?
Inside that tiny gap of air between the plates, an electric field is building up, pointing straight across the gap. At the same time, because the field is changing, it generates a magnetic field that loops around the outside edge of the plates.
Okay, so we have an electric field pointing across the gap and a magnetic field circling the gap. They are right angles.
And when they push against each other, they funnel the energy. The pointing vector shows the actual energy flow is parallel to the plates. It points radially inward, straight into the gap from the outside edges.
Wait, meaning the energy is not coming down the wires at all?
No, the actual physical energy that charges the capacitor is flowing inward from the completely empty space surrounding the outer edges of the plates.
I'm sorry, what?
Yeah, as you bring electrical charges together in a system, the wider electromagnetic field in the surrounding room physically moves toward the capacitor and rushes into the open gap from the sides.
I am really struggling to accept that. I mean, if the energy to charge the plates is literally just collapsing in from the empty air in the room, why do we even need the copper wires plugged into the wall? What are they even doing?
The physical copper wires are merely tracks. They are guides. The voltage in the wires is laying down the specific field conditions, creating the necessary electric and magnetic pressures in the environment.
Okay, so they're just setting the stage.
Yes. Those field pressures are what actually funnel the energy from the surrounding space into the gap. The wire is not a pipe carrying water. It is more like a trench you dig so the surrounding groundwater knows where to pool.
A trench for the groundwater.
Yeah.
Wow. Okay, that is wild for a dead-end capacitor.
Yeah.
But what if the wire is the destination?
What do you mean?
Think about a toaster or an electric heater. You have a piece of high-resistance wire, and electrons are being violently pushed through it, grinding against the metal, creating friction and heat. Surely, in that scenario, the actual energy is moving inside the copper pipe.
Let's look at the mechanism. When you push current through a high-resistance toaster wire, there is a voltage drop along the wire. That voltage drop creates an electric field in the empty air just outside the wire, running perfectly parallel to its surface.
Okay.
At the same time, the moving current creates a magnetic field that loops tightly around the outside of the wire.
So again, in the completely empty air just outside the surface of the copper, we have a parallel electric field and a circling magnetic field. They cross at right angles.
And their interaction creates a pressure that points straight inward, radially inward, toward the center of the wire from every single direction in the empty space outside it. The energy converges on the wire from the room.
Wait. So the electrons grinding around inside the toaster wire are getting the energy they need to generate heat from the invisible empty space outside the wire.
Figure 27.5 in the text illustrates this beautifully. Our baseline intuition says the electrons get their energy from being violently pushed along the wire, like water under pressure in a hose.
Right, that's what I thought.
But the physical reality says the electrons get their energy from the fields flowing into the wire from the outside environment. The energy flows from distant charges, travels through the wide area of space around the setup, and then converges inward, entering the wire from all sides to become heat.
All right, I'll buy that for moving current. The moving charges create the fields. The fields push the energy inward. But what if absolutely nothing is moving? What if we have a completely static situation?
Okay, let's do it.
Let's take a simple point charge, like a tiny sphere holding static electricity, and set it on a table next to a regular bar magnet.
Yeah.
Nothing is moving. Nothing is heating up. It's a completely dead, silent system.
It looks dead to our eyes, but the static charge is constantly radiating an electric field outward. The bar magnet is constantly looping a magnetic field outward. Those two invisible fields occupy the exact same physical space in the room. They cross each other at angles.
And the absolute rule of the pointing vector is that wherever an electric field and a magnetic field cross,
You have a physical flow of energy.
even in a dead system,
Yes. Even though absolutely nothing is moving and the system is dead, the math relentlessly describes a constant, continuous flow of energy circulating endlessly around the magnet and the charge, like an incompressible fluid that just keeps flowing around in circles forever.
it's like staring at a perfectly calm, still pond, right? Only to have a physicist tap the glass and tell you there is a massive, violent, invisible whirlpool spinning continuously right beneath the surface for no apparent reason. It feels absurd.
It really does.
Feynman himself jokingly calls the theory nuts at this point in the text. I mean, it feels like the formula is just spitting out bad data because we fed it a weird edge case scenario.
It absolutely feels like a glitch. I mean, why would energy circulate in a dead system? But this absurd invisible whirlpool is actually the load-bearing pillar of the entire foundation of physics. It is the key to the final, most crucial concept in the chapter, field momentum.
Okay, let's unpack that. If energy physically flows through space, like the armored truck driving down the highway, it doesn't just have a location. It has physical momentum. It has the power to physically push things.
Exactly. There is a fundamental, unbreakable theorem in mechanics. Whenever energy flows in any circumstance, the momentum density in that space is perfectly equal to the energy flow divided by the speed of light squared.
So the pointing vector divided by c squared.
Right. If energy moves, it carries physical momentum.
To prove that pure energy carries physical momentum, the text walks us through a brilliant thought experiment from Albert Einstein. We have to visualize a massive, perfectly frictionless boxcar sitting completely still on a set of train tracks.
Okay, got the boxcar.
Inside the train car, at one end, there is a device that shoots a single flash of light, a burst of pure energy to the opposite wall.
Just a flash of light.
Yeah.
No solid matter, no bullets, just energy.
Exactly.
Now remember what we established earlier with gravity. Energy has mass. The mass is equal to the energy divided by the speed of light squared. So when that flash of light physically travels from the back wall of the train car to the front wall, actual mass is physically moving from one side of the closed boxcar to the other.
Which means the center of gravity of the entire train car is shifting forward.
But physics forbids that.
Right.
You cannot permanently move your own center of gravity by simply doing things inside a completely closed, frictionless system. You cannot lift yourself up into the air by pulling up on your own shoelaces.
So to compensate for the invisible mass of the light moving forward, the massive heavy metal train car must physically recoil backward down the track when the light is fired, and then stop when the light hits the opposite wall.
Yeah.
The center of mass of the whole system has to stay in the exact same place.
Yes. And for that incredibly heavy physical train car to be pushed backward, the burst of light must have exerted a massive physical force against the wall when it was emitted. The light must carry actual physical momentum. The math dictates it perfectly.
That is such an elegant, simple way to prove that pure energy can push physical objects. I love that. But what if we change the direction?
Okay, how so?
Let's say the boxcar is already rolling smoothly down the track at a steady speed, and instead of shooting the laser forward, I shoot the laser from the floor of the train straight up to the ceiling.
Ah, now we are dealing with angular momentum.
Right.
Let's anchor this. Think about a figure skater spinning on the ice. When she pulls her arms in close to her body, she spins much faster. When she extends her arms out, she slows down. That is the conservation of angular momentum. The total amount of spin in a system has to remain constant, but it changes based on how far the mass is from the center pivot point.
Okay, so applying that to the train. Well, the train is moving forward down the track. The light flash shares that forward velocity. But as the light travels up from the floor to the ceiling, its distance from the pivot point, the track below, is increasing. It's like the figure skater extending her arms.
Exactly. To conserve the angular momentum of the entire moving system, that upward flash of light must carry horizontal momentum with it. If the light did not carry momentum, the whole train system would suddenly slow down or speed up in a way that violates the fundamental laws of conservation. The universe would spin out of control.
So pure, empty electromagnetic fields can carry linear momentum to push a train and angular momentum to control a spin. Let's bring this all the way back to the static magnet and the static charge sitting quietly on the table. The invisible, absurd whirlpool spinning beneath the calm pond. Why does it exist?
Because energy carries momentum. A circulating flow of energy in empty space means there is actual physical angular momentum hidden in the void around the magnet.
Hidden in the empty space.
Yes. Think about a classic puzzle in physics. You have a plastic disc with some electrical charges mounted on it, and it's sitting inside a strong magnetic field. The disc is disconnected. Everything is completely still.
Okay.
Then you flip a switch and turn off the magnetic field. Suddenly, the disconnected disc starts violently spinning on its own.
It looks like pure magic. Where did the rotational push come from if nothing physical touched the disc?
It comes from the invisible whirlpool. When you initially built up that static magnetic field around those charges, you created a circulating Poynting vector in the air. You locked actual physical angular momentum into the empty space itself.
Oh, wow.
It was just sitting there, spinning invisibly like a loaded spring. When you turn off the field, that hidden momentum has to go somewhere. It cannot be destroyed. So it drops out of the invisible space and physically slams into the disk, making it spin.
So what does this all mean? It means these counterintuitive ideas, energy funneling in from the sides of a wire, invisible whirlpools circulating around dead magnets on a desk.
Right.
They aren't just mathematical quirks. They are the absolute load-bearing pillars holding up reality.
Right.
If the empty space doesn't hold the momentum, the math breaks down and the whole physical world falls apart.
And that is precisely why Chapter 27 of Feynman is so vital to understand. It forces us to completely abandon the simplistic, linear pipeline models of how our world operates.
Let's recap our journey today. We learned that energy doesn't digitally teleport from place to place. It physically drives an armored truck through the space in our rooms.
Yep, the local conservation.
We learned that energy physically flows into your toaster wires from the outside air rather than being pushed down inside them. We learned that energy endlessly circulates around static magnets, and that this flowing invisible energy carries literal physical momentum that can push train cars and spin physical objects.
And if we connect this directly to your daily life, every single piece of technology you use, from the screen you were looking at right now to the battery inside it, relies entirely on these invisible field mechanics.
That's all around us.
The physical copper wires and the silicon traces, they're mostly just trenches. They are guides. The actual heavy lifting of the energy transfer that powers your entire modern life is happening in the empty space surrounding those wires.
The physical wires just tell the empty space what to do. I want to leave you with a final thought to chew on today. Think back to that light switch from the very beginning of the deep dive.
The simple flip of a switch.
You flip it, the room instantly lights up. But now you know the underlying physical truth. The energy didn't just flow through the walls like water inside a pipe. The invisible electromagnetic fields sitting entirely still in your room right now, right where you are sitting, possess actual physical mass.
It's wild to think about.
They carry literal momentum that can exert a physical push. They exert a tiny gravitational pull on the objects around them. So does the concept of empty space even exist at all? Or are we all just constantly, unknowingly swimming through a heavy, invisible ocean of locked-up energy? Look around you right now. Every device, every light bulb, every screen you see is running on this unbreakable set of mathematical rules.
Yeah, the laws of classical electromagnetism.
Exactly. They're like the ultimate operating system for reality, right? The rock-solid code that lets us build electric motors and, power entire cities.
It feels rock solid, definitely.
Right. But what if I told you that hidden right there in that foundational code of the universe is this totally fatal universe-breaking glitch?
And you don't even have to look at like a supermassive black hole to find it.
No, you don't. You just have to look closely at the simplest object imaginable, a single electron.
Yeah, the whole architecture of classical physics just completely falls on its face the moment you try to zoom in on that one particle.
It's wild. So that is our mission for today's deep dive. We are exploring the legendary Feynman lectures on physics, specifically looking at a mind-bending puzzle known as the electromagnetic mass problem.
Which is such a fascinating chapter, Chapter 28 in Volume 2.
Yes. We're going to unpack the paradox of the point charge, discover how an electron, literally fights against its own movement, and look at the wildly creative and honestly desperate ways physicists have tried to fix this bug.
And we really need to emphasize for you listening right now that this isn't just some dusty historical footnote.
Right. People think quantum mechanics just fixed everything.
Exactly. It's so tempting to assume quantum physics came along and cleanly patched all these classical errors, but it didn't. The fundamental trouble with the electron's mass is still an unsolved mystery today.
Even with all our upgrades to reality, the bug is still there. So let's unpack the actual glitch. To understand where the math breaks, we have to start with a seemingly simple task, right? Just calculating the energy of a single charged particle.
Sounds straightforward.
Right, but it leads straight into a mathematical brick wall.
So let's do a thought experiment. Imagine an electron as this tiny, solid sphere of negative charge, like a microscopic marble.
Okay, got my tiny marble.
Now, it has a specific measurable radius. And surrounding this little sphere is an electromagnetic field.
Right.
If we want to calculate the energy stored in that field, The math basically tells us it's a tug of war between the amount of charge the electron has and the size of the sphere.
It's inversely proportional, right? So if you make the sphere smaller...
The energy spikes upward, exactly.
And here is where the great difficulty comes in.
Yeah.
Because an electron isn't supposed to be a tiny marble.
Right. According to our best understanding, it's a fundamental particle, a true point charge.
Which means it has no internal structure, no volume at all. So we have to shrink that imaginary sphere's radius all the way down to absolute zero.
Which creates a total mathematical catastrophe.
Because you can't divide by zero.
Anyone who remembers middle school math knows that. As that radius gets smaller and smaller, the energy in the field gets bigger and bigger.
And if it hits zero, it shoots straight to infinity.
Infinite energy, yes.
Which is just a massive red flag in physics. I mean, to help you visualize this, it's like trying to pack an endless number of highly repulsive magnetic springs into a smaller and smaller box.
That's a great analogy.
Right. The tighter you pack them, the more aggressively they push back against each other. So you try to crush all those springs into a box that literally has no volume, a dimensionless point, the stored pressure just becomes infinitely huge.
And nature abhors infinity. I mean, if the electron just sat there doing nothing, maybe we could turn a blind eye to it. But energy matters the second things start to move.
Because the field moves with it.
Exactly. When a charged particle moves through space, its electromagnetic field carries momentum. The electric and magnetic fields interact in this specific way that creates a flow of momentum directed straight forward.
There's actually a really cool visual for this in the text, figure 28-1.
Yes. If you picture slicing up the empty space around that moving electron into little rings, which is what figure 28-2 shows, you can calculate the momentum in each slice.
And because the electron is perfectly symmetrical, all the sideways pushes cancel out.
Perfectly cancel out. So what you're left with is a net momentum pointing straight along the path of motion. The field itself is literally carrying momentum.
Okay, but here is the massive, mind-blowing aha moment. When you calculate the total momentum of that moving field, it turns out to be directly proportional to the electron's velocity.
Which is huge. Because what do we call a property that gives an object momentum proportional to its velocity?
We call it mass.
Mass. Exactly. This gives us the concept of electromagnetic mass.
And when physicists first realized this, it sparked this incredibly thrilling pre-relativity dream, didn't it?
Oh, absolutely. They thought, what if the electron doesn't actually have any inherent mechanical mass at all?
Like, what if mass as a fundamental concept doesn't even exist? What if all mass in the universe is just an illusion created by the momentum of electromagnetic fields?
It was such an elegant idea. The origin of mass was a total mystery back then. Suddenly, Maxwell's equations seemed to offer a magical answer to everything.
So they tested it, right? By calculating how big the electron would have to be if every single ounce of its observed mass was just generated by this field.
Yeah, and they derived a specific number, which we still call the classical electron radius.
Which is completely theoretical, right? Like 1/100,000th the diameter of an atom.
Something like that. But, and here's the tragic part, this beautiful dream shatters the moment Albert Einstein walks into the room.
Right, because of relativity.
Yeah. If all mass is just an electromagnetic illusion, then the different ways of calculating that mass have to perfectly align.
Because E equals mc squared. The energy and the mass are locked together.
Exactly. So if we calculate the electron's mass based on its field energy, we get one number. But if we use the field's momentum, we get a different number.
It's this incredibly frustrating algebraic mismatch.
Yeah, the mass from the energy equation has a 1/2 coefficient, but the momentum equation gives a 2/3 coefficient. They don't match.
And relativity says they absolutely must match.
Right. So that flashing warning light tells us something is fundamentally missing from our picture.
Okay, but wait, I need to push back on this whole model for a second because something is bugging me.
Go for it.
We're talking about the electron as a single, indivisible point of negative charge, or like a tiny sphere where all the charge is negative. How does it even hold itself together? Right? If every single piece of it is negatively charged, shouldn't it just intensely repel itself and instantly explode outward?
You've isolated the exact flaw in the purely electromagnetic dream.
Okay, so I'm not crazy. What is actually pushing inward to keep it intact?
Well, if the electron has any physical size at all, it should violently detonate. So we're forced to imagine that something else, something totally unknown, is holding it together.
And this brings in the French physicist Henri Poincaré, right?
Yes. He proposed that there must be non-electrical forces at work inside the particle. He called them Poincaré stresses.
Which to me just sound like mysterious, invisible rubber bands holding the universe together.
That's essentially what they are. It's mathematically necessary. If you calculate the energy and momentum of these mysterious inward-pulling rubber bands and add them to the equations,
The mismatch disappears.
it finally disappears. The energy mass and the momentum mass perfectly align at that 4/3 ratio.
But the cost is devastating. The dream is dead.
The beautiful dream is completely dead. We can't say mass is purely electromagnetic anymore.
Right, because we had to introduce these messy, outside, non-electrical rubber bands.
And as soon as you put rubber bands inside an electron, you get 100 new questions, like does it vibrate, does it stretch? It ruins the elegance.
And it gets infinitely weirder when the electron actually starts moving. Because electromagnetic influences take time to travel, right? So the forces inside the electron get entirely out of whack when it accelerates.
Yeah, we call this concept retardation. Even though the signal moves at the speed of light, it takes time to travel from one side of the electron to the other.
Because it actually has a tiny physical size in this model.
Exactly. Imagine figure 28-3 from the lectures. When the sphere is perfectly still, all the repulsive forces pushing out balance the rubber bands pulling in. Everything is calm.
But when it hits the gas and accelerates forward, that equilibrium just shatters.
Because the front of the electron is reacting to where the back of the electron used to be, a tiny fraction of a second ago.
Right. The internal forces get unaligned. And the text explains that the electron literally exerts a force on itself. A self-force.
Yes.
Trying to visualize this is wild. I like to think of it like try to accelerate a speedboat that has a massive open pool of water sitting on the deck.
Oh, I like that.
Right. When you hit the gas and the boat surges forward, the water inside the pool sloshes violently to the back. And that sloshing water pushes against the back wall, literally fighting against the boat's own acceleration.
That is a brilliant analogy. The electron's own field acts exactly like that sloshing water. It pulls back against its own motion.
But the math of this self-force is a two-part monster, isn't it?
It really is. The first part of the formula is tied directly to the acceleration itself. And if you shrink the electron down to a point charge, this part of the force shoots to infinity.
So the infinite mass problem just rears its head again. It would take infinite energy to accelerate the boat.
Exactly. But we can't just throw the whole equation away because the second part of the formula is absolutely essential.
The radiation resistance.
Yes. It's tied to the rate of change of acceleration. And it's a verified, real-world phenomenon. When you accelerate a charge, it radiates electromagnetic waves.
It broadcasts energy out into the universe, which is literally how radio antennas work.
Exactly. And to conserve energy, that broadcasted energy has to come from somewhere. It actually has to be physically harder to push an accelerating charge than a neutral object.
Because you're pushing against the radiation.
Right. That extra resistance is radiation resistance. And for a single electron floating in empty space, the only possible source of that force is the electron acting on itself.
So physicists were basically backed into a terrifying corner. We desperately need the self-force to explain why antennas work.
But we hate the self-force because it gives the electron infinite mass.
It's like a video game developer trying to fix a glitch in a character's movement code, right?
Yeah.
You patch it, and suddenly you realize you've accidentally broken the game's entire gravity engine.
That's exactly how it felt. You can't just delete the self-force without breaking the fundamental conservation of energy.
So how did these brilliant minds try to fix it? Because the workarounds get pretty wild here.
Oh, they took incredibly desperate measures. They realized they had to literally hack the foundational laws of Maxwell's equations.
Some of these sound completely absurd, like Paul Dirac's idea.
Dirac's advanced waves.
Yeah.
It's ingenious, but mathematically bizarre.
I was reading this part, and it genuinely sounds like science fiction. Because standard waves, like if you throw a rock in a pond, the ripples move outward, forward in time. Those are retarded waves.
Right.
But advanced waves are ripples that start at the edge of the pond and travel inward, converging on the rock before it even hits the water. They travel backward in time. Was Dirac seriously suggesting the electron uses time travel?
Mathematically, yes. He proposed that an electron reacts to a combination of its own fields. Half travels forward in time normally, but the other half travels backward in time.
That's insane.
But here's the magic. When you combine the math of these forward and backward waves, a miraculous cancellation happens. The backward advance waves perfectly cancel out the term that causes the infinite mass.
Oh, wow.
But crucially, they leave the radiation resistance term perfectly intact.
So it's the perfect math trick. You fix the glitch without breaking the radio antenna.
Exactly. But it requires the electron to respond to waves from its own future.
Which is hard to swallow. And if you think that's wild, the Wheeler-Feynman theory takes it a whole step further.
Oh, the Wheeler-Feynman absorber theory.
Yeah, they proposed the electron doesn't interact with itself at all. The whole self-force is an illusion.
It really is a masterpiece of cosmic orchestration. In their model, when you shake an electron here on Earth, it sends a signal out into the void.
And it travels forward in time until it hits every other electron and proton in the entire cosmos.
The distant stars, the galaxies, everything. And then all those distant charges shake in response. But they instantly push back using Dirac's time-traveling advanced waves.
Backward in time. So the combined echo from the entire universe converges perfectly back on your original electron at the exact moment you started shaking it.
Yes. So the resistance you feel when you push that electron, the radiation resistance, is actually the combined pushback from the rest of the universe.
You literally have to shake the universe to explain an antenna on Earth. It's beautiful,
Yeah.
but incredibly complex. Were there any simpler hacks?
Fritz Bopp tried a much more pragmatic approach. He looked at the underlying problem. The classic rule that says the force gets infinitely strong as distance shrinks to zero.
Right, the infinite spike.
So he proposed just mathematically rounding off the sharp edges. As you can see in figure 28-4, he introduced a narrow mathematical function that smooths out the spike.
It's like putting a speed bump right before you hit the zero mark.
Precisely. At normal, everyday distances, his math acts exactly like standard classical theory. You'd never notice. But when you zoom down to the core of the electron, it rounds off the infinity.
Keeping the mass finite. So we have time-traveling waves, universe echoes, and mathematical speed bumps. Did any of these actually work in the long run?
Well, the ultimate reality check is quantum mechanics, and none of these classical hacks survived the transition.
Wait, really? None of them?
None. When quantum electrodynamics, or QED, was developed, physicists crossed their fingers and hoped the infinite mass problem would just naturally blur away.
Because of the uncertainty principle and all that.
Exactly. But it didn't. The infinities remained. Even in quantum physics, there is still no completely consistent theory that doesn't produce an infinity for the self-energy of a point charge.
Okay, wait. If the math still produces infinity, how do modern physicists actually build models? I mean, I've heard the term renormalization. People say it's just sweeping the infinity under the rug. Is it just a cover-up?
It's much more sophisticated than sweeping it under the rug, though some physicists do still find it philosophically troubling.
Because it feels like a cheat.
Kind of. Renormalization is a process of recognizing that our equations produce two infinities, an infinite theoretical bare mass and an infinite theoretical field energy.
Okay.
So they figured out a mathematical framework where you can carefully subtract one infinity from the other. They cancel out, and what's left is a perfectly finite number that matches the real-world mass of the electron.
That is wild. It's like balancing a ledger, where both the income and the expenses are infinite, but somehow the profit is exactly $5.
That's actually a great way to put it. It works practically, but it means the underlying glitch, the fact that the equations generate infinities in the first place, is still hiding in the architecture.
Which brings up a fascinating real-world question. After hearing how totally broken the math is, you might be wondering if electromagnetic mass is even a real thing, or just a phantom of bad equations.
Right. But surprisingly, nature has given us a perfect laboratory test to prove that electromagnetic mass is very real.
And this brings us to protons and neutrons.
Yes. The nucleus of an atom is held together by the strong nuclear force. And as far as the strong force is concerned, protons and neutrons are completely identical twins.
It treats them with exact mathematical equivalence.
Exactly. The only difference is their electric charge. The proton is positive, the neutron is neutral. So if the strong force treats them equally, any difference in their mass must be purely electromagnetic.
Okay, let's follow the logic here. The classical theory says the charged particle, the proton, has an electric field, so it should have extra electromagnetic mass.
Right.
But the neutron is neutral, so it shouldn't have that extra field mass. It should be lighter. But if you look at the actual data, the neutron is measurably heavier. It's heavier by like 1.3 MeV.
It looks like a massive contradiction.
Right. Is the theory just totally backward?
It looks that way until you look closer. The neutron isn't just a blank, featureless billiard ball, it has a deeply complex internal structure.
Which figure 28-5 illustrates perfectly.
Yes. A neutron actually spends a portion of its existence as a proton, surrounded by a tightly bound cloud of negatively charged particles called pi mesons.
Ah, so even though the total charge from the outside is 0, inside the neutron, there are positive and negative charges intensely interacting.
Exactly. It has internal electromagnetic energy, and if you isolate the pi mesons themselves, the charged versions are measurably heavier than the neutral ones. So it perfectly aligns with the theory. Having a charge genuinely adds mass. Electromagnetic mass is absolutely real.
But to understand why this internal structure matters, you have to realize how different the nuclear force is from the electric force, right? Because they don't act the same way at all.
Not at all. We call the nuclear field a Yukawa potential, which you can see graphed in figure 28-6.
Electromagnetism reaches across the universe. It's like a massive invisible magnet. But the nuclear force is completely different.
It has an incredibly steep exponential drop-off.
I think the best way to visualize the Yukawa potential is comparing a magnet to a piece of Velcro.
Oh, Velcro, yeah.
The electromagnetic field is a magnet. You can feel it pulling from inches away, stretching out forever. But the nuclear field is Velcro. It's incredibly strong, but it only works when the two pieces are perfectly microscopically touching.
If they're a hair apart, the force drops instantly to 0. That's a brilliant way to frame it. And because the nuclear force is Velcro, the complex internal structure of these particles basically determines their mass.
So we know electromagnetic mass is real, but we still can't calculate the baseline mass of an electron without hitting that infinite wall.
Nope.
And just to add supreme insult to injury, we have to talk about the universe's biggest troll, the muon.
Oh, the muon is the most perplexing particle we've ever discovered.
It behaves exactly like an electron in every conceivable way, right? Same charge, same spin. If you ran a battery on muons, your devices wouldn't know the difference.
It'd run perfectly fine.
But for some completely unknown reason, the muon is over 200 times heavier than the electron.
206 times heavier, to be exact. It makes absolutely no sense based on our current theories.
It's like going to the grocery store, buying a perfectly normal-looking apple, and when you pick it up, it weighs as much as a solid bowling ball.
It's arguably one of the greatest unsolved mysteries in particle physics. I mean, if we don't even know where the electron gets its mass, the muon is just an even darker puzzle.
Are there any theories?
Some theorists hold out hope that when we finally discover the flawless equation for mass, it'll be a quadratic equation with two distinct solutions, one for the electron, one for the muon. But right now, we're entirely in the dark.
So let's pull all of this together. We started with the mathematical beauty of calculating field energy, but that led us straight into the terrifying infinity of the point charge.
Yep, the exploding electron.
We had to wrap it in mysterious rubber bands. We watched it fight its own acceleration like a boat with sloshing water.
We traveled backward in time with advanced waves.
Shook the entire universe just to broadcast a radio signal. And we learned that even with quantum mechanics, physics is still fundamentally searching for the true origin of mass.
It's deeply humbling. We can build global power grids and quantum computers using these laws, but the deepest bedrock foundations still have cracks we haven't repaired.
I want to leave you with a final kind of mind-bending thought to mull over, a thought that builds on this entire paradox.
Let's hear it.
We saw how an unimaginably tiny point charge can warp the fields around it so intensely that its energy shoots straight to infinity. If the mere existence of a solid point breaks the math of the universe so violently, maybe we need to completely rethink what a particle actually is.
That's a profound question.
Right. Like, could it be that the very idea of a solid localized particle is just a human illusion? What if the universe isn't made of tiny billiard balls at all, but is entirely made of nothing but interacting, vibrating fields? Maybe the glitch isn't in the math itself. Maybe the glitches are stubborn insistent on treating the electron as a solid thing in the first place.
You know, imagine you're sitting in a car and someone just glues the gas pedal right to the floor.
Oh, that sounds safe.
Right. You're shooting straight ahead, accelerating nonstop, faster and faster. And that is essentially what it's like to be a charged subatomic particle placed inside a uniform electric field.
Yeah, I mean, there is absolutely no steering involved in that scenario. It's just pure straight line acceleration, pushing that particle endlessly in one direction.
But now imagine instead of the gas pedal being stuck, your steering wheel gets locked into a hard turn.
Okay.
You aren't speeding up, you're just trapped, going in an endless circle. And that simple difference that locks steering wheel is exactly what a uniform magnetic field does to a moving particle.
Hmm. And that fundamental behavior really is the starting point for some of the most complex engineering in human history.
It really is. It's the secret to how scientists manage to herd the invisible world. So today, we're doing a deep dive into the brilliant, honestly kind of counterintuitive physics of moving charges.
Yeah, we're going to explore how locking that subatomic steering wheel lets us do incredible things, like
Sure.
uh, physically sorting atoms, attempting to photograph the molecular structure of DNA.
Which is wild.
Right. Building particle accelerators the size of small cities, and believe it or not, even popping the popcorn in your microwave.
Yeah, we're really going everywhere today. But we should probably unpack that circular motion first, because from the text, a magnetic field doesn't just make things spin in flat little rings.
No, it doesn't. If a particle enters the magnetic field and it already has some forward momentum, say it's moving slightly along the direction of the field lines, it doesn't just go in a flat circle.
Right.
It keeps moving forward while it's turning.
So it traces out a corkscrew path, like a spiraling spring, basically.
Exactly, yeah. A cylindrical helix, to use the formal geometric term.
Yeah.
The magnetic field is always pushing the particle sideways, perpendicular to however it's moving. And that constant sideways push is the absolute foundation of all the machinery we're about to discuss. Once you understand that a magnetic field forces a particle into a curve, you can use the geometry of that curve to figure out exactly what kind of invisible particle you're dealing with.
And that brings us to the first major application we found in the sources, right? The momentum spectrometer. I like to think of it as a sorting hat for subatomic particles, because if magnetic fields force particles into circles, I'm guessing not all circles are the exact same size.
Right, they aren't.
Like, does a heavier or maybe a faster particle take a wider turn just because it has more momentum and is, harder to yank inward?
That intuition is spot on.
Yeah.
The radius of the circle a particle makes is directly tied to its momentum.
Okay, so heavier means wider.
Basically, you take a heavier particle or one moving significantly faster, its momentum is higher. When it hits that magnetic field, the field tries to curve it, but that higher momentum means it carves out a much wider, lazier arc. On the other hand, a lighter or slower particle gets whipped into a very tight, small circle. The math links the radius directly to the particle's momentum, divided by its charge and the strength of the magnetic field.
So how does a physicist actually build a machine to use that? Like, practically speaking.
Well, they build what's known as a 180-degree momentum spectrometer. Picture a vacuum chamber with a strong, perfectly uniform magnetic field pointing straight up.
Okay, got the picture.
You shoot a narrow beam of unknown charged particles into it. Because they all have different momentums, they immediately fan out, carving circles of different sizes.
Right.
So all you have to do is place a detector exactly a half circle away, 180 degrees from where they entered. The particles hit the detector at different spots.
Oh, I see.
You measure the distance of the spot from the entry point, and you instantly know the exact momentum of whatever hit it.
That seems incredibly elegant if you have a perfectly neat straight beam of particles.
Which you usually don't.
Exactly. From what I understand about working with something like a radioactive sample, you don't get a neat beam, you get this messy spray of particles flying out at slightly different angles. Wouldn't a messy starting spray completely ruin the clean sorting circles?
You would think so, yeah. And that was a massive hurdle initially. But this specific 180-degree geometry contains a mathematical miracle called focusing.
Focusing, like a camera lens.
Sort of, yeah. Imagine a bunch of particles that all have the exact same momentum, but they enter the magnetic field sprayed out at slightly diverging angles. They'll all take slightly different circular paths, their orbits shifting slightly left or right.
So they spread out, making a blurry mess.
They do spread out initially, but geometry forces them back together. Because they are all tracing circles of the exact same radius, when they complete exactly half of their turn at that 180-degree mark, those diverging paths cross over one another again.
Wait, really?
Yeah, they converge back to a single sharp point on the detector.
That is wild. So you don't need a perfectly aimed laser beam of particles to get a precise measurement. You can just let a messy cone of them spray into the machine, and the magnetic field naturally weaves the ones with the same momentum back together into a tight focal point.
It vastly speeds up experiments. When physicists are trying to measure the distribution of energies in radioactive beta decay, for instance, this 180-degree focusing allows them to capture a much larger fraction of the emitted electrons while still getting incredibly precise momentum readings.
Okay, so the half-circle setup makes total sense for a spray that's contained mostly in one plane. But what if your radioactive sample is incredibly weak?
Hmm.
Like it's barely spitting out any particles at all, and they're
Mhm.
flying out in literally every three-dimensional direction. A simple, flat, half-circle detector wouldn't catch nearly enough to be useful, right?
No, it wouldn't.
So how do you cast a net big enough to catch a sphere of flying particles?
Well, you have to switch from circles to those corkscrews we mentioned earlier.
The helices.
Right. Physicists designed something called an axial field spectrometer. Instead of shooting particles across the magnetic field to make flat arcs, you place the radioactive source directly inside the field, lined up along a central axis.
Okay.
The particles fly out in all directions, but the field forces them to spiral down that central axis.
So you've got this chaotic tornado of subatomic particles spiraling outwards. How do you sort them?
You use physical obstacles. By carefully tuning the strength of the magnetic field, physicists make the particles trace very specific spirals. They place a solid wall in the middle of the chamber, but they cut a specific ring-shaped gap into it, an annulus.
Oh, I see where this is going.
Yeah. Particles with the specific momentum you are looking for will trace a spiral that flares outward, hits its maximum width perfectly at the gap, slips right through the ring, and then spirals back inward to a detector on the other side.
So anything with too much momentum spirals too widely and smashes into the solid wall.
Ye-
And anything with too little momentum spirals too tightly and hits the inner part of the wall. The ring acts like a physical sieve for the corkscrews.
A physical sieve is a great way to picture it, but building that sieve requires a massive volume of a perfectly uniform magnetic field. To pull this off, engineers had to wind heavy electrical wire around colossal, egg-shaped frames, ellipsoids of rotation.
Wow.
And because metal frames would distort the magnetic field, they often built these huge, intricate structures out of wood or aluminum. By calculating the exact spacing of the wires, they synthesized a flawless, bubble-like magnetic field inside.
That is just incredible engineering. So sorting particles by trapping them in loops and spirals is brilliant. But what if we want to actively aim them?
Aim them, right?
Yeah, what if the goal isn't to sort them into buckets, but to focus them, to create a sharp picture? You know, the same way a curved glass lens focuses a beam of light to take a photograph.
Then we step out of spectrometers and into electron lenses. We're moving from sorting to actively manipulating particles to basically see the invisible.
Let's start with electrostatic lenses. These use changing voltages to bend a beam of electrons, kind of like the ones used in the backs of old, bulky tube televisions to paint the picture on the glass screen.
Yeah, the old cathode ray tubes.
Exactly. I was trying to wrap my head around how an electric field, which just accelerates things in a straight line, like our stuck gas pedal, can act as a curved lens. I came up with an analogy about running through a muddy field, but I'm struggling with the mechanics of why the electron doesn't just get pushed right back off course when it leaves the lens.
Let's break down the actual geometry of what the electric field is doing. Picture two metal tubes arranged end to end, with a small gap between them.
Okay, two tubes.
The first tube is at a low voltage. The second is at a high voltage. An electric field forms in that gap. Down the exact center axis, the field lines point straight ahead. But near the edges of the gap, the electric field lines bulge outward, bowing into the empty space. We call these fringing fields.
Okay, so the invisible lines of force are bulging out like a barrel.
Right. When an electron enters the gap near the edge, it hits that bulging field line.
Yeah.
Because the line is curved inward toward the center, the electron gets a sharp kick toward the central axis. It's
Oh.
being focused.
But here is where my analogy falls apart. As the electron crosses the middle of the gap and enters the second half, the field lines are bulging in the opposite direction. They are bowing outward. So shouldn't that second half give the electron an outward kick that perfectly cancels out the inward kick? Why doesn't it just leave the lens parallel to how it entered?
Well, the outward kick is there. But you have to remember what an electric field fundamentally does. It accelerates. As the electron crosses that gap from the low voltage to the high voltage, it is speeding up dramatically.
Oh.
By the time it reaches the second half of the lens, the part with the outward bulging lines that want to defocus it, it is moving much, much faster than when it entered.
Oh, wow. So because it's moving faster, it zips through that second outward pushing half in less time.
Exactly. The force is roughly the same, but the time spent experiencing that outward force is significantly shorter. The inward kick from the first half has more time to act than the outward kick from the second half.
That is so clever.
The net result is that the focusing force always wins. The electron gets permanently bent toward the center axis.
That makes total sense. Now, that same principle, using fields to create a net inward squeeze, is applied in magnetic lenses, which are the heart of the electron microscope. They use a cylindrically symmetric electromagnet to squeeze the electron beam. But why do we even need an electron microscope? What is it about glass lenses and visible light that forces us to use magnetic fields instead?
It really comes down to the physical limits of light itself. If you want to see something incredibly small, your measuring stick has to be smaller than the object.
Right.
Visible light is a wave, and its wavelength is about 5,000 angstroms. You simply cannot resolve two distinct objects if they are closer together than the wavelength of the light you're bouncing off them.
And for context, a single atom is roughly 1 or 2 angstroms wide. So using visible light to look at an atom is like trying to feel the microscopic grooves on a vinyl record while wearing thick winter mittens.
That's a perfect analogy.
The tool is just too clumsy for the detail.
Exactly. But an electron, thanks to quantum mechanics, also behaves like a wave. If you accelerate an electron to 50 kilovolts, its wavelength shrinks to about 0.05 angstroms.
Whoa. 0.05.
Mathematically speaking, an electron microscope should be sharp enough to easily resolve the exact position of every single atom in a DNA molecule. Biology would basically become structural engineering. We could just look at the atomic machinery of life.
But we can't do that. I mean, nobody has ever seen a high-resolution photograph of the atoms inside a living DNA chain. So what is the tragic flaw here? If the wavelength of the electron is small enough, why is the picture still blurry?
The flaw lies in the magnetic lenses themselves as a phenomenon called spherical aberration.
Spherical aberration.
Yeah. In an ideal, perfect lens, all the rays in a beam, whether they pass through the exact center or graze the white outer edges, would bend and cross at one perfect, incredibly sharp focal point.
But the magnetic lenses don't do that.
They cannot. Any electron that enters near the outer edge of a static symmetrical magnetic lens ends up focusing at a slightly different spot than an electron that enters near the center. Instead of a single crisp point, you get a smeared, overlapping blur.
Can't we just grind a better magnetic lens? Optical lenses made of glass have this same problem, but camera makers combine different shapes of glass concave and convex to cancel the blur out.
That is the truly agonizing part. It's actually a proven mathematical theorem that you cannot combine static electric and magnetic fields to fix this.
Wait, really? It's mathematically impossible?
It is a fundamental, irreducible limitation of static symmetric fields. Because of that inherent spherical aberration, the best resolution we can practically achieve is stuck at around 20 angstroms. It is tantalizingly close, but it's just blurry enough that individual atoms remain hidden.
Wow. It's like nature put up a frustratingly arbitrary roadblock right before the finish line. Well, let's zoom out from the incredibly small to the unfathomably large. An electron microscope only has to keep a beam focused across a vacuum tube for a few feet.
Right.
But what if you need to keep a beam of subatomic particles perfectly focused on a circular track for millions of miles?
Now we're entering the territory of high-energy particle accelerators, specifically synchrotrons. When physicists want to smash particles together at nearly the speed of light, they trap them in giant underground magnetic rings.
Like the Large Hadron Collider.
Exactly. The challenge isn't creating a single static image. It's keeping billions of particles perfectly aligned on an endless racetrack.
And you can't just use a simple, uniform magnetic field or locked steering wheel to do this, can you? Because out in the real world, engineering is never perfect.
Never.
If the magnetic field is even a 0.001% too strong in one random section of the ring, the particle turns a microscopic fraction of a degree too sharply. Over millions of laps, that tiny error snowballs. The particle starts to walk off its path, spiraling out radially or drifting vertically until it crashes into the metal wall of the vacuum tube.
Which means the magnetic field can't just be a passive steering wheel. It has to actively push stray particles back to the center plane every time they wander. You need radial focusing to keep them from hitting the inner or outer walls, and you need vertical focusing to keep them from drifting up into the ceiling or dropping into the floor.
Okay, let's tackle radial focusing first. If a particle drifts too far toward the outside wall, I'd assume you just design the magnet so the field is stronger on the outside edge. It hits the stronger field, gets bent harder, and is shoved back to the middle.
That works, but amazingly, you can actually maintain radial focusing even if the field gets slightly weaker toward the outside.
Really?
Yeah. Physicists measure the slope of this field strength using a number called the field index, or N. The math dictates that for a particle to stay radially stable, N simply has to be greater than -1. The field can weaken slightly, but it can't fall off a cliff.
Fair enough. But what about vertical focusing? If the particle starts drifting up toward the ceiling of the pipe, how do you push it back down? The magnetic lines usually run straight up and down to make the circle in the first place.
To create a vertical force, the magnetic field lines cannot be perfectly straight and vertical. They have to bulge.
Bulge, like the barrel shape again.
Exactly. They have to physically curve outward. If a particle wanders up, it hits that outward curving magnetic line, and the geometry of the field forces it back down toward the center.
Okay, so just curve the lines. What's the problem?
The problem is the laws of electromagnetism. In free space, you cannot independently control every aspect of a magnetic field. Think of the field lines like stretched rubber bands. If you force them to bulge outward to create that vertical focusing, the lines naturally spread farther apart from each other as you move away from the center.
And when field lines spread apart, that means the overall magnetic field is getting weaker.
That's the mathematical trap right there. By making the field curve to keep particles off the ceiling, you are mathematically forcing the field to become weaker toward the outer wall. To get vertical focusing, the field index N must be less than 0.
Wait a second. You just said that to keep particles from hitting the walls, the field index N had to be greater than -1?
Mm-hmm.
But to keep them from hitting the ceiling, it has to be less than 0. They are actively fighting each other.
You are trapped in an incredibly narrow window. To achieve both, N has to sit precariously between 0 and -1. The system is constantly on the verge of flying apart. Physicists call this weak focusing.
Weak focusing.
Yeah, it requires astronomically huge, expensive magnets just to keep the beam in a sloppy, wide path that barely stays inside the pipe.
Which sets the stage for what is undoubtedly the most brilliant, mind-bending engineering trick in this entire deep dive. Physicists looked at that impossible compromise and invented the alternating gradient principle.
It completely revolutionized our ability to explore the universe.
The tool they used is called a quadrupole lens. Instead of a normal magnet, it has 4 poles, 2 north, 2 south, arranged in a circle. In the exact center, the magnetic field is 0. But as you move away from the center, the field gets incredibly strong.
Right.
This shape creates a massive focusing force horizontally, shoving particles toward the middle. But the fatal flaw is that it simultaneously violently defocuses vertically. It squeezes the beam left and right, but rips it apart up and down.
And if you just rotate that exact same magnet 90 degrees, it does the exact opposite. It focuses powerfully vertically, but violently defocuses horizontally.
Now hold on. If I put a magnet that pushes inward horizontally right next to a magnet that pulls outward horizontally with the exact same strength, doesn't that just equal a net force of 0?
You would think so.
You squeeze the toothpaste, then you unsqueeze it. How does alternating them actually focus the beam?
The forces don't cancel out because you have to factor in where the particle is physically located when it hits each lens.
Well,
remember, in a quadrupole, the force is strongest at the edges and 0 in the dead center. Let's trace a particle drifting dangerously far to the right. It slams into the first lens, which focuses horizontally. Because the particle is far out at the edge, it gets hit with maximum force. It gets a massive shove to the left, back toward the center axis.
okay, so it's moving diagonally inward now.
It travels a few feet down the vacuum tube and reaches the second lens, the one that defocuses horizontally. But because of that first massive shove, the particle is now physically much closer to the center of the pipe.
Oh, and because it's closer to the center, the magnetic force of the second lens is much weaker. So the outward pull from the second lens is puny compared to the inward push from the first lens.
You got it. The focusing push always happens when the particle is far out and the field is strong. The defocusing pull always happens when the particle is near the center and the field is weak. The focusing force always wins out over the defocusing force.
That is so smart.
You just line them up, focus, defocus, focus, defocus, and the beam gets squeezed tighter and tighter in both directions.
To make this visible for everyone, there's a phenomenal mechanical analogy for this in the sources. Visualizing invisible magnetic fields is hard, but imagine a pendulum, just a solid rod with a weight on the end attached to a pivot.
Okay.
Normally, it hangs straight down to the floor. That is a stable system. If you try to balance it upside down, pointing straight up toward the ceiling, it immediately falls over. Gravity pulls it away from the center. Gravity is strongly defocusing it.
Any slight drift from perfectly vertical, and the whole thing crashes down.
But what if you take the pivot point of that pendulum and attach it to a motor that violently vibrates straight up and down? It alternates rapidly between accelerating downward and accelerating upward. When the pivot drops out from under it downward, it actually creates a momentary force that pulls the weight inward toward the vertical axis. It acts like a focusing force.
And when the motor violently shoves the pivot upward, it pushes the weight away from the vertical axis, defocusing it.
But just like our alternating magnets, the average effect of bouncing between focusing and defocusing results in a net focusing force. If you vibrate that pivot fast enough, the pendulum will stand perfectly stable, straight up in the air, completely defying gravity.
The upside-down pendulum is such a perfect way to visualize it. That dynamic balance of alternating extremes is the only reason modern synchrotrons, like the Large Hadron Collider, can keep tiny protons perfectly aligned while racing around a 17-mile track at nearly the speed of light.
Okay, we've covered electric fields acting like a stuck gas pedal. We've seen magnetic fields act like a locked steering wheel. What happens if you subject a particle to both at the exact same time?
We enter the realm of crossed fields. Imagine an electric field pointing straight down from the ceiling and a magnetic field pointing horizontally across the room. They are perfectly perpendicular to each other.
Let's track a single electron dropped into that room from a standstill. The electric field, the gas pedal, immediately pushes it downward and speeds it up.
As it accelerates downward, it starts crossing the magnetic field lines. Now, recall our momentum spectrometer. The radius of a magnetic turn depends entirely on momentum. The faster the electron goes, the larger its turning radius. The magnetic field struggles to bend it.
So it sweeps out in this wide, incredibly fast curve. But eventually that huge curve points the electron back upward, pushing it directly against the electric field.
Right, now it's moving uphill. It's fighting the electric field, so it decelerates rapidly. As it loses momentum, the magnetic field is finally able to grab it tightly, yanking it into a much sharper, tighter circle at the top of its arc.
It's acting like a roller coaster. Fast and wide at the very bottom, slow and tight at the very peak. So the electron just traces this repeating series of arches, loop, 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 bouncing along in a straight line perpendicular to both fields. It's a path called a cycloid.
While the particle is executing this frantic, looping cycloid dance, its overall average motion is a steady, constant, sideways crawl. Physicists call this the drift velocity. It is remarkably precise, equal simply to the strength of the electric field divided by the strength of the magnetic field.
And this cycloid dance isn't just an obscure chalkboard diagram. This specific crossed field motion is the exact mechanism operating inside a magnetron tube.
A device sitting in almost every kitchen on Earth. The looping motion of electrons through crossed electric and magnetic fields in that tube generates the exact frequency of microwave radiation needed to heat up your leftover pizza or pop your popcorn.
It's amazing.
It really is. It all comes back to a particle trapped in a magnetic loop.
Let's take a breath and look at the ground we've covered. We started with one single geometric truth. A uniform magnetic field makes a particle turn. From that locked steering wheel, we watched the physics scale up to sorting atoms by momentum, struggling to photograph the microscopic world, flawlessly balancing billions of protons in a multi-mile accelerator using alternating forces, and eventually crossing fields to cook our food.
It perfectly illustrates how mastering one foundational mechanism opens up entirely different worlds of application. But I want to circle back to something we discussed earlier, a detail that offers a rather provocative thought experiment.
Let's hear it.
We talked about the heartbreaking reality of electron microscopes. We are permanently handicapped by spherical aberration. We can't take a sharp photograph of a DNA molecule because the geometry of any static, symmetrical magnetic lens will inevitably blur the image. The physics of static fields strictly forbids a perfect focus.
We are forever stuck at that 20 angstrom blur limit.
But pay close attention to the conditions of that mathematical limitation. The theorem states it only applies to electric and magnetic fields which are static, meaning constant in time.
Wait, constant in time? You mean it only applies if the fields never change?
What if they weren't static? What if some brilliant engineer designed an electron microscope using rapidly changing dynamic fields? Think about the particle accelerators. We used rapidly alternating fields, the upside-down pendulum trick, to achieve a stability that was mathematically impossible with static fields.
Oh, wow.
Could a similar principle of high-frequency dynamic fields be the key to finally overcoming spherical aberration? Could embracing chaos and alternating fields be the loophole that eventually lets us see the hidden structure of the universe, atom by atom, perfectly sharp.
That is a staggering thought.
Mm.
Using the chaos of vibrating fields to bring the microscopic world into perfect, crystal-clear focus. It really makes you wonder what other boundaries we're currently calling impossible simply because we haven't figured out how to jiggle the pivot yet.
There is always a deeper layer of complexity waiting to be exploited. A slight shift in perspective changes the entire realm of possibility.
Well said. We want to thank you for joining us on this deep dive into the invisible, winding paths of charged particles. Until next time, keep your curiosity accelerating, and we'll see you on the next deep dive. If I told you that a pure, flawless piece of metal is actually incredibly soft.
Yeah, most people would think you were completely crazy.
Right, and that the only reason skyscrapers don't just, bend over in the wind is because their steel is absolutely riddled with microscopic flaws.
It sounds completely counterintuitive, but it's the absolute truth.
Yeah.
We tend to just accept the materials around us as a given.
Exactly, like a diamond is hard, glass shatters, metals are tough. But for today's deep dive, we are really popping the hood on solid matter itself.
Because we usually only experience the world at that macroscopic level. We feel the texture, we test the strength, but we're completely blind to the underlying geometric machinery making those properties possible.
And to reveal that machinery, we have an amazing stack of sources today for you. We are pulling directly from Chapter 30 of Volume 2 of the Legendary Physics Lectures, which is titled The Internal Geometry of Crystal.
A classic.
It really is. And to cap it off, we're also diving into this truly brilliant scientific paper from 1947 by Sir Lawrence Bragg and J.F. Nye.
Which is such a fascinating read.
So our mission today is to decode how the invisible microscopic arrangement of atoms dictates the everyday properties of literally everything you touch.
Right.
Like, why does a piece of tin actually cry or, tick when you bend it? And why on earth did serious 20th century scientists spend hours blowing microscopic soap bubbles just to figure out how steel works?
Setting the stage here is really crucial, I think, because when we use the word crystal, most people immediately picture like a glowing purple amethyst in a museum.
Or a diamond ring.
Exactly. But from a physics perspective, a crystal isn't just a pretty rock. It's really the foundational rule of solid matter.
Okay, so what exactly is happening at that foundational level?
Well, we're looking at what happens when atoms, which are usually moving erratically in a liquid or gas, lose their thermal energy, they get stuck together, and they basically seek the lowest possible energy state.
And when they do that, they lock into these rigid, repeating three-dimensional patterns, right?
Spot on. They form what we call a crystal lattice.
Whenever I try to visualize a repeating pattern like that, I immediately think of designing wallpaper.
Oh, that's a perfect analogy.
Yeah, because in the lecture sources, there's this fantastic illustration of a 2D crystal lattice. And it looks exactly like a wallpaper pattern. I mean, you don't draw the whole wall at once.
Right, you find the simplest repeating element.
Exactly. Which in physics is defined by two primitive vectors. Basically, just two arrows pointing from one atom to the nearest identical spots. And once you establish that basic stamp, nature just stamps it endlessly left, right, up, down.
That wallpaper analogy captures the fundamental geometry perfectly, just, extended into 3 dimensions. The atoms find that low energy arrangement, that basic primitive stamp, and they just repeat it infinitely.
To build a solid object.
Yes. But the actual mechanical process of how that happens in nature is, well, it's anything but a gentle, orderly stacking.
What do you mean?
If you imagine a crystal growing out of a hot liquid solution, it is an incredibly violent, chaotic process of trial and error. And it's all driven by thermal energy.
Because the atoms in that liquid state are still hot, meaning they're constantly vibrating and shooting around.
Frantically. Every single atom in that liquid is bouncing against the growing solid face of the crystal about 10 trillion times every single second.
Wait. I have to pause you right there. 10 trillion tests per second.
10 to the 13th power, yeah. Every second.
Per atom. If they are moving with that much violent energy, bouncing 10 trillion times a second, how does the crystal ever actually form? Shouldn't that same energy just, knock everything apart?
It's a very delicate thermodynamic balancing act. I mean, most of the time, the atom does just bounce off.
Yeah.
But remember, they are actively looking for the lowest energy state. So if an atom hits the surface at the exact right angle and drops into a spot where it perfectly aligns with that repeating wallpaper geometry...
It sheds some energy.
Exactly. It sheds a tiny bit of energy and falls into a sort of energetic well. Once it locks into that specific geometric slot, the thermal energy required to knock it back out is slightly higher than the energy it currently has.
Oh, wow. So it's basically trapped by its own efficiency.
Right. It becomes statistically more likely to stay than to leave. So by continually testing the surface 10 trillion times a second, the atoms gradually build up these massive, perfect geometric structures, one atom at a time.
That scale just completely defies human comprehension.
It really does.
And what blows my mind is how this invisible microscopic stamping process entirely dictates the visible macro shape of the thing you might be holding in your hand right now,
Because that internal geometry creates what we call cleavage planes.
which are the fault lines where the crystal can easily break or split.
Yeah.
Right.
Exactly. We see this directionality dictate physical properties all the time. The lectures use a great example with quartz.
Oh, the quartz example is amazing. Like if you go out and dig a natural quartz crystal out of the dirt, it usually looks kind of lopsided and messy.
Right, because of the environment.
Yeah, the visible faces are all different sizes because maybe there was a rock in the way while it was growing, or the liquid it grew from flowed unevenly.
But, and this is the fascinating part, if you take a protractor and measure the angles between those lopsided external faces,
They are always exactly 120 degrees. It's so wild.
always, the exterior environment can warp the overall size of the faces, but it simply cannot alter the underlying mathematical laws of the atomic stamp.
Because the internal hexagon of the atoms locks those angles in place.
Exactly. You see that extreme contrast in everyday minerals, too. Think about the difference between mica and asbestos.
Okay, so both are natural minerals containing silica, right?
Yes, but their internal atomic wallpaper is totally different. If you find mica in the ground, its atoms bind incredibly strongly in two directions, forming these tough, flat sheets.
Oh, right. You can peel mica into layers so thin they're transparent, but if you try to actually rip the sheet itself, it's remarkably tough.
And asbestos behaves in the exact opposite manner. It has strong atomic bonds in only one direction.
So what's the macro result of that?
A material that pulls apart easily in two directions, but in that third direction, it forms these tough, microscopic, one-dimensional fibers.
So the entire mechanical personality of the material, like how it crumbles or flakes in your hand, is just a macro manifestation of its microgeometry.
Firstly.
Okay, so if atoms are just blindly dropping into the most efficient, lowest energy slots, why do we only see a few specific shapes in nature? I mean, why isn't there an infinite variety of atomic wallpapers?
That comes down to the strict rules of spatial symmetry. In a flat, two-dimensional plane, mathematically, there are exactly 17 possible repeating patterns.
Only 17.
Yep. You can rotate them, you can reflect them like a mirror, you can offset them, but you absolutely max out at 17.
But crystals are three-dimensional structures.
True. And in 3 dimensions, the math allows for exactly 230 possible spatial symmetries.
Okay, 230 makes a bit more sense.
And crystallographers group these 230 symmetries into 7 main classes. They range from the least symmetric, which is the triclinic class, all the way up to the most highly symmetric class of all, which is the cubic crystal.
You know, I was reading this part of Chapter 30, and I immediately hit a mental roadblock.
Oh, why is that?
Well, nature clearly loves the number 5, right? We have starfish, we have 5-petaled flowers. So if atoms are just trying to pack together efficiently, why can't we have a 5-sided crystal?
Ah, the missing pentagons.
Yeah. Why is there no pentagon wallpaper in those 230 mathematical symmetries?
The absence of pentagons in repeating lattices is honestly one of the most fascinating proofs in geometry. It's known as the impossible five-fold symmetry.
Okay, walk me through it.
Let's try to build that 2D atomic wallpaper you mentioned earlier, but using a pentagon. A 5-fold symmetry means you should be able to rotate your pattern by 72 degrees, and it will match up perfectly with itself.
Which sounds completely reasonable on paper.
It does, until you actually try to place the atoms based on your primitive vector, which, remember, is the shortest allowed distance between two identical atoms in your pattern.
Okay, so let's say that mandatory minimum distance is exactly 1 nanometer.
Sure. If you place your first atom, and then rotate your angle by 72 degrees to place the next one to create that 5-fold pentagon pattern, the geometry breaks down.
Wait, where does the math actually fail? If I put 5 atoms in a ring, shouldn't they just lock together?
Well, a single ring of 5 atoms is fine. The problem is making it repeat infinitely to form a solid crystal.
Oh, I see.
If you keep rotating 72 degrees to place the next ring of atoms, the distance between the new atoms you just placed would be shorter than your original 1 nanometer minimum distance.
So they would literally overlap.
Exactly. They would crash into each other. It is mathematically impossible to fill a flat space completely with a repeating lattice of regular pentagons without leaving empty gaps or having the shapes overlap.
So you simply cannot tile a floor with regular pentagons.
The geometry outright forbids it. The only rotational symmetries that can actually fill a space infinitely without breaking their own minimum spacing rules are 1, 2, 3, 4, and 6-fold symmetries.
What about 8-sided, like an octagon?
Octagons fail for the exact same reason as pentagons. The atoms would crash into each other trying to form the repeating pattern.
Okay, so the math says we can only have certain symmetries. But what does this actually do for you, the listener? Like, if I'm holding a piece of material, why do I care if its internal atoms are packed in a cubic symmetry or an orthorhombic symmetry?
Because the internal symmetry governs how the material interacts with the outside universe. Physicists describe these interactions using what are called macroscopic tensors.
Macroscopic tensors, okay.
Take electric polarizability, for example, which is basically a measure of how the material responds when exposed to an electric field.
Let me try to translate that into a real-world example. Say you have a crystal that falls into that perfect cubic symmetry class. If I run an electric current through it, the electricity flows through the material with the exact same resistance no matter what angle or direction I apply the current from. Right.
That is spot on.
Yeah.
We call a material like that an isotropic dielectric.
Isotropic, meaning the same in all directions.
Right. Because the atomic spacing in a cubic crystal is perfectly symmetrical in all directions. Its polarization ellipsoid, which is the mathematical shape describing its electrical response, is a perfect sphere.
But if I use, say, an orthorhombic crystal, which resembles more of a stretched rectangular box instead of a perfect cube, the symmetry is broken.
But as a result, that orthorhombic crystal will conduct electricity or polarize differently depending on which specific angle you apply the field.
So the abstract internal math literally dictates the tangible real-world physics.
Exactly.
Okay, so if crystals are these mathematically perfect, rigid arrays of atoms, then physically breaking them or bending them should be nearly impossible.
You would think so.
Which leads to one of the biggest paradoxes in material science. When we think of metal like iron, steel, copper, we instinctively think of immense strength. I mean, we build bridges out of them.
We do, but metals actually have incredibly simple, highly symmetrical crystalline structures, like a body-centered cubic lattice.
So what's the paradox?
The paradox is that pure, perfect metal crystals are not strong at all. In fact, they are incredibly soft.
Wait, really?
Yeah, you can take a pure, single crystal of metal and permanently distort it with almost zero physical effort.
But if they are just perfect cubes stacked infinitely, shouldn't they be rock solid?
Well, you would assume that if you push on a perfect crystal like, applying a shear force to slide the top half over the bottom half, every single atom in that top plane would have to break its bond and slide at the exact same time.
Right.
If metals actually behave that way, they would be virtually unbreakable. The energy required to sever millions of atomic bonds simultaneously is staggering.
But it doesn't happen that way. Chapter 30 uses a fantastic analogy for this, and it totally changed how I view materials.
The rug analogy.
Yes. Trying to shear a perfect crystal is exactly like trying to move a massive, heavy area rug across a living room floor. If you grab the edge of a giant rug and try to drag the entire thing at once, the friction is too high. You can't budge it.
So you change your strategy.
Exactly. You make a little wrinkle at one end of the rug, and then you just push that single wrinkle across the floor to the other side. You're only ever lifting and moving a tiny few inches of the rug at a time. But by the time the wrinkle reaches the far edge, the entire rug has shifted forward.
That physical mechanism in a crystal is formally called a dislocation. A dislocation is simply a geometric flaw, a missing half plane of atoms inside the crystal lattice.
So it's basically an atomic wrinkle.
Right. When you apply stress to a piece of metal, the entire plane doesn't slide. The slippage happens one single row of atoms at a time as that empty space, that atomic wrinkle, zips through the lattice.
And because the metal only has to break and reform one row of bonds at a time, it takes almost no energy. This is why pure metals are soft. You can even hear this happening on a macro scale, which is so cool. If you take a thick piece of pure tin wire and bend it right next to your ear, you will hear a distinct, rushing, ticking sound known as the tin cry.
It's an amazing phenomenon.
You are literally listening to the acoustic shock waves of millions of crystal planes snapping into new positions as those dislocations tear through the metal.
Which introduces a monumental engineering problem. I mean, if pure metal is soft because these dislocations can slide through them so easily, how do we build skyscrapers? How do we get hard steel out of soft iron?
We have to trap the wrinkles.
Yes, we purposefully introduce impurities. When forging steel, you melt pure, soft iron and dissolve a small amount of carbon into the mix.
And because the carbon atoms are a different size,
They don't fit cleanly into the iron's cubic wallpaper pattern. They create microscopic distortions in the geometry.
so now when you bend that steel and a dislocation tries to slide through the crystal like a wrinkle in a rug, it slams into that distorted carbon grain and gets pinned.
The wrinkle cannot move forward. And if the microscopic wrinkles can't move, the macro piece of steel simply cannot bend.
That is incredible. The flaws are literally the source of the strength.
They are?
And it's not just about adding chemical impurities either. You can physically create the same effect yourself, which is something called work hardening.
Right, like the copper bracelet trick mentioned in the sources.
Yeah. If you take a perfectly pure, dead soft copper bracelet, you can bend it around your wrist with ease. But as you bend it, you're physically tearing the internal crystal structure and generating thousands of brand new dislocations.
You are creating new wrinkles.
Tens of thousands of them. And as you keep bending the copper back and forth, all those individual wrinkles start running into each other inside the lattice.
They angle up.
Exactly, creating this massive microscopic traffic jam. Suddenly, the dislocations can't move anymore because they are physically blocking each other's paths. The copper becomes rigid and hard.
You can't unbend it.
Right, and to make it soft again, you have to heat it up a process called annealing.
Which pumps enough thermal energy back into the atoms to let them vibrate, iron out all those tangled wrinkles, and reform into perfect soft crystals again.
You know, it's worth noting that while we view dislocations as flaws, they are actually essential for existence.
Oh, absolutely. Without specific types of dislocations, crystals would struggle to grow at all.
I have to admit, I was slightly confused by this part of Chapter 30. We talked earlier about atoms bouncing 10 trillion times a second, looking for a low-energy corner to lock into. But once a crystal finishes a completely flat layer of atoms, it runs out of corners. The surface is just a smooth plane. How does the crystal keep growing if there's nowhere secure for the next atom to grab onto?
That was actually a massive puzzle in physics for a long time. An atom landing on a perfectly flat crystal face might form one weak bond with the layer below it, which just isn't enough to withstand the thermal vibrations.
So it just gets knocked right back off.
Right. The solution nature found is a specialized flaw called a screw dislocation. Imagine a parking garage ramp or like a spiral staircase.
So instead of building flat, complete layers one by one, the crystal face gets slightly offset. It creates a continuous geometric step that spirals upwards around a central axis.
Exactly. A screw dislocation creates a permanent corner. It's a step that never disappears, no matter how many trillions of atoms you add to it. The crystal literally relies on this built-in flaw to grow, spinning around and around itself.
The lecture sources actually include a fantastic photograph of a microscopic paraffin crystal, and it looks exactly like an infinite spiral staircase. The geometric flaw acts as the engine for its own growth.
It's beautiful.
But here's the thing. Everything we are talking about right now, the 10 trillion thermal bounces, the tangling atomic wrinkles, the spiral staircases, is happening at a scale we simply cannot see with the naked eye.
Right.
And back in 1947, when Sir Lawrence Bragg and J.F. Nye were writing their paper on metal crystals, they didn't have the ultra-powerful scanning tunneling microscopes we use today to image individual atoms. So how did they prove any of this?
They engineered one of the most elegant analog scientific models ever devised. They built a visible, two-dimensional metallic crystal on a tabletop using thousands of tiny floating soap bubbles.
Okay, but why soap bubbles? You can't just use dish soap to understand steel.
It turns out you can because of the unique nature of the metallic bond. In a pure metal, atoms don't just form rigid individual links with their specific neighbors. They release their outer valence electrons into a universal shared pool.
So it acts like a fluid sea of negative glue holding all the positive atomic ions together in a dense pack.
Exactly. And tiny soap bubbles floating on the surface of a liquid mimic that exact same physical dynamic.
The bubbles are drawn together by general capillary attraction.
Right. That capillary force perfectly simulates the universal pool of free electrons in a real metal. The floating bubbles pull themselves into the tightest, lowest energy geometric arrangement, visually demonstrating exactly what atoms do.
I pushed hard on the mechanics of this when reading the 1947 paper, because if you just blow bubbles in a sink, you get a chaotic mess of big bubbles and small bubbles.
True.
But a pure crystal requires completely uniform atoms. The apparatus they built to achieve this is just wild. How did they get 100,000 bubbles that were all exactly 0.14 millimeters wide?
They constructed a rotating dish filled with a specialized soap and glycerin solution. They spun the fluid at a very precise speed past a microscopic glass jet that was pumping out air at a constant pressure.
So the speed of the fluid sheared the air off at the exact same interval.
Yes, acting like a high-speed atomic printing press that mass-produced over 1,000 perfectly uniform microscopic bubbles every single second.
And the results they achieved with this bubble raft were staggering. I mean, the invisible physics of solid metal was suddenly playing out in macro scale right in front of them.
When they gently compressed the edges of the bubble raft with springs, it behaved exactly like a metal yielding to stress.
They physically saw the rug wrinkle.
They did. They saw a line where there was an extra row of bubbles, and they watched that single dislocation zip across the raft at lightning speed, shifting the entire crystal structure by exactly one bubble width.
And they didn't stop at just proving the dislocation theory. They simulated the carbon impurities in steel by intentionally dropping in a bubble that was slightly too big.
The photographs in the paper show how that single wrong-sized bubble warps the neat, perfect rows of the lattice in every direction.
Which lets you visually see why a dislocation would slam into that warped area and get pinned.
Exactly. But the most dramatic experiment they ran was simulating that annealing process we discussed earlier with the copper bracelet.
Oh, right. They took a perfect raft of uniform bubbles and violently stirred it with a glass rake,
Utterly destroying the symmetry. The raft broke into dozens of tiny, highly strained individual grains with chaotic dislocations completely fragmenting the lattice.
But then they stopped stirring. They just stepped back and watched.
Over the next 25 minutes, with zero outside interference, the raft began to heal itself.
Because the bubbles, just like atoms, naturally sought out that lowest energy state.
Right. The highly energetic boundaries between the broken grains shifted. The larger grains naturally consumed the smaller broken fragments until the entire chaotic mess reorganized back into massive, perfect crystal structures.
It was a macro-scale demonstration of metal annealing, playing out quietly on the surface of a soapy liquid.
Taking the most complex, invisible forces binding our universe together and modeling them perfectly with a bowl of soapy water is just incredible science.
It really is. So what have we uncovered on this deep dive? We've journeyed from atoms frantically vibrating 10 trillion times a second to find a low-energy geometric slot, to the rigid mathematical laws that completely forbid five-sided atomic wallpaper. And most surprisingly, we found that perfect crystals are inherently weak. It is the flaws, the missing rows, the atomic wrinkles, the microscopic traffic jams that allow us to forge steel, build skyscrapers, and really shape the material world.
And if we pull all this microscopic geometry back up to the macroscopic world one last time, there is a final, slightly provocative thought I'd love to leave you with.
Oh, let's hear it.
The next time you take a cheap metal paperclip and mindlessly bend it back and forth until it snaps.
Which we've all done.
Right. You aren't just breaking a simple piece of wire. You are literally tangling millions of microscopic atomic dislocations. You are creating a structural traffic jam so incredibly severe that the crystal lattice finally gives up and literally tears itself apart.
Wow. So you literally hold the power to manipulate the internal geometry of crystals right in your hands.
You really do.
A macro-scale consequence of a micro-scale law. That is definitely something to ponder the next time you hold a piece of metal. Thanks for joining us on this deep dive. If I told you that the twisting force you use every single day, like the torque you apply to turn a doorknob or, steer your car, was actually a mathematical illusion.
Well, a mathematical glitch, really.
Yeah, a glitch caused by the fact that we just happen to live in 3 dimensions. I mean, would you believe me?
It sounds totally absurd when you frame it like that. I mean, it goes against literally everything we're taught in basic high school physics.
It really does.
But when you actually look at the geometry of the universe, that glitch is very, very real.
And that mind-bending reality is exactly what we're getting into today. Welcome to the deep dive. Today, we are taking a fascinating journey through a notoriously brilliant piece of source material. We're looking at Volume 2, Chapter 31 of the legendary Feynman Lectures on Physics.
Classic.
Absolute classic. And our mission today is to demystify this mathematical concept that sounds, honestly, incredibly intimidating, but is secretly running the entire physical world behind the scenes. We are talking about tensors.
And it's a really vital mission, too, because, well, physicists have this habit of taking the simplest possible example of a phenomenon, pretending the world is perfectly symmetrical, and just calling that physics.
Yeah, the classic textbook scenario.
Exactly. They like to assume the universe is isotropic, meaning it behaves the exact same way no matter what direction you look.
Right, like you push a block, it slides straight ahead in a frictionless vacuum. You shine a light, it goes straight through the glass. Cause and effect just line up perfectly.
It's comforting. I mean, the math is easy. But when you step out of the classroom and look at a real piece of strained metal or a complex crystal, that simple picture just shatters. We live in an anisotropic world.
It's a messy physical landscape.
It is. And in that landscape, direction changes absolutely everything. So to understand that reality, simple math just doesn't cut it.
Yeah. Simple vectors, you know, those basic arrows with a direction and a length that we all use to describe forces, they just aren't enough. And what I really love about the Feynman lectures is how they take this incredibly abstract, multidimensional math and ground it in tangible things you can actually visualize.
It's a masterclass in translation, really. Because to understand why we even need tensors, we first have to understand the limits of those simple physics equations. So let's start with something physical, like a crystal, and this concept called polarizability.
Okay, well, let's unpack this. Polarizability. We're talking about applying an electric field to a substance, right?
Precisely. In a lot of common materials, if you apply an electric field to them, the atoms react. The positive charges pull a little bit in one direction, and the negative charges pull a little bit in the opposite direction.
They stretch out.
All right, they stretch out and produce what we call a dipole moment.
They get polarized.
Yeah.
And in that simplified, perfectly symmetrical world we talked about, if I push the electric field straight up, the charges stretch straight up. The input matches the output perfectly.
But in the real world, in anisotropic crystals like calcite, which is that beautiful clear crystal famous for creating double images when you look through it.
Oh, right, yeah.
In calcite, the polarization is not in the same direction as the electric field you applied.
I was actually trying to picture this when I was going through the notes, and I came up with an analogy. It's sort of like pushing a broken shopping cart.
Ooh, I like that.
Yeah, so you push straight forward, and that push is your electric field. But because the wheels are janky and they resist motion in certain directions, the cart actually veers off at a weird angle, and that veering path is your polarization.
That is a brilliant way to visualize it, because if you imagine you're holding a piece of that calcite crystal, its internal atomic structure is like a rigid scaffolding.
Okay.
If you apply an electric field at, say, a 45-degree angle to that internal scaffolding, the charges inside might be able to move very easily up and down the main struts, but they feel very stiff if the field tries to push them sideways.
So they basically just take the path of least resistance.
Right. The resulting movement, the polarization, is a compromise between the direction you pushed and the directions the crystal will actually allow those charges to move. So it doesn't point at 45 degrees anymore, it veers off.
And this is exactly where the math has to evolve. Because the simple vector arrow representing my push and the vector arrow representing the crystal's reaction, they are no longer parallel.
And what's fascinating here is just how complex that relationship gets. To accurately describe this mathematically, you can't just say force equals response times a single number.
Because it's splitting off in different directions.
Exactly. Because an electric field pushing purely in the x direction will cause polarization, not just in the x direction, but it might also cause a little bit of drift in the a direction and the z direction.
So a single push in one direction echoes across all three spatial dimensions.
It does. And a push in the y direction does the exact same thing across x, y, and z. And so does a push in the z direction. So if you want to predict exactly how this crystal will behave, you need a mathematical system that tracks every possible cross-interaction. The x effect on x, the x effect on y, the x effect on z, that's 3 numbers right there.
And then the y effect on x, y, and z, that's 3 more. And the z effect on x, y, and z, another 3.
So you end up with 9 proportionality constants. It's a 3x3 grid of numbers. And that grid, connecting one 3D vector to another 3D vector, that is what we call a tensor of the second rank.
Okay, so we have this 3x3 grid of 9 numbers dictating how our crystal behaves. But I mean, 9 numbers is a lot to hold in your head. How do we actually visualize what this grid is doing to the crystal without getting completely lost in a sea of algebra?
Well, the geometry gives us a really elegant solution here. Instead of staring at a spreadsheet of numbers, we can plot the energy required to polarize the crystal.
Okay, how does that work?
If you imagine testing every single direction and asking, what electric field gives me the exact same specific amount of energy, those points map out a 3D shape.
Oh, like connecting the dots.
Exactly like connecting the dots.
Yeah.
And for any tensor of the second rank dealing with polarizability, that shape always forms an ellipsoid.
So like a squashed sphere.
Right. Imagine a perfect sphere that's been squashed or stretched, like an American football or a really smooth river stone. The shape and orientation of that energy ellipsoid perfectly captures the behavior of those 9 numbers.
Wow, that makes it so much easier to picture. But wait, if I have a grid of 9 messy numbers all interacting with each other, is there a way to simplify it? Like, what if I just rotate how I'm looking at the crystal?
You've just hit on one of the most powerful properties of tensors. The polarization tensor is symmetric.
Wait, what does symmetric actually mean in the context of a 3 by 3 grid?
It means the crosstalk is perfectly balanced. The amount that a push in the x direction affects the a direction is exactly equal to the amount of push in the a direction affects the x direction.
Oh, I see.
Because of this perfect mirror image behavior across the grid, you can always tilt your coordinate axis. Imagine taking your standard x, y, and z graph and physically rotating it in space until the axes line up perfectly with the longest diameter, the shortest diameter, and the middle diameter of that squashed sphere.
The principal axis.
Exactly. And when you align your coordinates to those specific axes of the ellipsoid, something magical happens to the math. All that messy crosstalk just disappears.
Really?
Yes, the complex 9-number tensor simplifies down to just 3 core numbers running diagonally down your 3 by 3 grid. All the other 6 numbers, the cross interactions, they become absolute zero.
So just by changing our perspective, rotating the axis, we turned a total nightmare equation into a clean set of 3 numbers.
We did.
But what if the crystal isn't messy? What if I have a perfectly symmetrical cubic crystal, like a tiny grain of table salt? Does its internal geometry dictate a simpler shape?
Yes, the physical symmetry of the material strictly limits the shape of the tensor. For a perfectly cubic crystal, all 3 principal diameters of the ellipsoid have to be equal.
Which would make it just a perfect sphere.
Right. And mathematically, a perfectly spherical tensor is represented by something called the Kronecker delta. It's a very neat matrix where you just have a 1, a 1, and a 1 on the diagonal and zeros everywhere else.
So it behaves the same in all directions.
Exactly. It means the polarizability is identical in all directions. It behaves just like those simplified isotropic textbook examples.
Okay, so the tensor molds perfectly to the physical reality of the object, but everything we've talked about so far is microscopic, right? It's atoms shifting inside crystals. But tensors govern the macro world too, don't they? Like things we can hold and throw.
They absolutely do. And this is where we move from the tensor of polarizability to the tensor of inertia. It's about objects spinning in space. And there is a massive, very common misunderstanding in physics that the source material points out brilliantly here.
Yes, and here's where it gets really interesting for me, because this kind of broke my brain a little bit. If you throw a football or like spin a block of wood, you'd intuitively think the direction it's spinning, its angular velocity, is the exact same direction as its angular momentum. You spin it forward, the momentum goes forward.
Right, it's what almost everyone learns. Because in high school, we usually only study perfectly symmetrical objects, like a top or a bicycle wheel spinning neatly on an exact axis. But if you tried to spin an irregularly shaped rock, or a weirdly cut block of wood.
Its angular momentum vector does not point in the same direction as its spin.
Exactly. Because the mass is distributed unevenly, some parts of the rock are heavier and further out from the center. They pull the momentum off axis. It's your broken shopping cart all over again, but with spinning mass instead of electric charge.
So the input, the spin, doesn't align with the output, the momentum, which means we need another 3x3 grid, another tensor of the second rank to connect them. But this brings us to that massive revelation we teased at the very beginning of the deep dive, the torque.
Yeah, this raises an important question. What actually is torque? In school, we learned that torque, the twisting force, is a vector. You multiply a force by a distance, and you get an arrow pointing perpendicular to both of them. It's called a cross product.
Right, the classic right-hand rule. You point your fingers one way, bend them another, and your thumb points toward the torque vector.
Well, the Feynman lectures argue that the right-hand rule is a lie, or at least a very lucky coincidence. Torque is not a true vector. Cross products are actually anti-symmetric tensors of the second rank in disguise.
Whoa, okay, back up. Anti-symmetric tensor. What does that even mean? And how on earth does a 3x3 grid masquerade as a simple 3D vector arrow?
Okay, let's break it down. We know a second-rank tensor in 3 dimensions is a 3x3 grid, 9 numbers. In an antisymmetric tensor, the numbers on the main diagonal, x, x, y, y, z, they must all be exactly 0.
Why 0?
Because logically, a force purely in the x direction cannot create a twisting motion around the x-axis. You can't twist an axis by pushing perfectly parallel to it. So those 3 diagonal numbers vanish. We're left with 6 numbers.
Okay, 9 minus 3 is 6. I'm with you.
Now, for the antisymmetric part, the remaining 6 numbers form pairs across the diagonal. the XY effect and the YX effect. In a symmetric tensor, those two would be identical. But in an antisymmetric tensor, they are mirror opposites. One is positive, one is negative. If XY is 5, YX is -5.
Ah, so if you know one, you automatically know the other. They aren't independent pieces of information.
Precisely. So out of those 6 remaining numbers, only 3 of them are actually independent. The other 3 are just their negative twins.
So an antisymmetric tensor in 3D space only contains 3 independent numbers.
Right. And how many numbers do you need to describe a standard vector arrow in 3-dimensional space?
3, just the x, y, and z coordinates.
Exactly. Because they both rely on exactly 3 independent numbers, mathematicians long ago realized they could just map the tensor's 3 numbers onto a 3D arrow. They essentially shoved the complex grid into a simple vector shape. It acts like a vector purely by accident, because there happen to be exactly 3 spatial dimensions in our universe.
That is wild. It's like a mathematical cheat code. But wait, what if we lived in a universe with 4 spatial dimensions?
If we lived in 4 spatial dimensions, your grid would be 4 by 4. 16 numbers, 4 zeros on the diagonal leaving 12. 12 numbers paired off as positive-negative twins leaves you with 6 independent terms.
And you definitely cannot represent 6 independent terms with a single 4-dimensional arrow.
You cannot. The fake vector trick completely falls apart in 4 dimensions. You would have no choice but to use the full tensor to calculate a twist. So torque at its foundational level is a tensor. We've just been living in a dimension that lets us cheat.
My mind is completely blown. Okay, so tensors explain how forces and momentum get redirected when things spin or push through crystals. But what about objects just sitting completely still? What about the forces happening inside solid matter?
Now we are transitioning from the mechanics of motion to the mechanics of stress. Imagine a solid object under intense pressure. There are internal forces between neighboring parts of the material, keeping it from just collapsing or shearing apart. To describe this, we use the stress tensor.
And this is where the source material brings in the jello. Feynman literally says, consider a block of jello. It's such a great visual.
It really is. If you're picturing that block of jello in your head right now, imagine taking a very sharp, invisible knife and slicing straight through it. Even though it's still sitting there perfectly intact, the material on the left side of that invisible cut is exerting force on the material on the right side, and vice versa.
You'd intuitively think the jello is just pushing straight across the cut, right? Like when you squeeze a water balloon, the water just pushes straight out against the rubber.
That's hydrostatic pressure, or normal force. But solids, and even wobbly things like jello, they don't just push straight back. They also have shear forces. This is force that slides parallel to the cut. Imagine pressing your hands together and then trying to slide one up and one down. That friction is a shear force.
So if I'm looking at the face of my imaginary slice inside the jello, the force isn't just pushing into it. It could be dragging up or dragging sideways across the face of the slice.
Exactly. And if you make your invisible cut at a slightly different angle, the combination of those pushing and dragging forces changes completely. So how do we track all of this chaos? We use the tensor grid. We take an imaginary slice perfectly perpendicular to the x-axis. On that slice, we measure the force pushing straight in, the force dragging up, and the force dragging sideways. That gives us 3 numbers.
Then you make a slice perpendicular to the y-axis and you get 3 more numbers. Slice perpendicular to the z-axis, get the final 3. 9 numbers total. The 3 by 3 tensor is back.
It's back. And here's the magic of the stress tensor. With just those 9 core numbers, which represent the stress purely along our clean x, y, and z axis, you can mathematically calculate the forces balancing on a slice cut at any arbitrary, weird angle through that jello.
So what does this actually mean for you listening? Like, let's say you're a civil engineer building a bridge. Is this how you know if a steel beam is going to snap under the weight of rush hour traffic?
Absolutely. A massive steel beam isn't just dealing with gravity pulling straight down. It's bending, it's twisting, experiencing huge shear forces inside the metal lattice. The stress tensor allows an engineer to say, given the external load on this beam, what is the exact internal stress on an imaginary microscopic plane sliced at, say, a 37-degree angle deep inside the steel?
Because if the internal shear force dragging across that specific microscopic plane exceeds the molecular strength of the steel,
the metal shears, the beam snaps, the bridge fails. The math becomes very, very real very quickly. And there's a fascinating detail about why this specific stress tensor has to be completely symmetric, just like our crystal polarization.
oh, right, the spinning microcube. Explain that, because I loved the logic of that in the source.
Yeah, imagine zooming way in on a tiny microscopic cube of material inside that steel beam. If the shear force dragging up on the right face of that tiny cube wasn't perfectly balanced and matched by the shear force dragging across the top face.
The forces wouldn't cancel out. The tiny cube would experience a torque. It would literally start spinning infinitely fast inside the solid steel beam.
Which obviously doesn't happen. The bridge sits still. The solid remains solid. So the forces must perfectly balance out across the faces, which mathematically dictates that the tensor grid must be symmetric. The xy shear must equal the yx shear.
The physical reality of a stationary object enforces the mathematical symmetry. Incredible. Now, we've been talking entirely about second-rank tensors so far. A 3x3 grid, 9 components, connecting one vector to another. But we don't stop there, do we? What happens when you need to connect one entire 3x3 grid to another 3x3 grid?
You're talking about the relationship between stress and strain. We just mapped out the stress, the internal forces. But what about the strain? How much does the material physically deform, stretch, or compress under those forces?
Right. To relate a second-rank tensor for stress to another second-rank tensor for strain across 3 dimensions, you need a tensor of the 4th rank.
Which means taking our base of 3 dimensions and raising it to the power of 4. 3 times 3 times 3 times 3.
That's 81 numbers. An 81-component grid just to figure out how a piece of metal bends. That sounds like an unmanageable nightmare.
It sounds completely impossible. But thankfully, the universe is governed by those physical symmetries we just discussed. Because the microcubes don't spin out of control, and because the fundamental elastic energy of a material doesn't magically change depending on how you look at it, dozens of those 81 numbers are forced to mirror each other or cancel out to 0.
So the symmetry basically rescues us from the algebra.
Exactly. Even for the most complex asymmetric crystals in existence, you only need a maximum of 21 distinct independent numbers to perfectly describe their elasticity.
I mean, 21 is still a lot, but way better than 81. And what if the material is isotropic, like a perfectly uniform block of glass?
The symmetry collapses it dramatically. It drops down to just 2 constants, 2 numbers to describe the entire elastic behavior of the material in 3D space.
It is stunning how symmetry simplifies the universe. But we can't end this deep dive without touching on the ultimate mind-bender. We've been trapped in standard 3-dimensional space this whole time. What happens when we leave it?
We enter the realm of Einstein. The culmination of this math is the 4 tensor of electromagnetic momentum in relativity, or, more broadly, the stress energy tensor.
So we take our x, y, and z spatial grid and we expand it. We add time, the hat dimension. So instead of a 3x3 grid, we suddenly have a 4x4 grid. 16 components representing 4-dimensional space-time.
And if we connect this to the bigger picture, the way the physical meanings of these components shift when you swap a dimension of space for a dimension of time is truly beautiful. Let's walk through it. We already know that the pure space components, forces interacting across x, y, and z, represent the flow of momentum. That's the mechanical stress in the steel beam we just talked about. Momentum moving across space.
Okay, so space to space is mechanical stress. I'm with you.
But what happens when you look at the time component of momentum flow? Imagine momentum, but instead of moving along an x-axis, it's just moving forward in time. It's not shifting in space. It's just sitting there as seconds tick by. What is that?
Well, if it's not moving, but it exists in an area over time, that is simply the density of the momentum in that spot.
Exactly. The flow of momentum through time is momentum density. Now let's do the exact same thing for energy. The spatial flow of energy, energy physically moving through XYZ space, is called the Poynting vector. It's essentially light, or electromagnetic radiation traveling from point A to point B.
So light is energy flowing through space. And following that exact same logic, what is the time component of energy flow? Energy sitting in one place, not moving spatially as time ticks forward.
It's just energy density.
Yeah.
Mass energy sitting in a location. So when you build this 4x4 tensor grid, it perfectly unites the concepts of physical pressure, the flow of light, momentum density, and energy density into one single unified mathematical object.
That is staggering. Let me make sure I'm wrapping my head around this. By using a 4D tensor, Einstein basically proved that a beam of light traveling across the room, the physical pressure inside a bridge's steel beam, and the sheer mass energy density of an object sitting still are not separate phenomena. They are just different faces of the exact same underlying 4-dimensional geometry.
That is exactly the profound truth at the bottom of all this math. Tensors are not just abstract torture devices designed to make physics students cry.
Even though they definitely do.
They do. but they are the essential grammar of the universe. They are the ultimate translation tool that allows us to understand how directional forces truly interact.
Whether it's the electric field veering through a calcite crystal, the sheer forces keeping a block of jello from collapsing, or energy and light flowing through the four dimensions of space-time, they describe the messy, complex, anisotropic reality we actually live in, rather than the simplified textbook version we were all promised.
And realizing that those simple vectors we rely on every day are often just an approximation, or even a literal mathematical accident, is a major step in thinking like a true physicist.
Yeah.
You really can't unsee the complexity once you know it's there.
You really can't. And that brings us right back to where we started today. We naturally love our clean, straight lines. We like our frictionless vacuums and perfectly symmetric physics problems where cause directly points to effect. But the universe doesn't owe us simplicity. It's complex, it's direction-dependent, and it is deeply, fundamentally interconnected.
And honestly, the fact that we can decipher that complexity using these mathematical grids is what makes physics so beautiful.
Absolutely. It makes the real world so much more interesting than the textbook version. So I'll leave you listening with this final thought to mull over. We just walked through how the standard 3D cross product of torque, the twisting force you experience every single day when you open a door, is essentially a mathematical cheat code. It's just a lower dimensional shadow hiding the true reality of a second-rank tensor. It really makes you wonder, what other simple, everyday, common sense rules that we take for granted in our daily lives are actually just lower dimensional shadows of a much grander, multidimensional truth? Something to think about. Thanks for taking this deep dive with us. Imagine holding a solid, heavy brick of lithium metal right up to your face and just being able to look right through it like a pane of perfectly clear glass.
Right, which sounds completely like science fiction. Or, I don't know, a glitch in a video game.
Yeah, exactly. But according to the physics we're exploring today, it's actually an absolute mathematical reality.
It really is. And it goes against all our daily intuition, right? When you think of it, a solid block of metal, you expect absolute opacity.
Right, light hits the surface and the light just stops.
Exactly. We rely heavily on that boundary between light and matter just to navigate the physical world. But stepping into the world of high-level electrodynamics shows us that this solid wall isn't, a fundamental absolute.
Because at specific frequencies, a dense chunk of metal just ceases to interact with an electromagnetic wave entirely.
Yeah, it becomes completely transparent. The wave passes through as if the metal simply wasn't even there.
Which is wild. So our sources for this deep dive are drawn from Chapter 32 of Volume II of the legendary Feynman Lectures on Physics.
An absolute classic text.
Oh, absolutely. We're tackling the original lecture text, the underlying mathematical arguments, and 3 specific figures that illustrate wave amplitudes and the erratic motion of electrons.
And our mission today is really to trace that journey, right? Starting from a basic understanding of refraction, how light bends and slows down.
Right.
All the way to the incredibly complex reality of what happens when light pushes its way through crowded atoms, liquid mixtures like sugar water, and eventually into solid, highly conductive metals.
Okay, so to get to transparent metals, we first have to establish the baseline of what an electromagnetic wave actually does when it hits a single atom.
Yeah, we have to start small. So in foundational physics models, we treat the atom as a harmonic oscillator.
Meaning like a mass on a spring.
Exactly. You picture an electron bound to its nucleus, acting just like a mass attached to a microscopic spring. When an incoming beam of light, which is an oscillating electric and magnetic field, hits that atom, the electric field physically displaces the electron cloud.
It pushes and pulls it in rhythm with the wave.
Right, exactly.
Okay, let's unpack this. Because the electron has a negative charge and the nucleus has a positive charge, displacing that electron creates an oscillating dipole. And from basic electromagnetism, we know that any accelerating charge radiates. So this tiny shaking electron starts broadcasting its very own secondary electromagnetic wave in all directions.
And the generation of that secondary wave is the crucial mechanism for literally everything that follows.
Because it interferes with the incoming light.
Yes. The new wave radiated by the oscillating electron interferes with the original incoming light wave. And because the electron has mass, there's a slight delay in how it responds to the push and pull.
So it's lagging behind a bit.
Exactly. Its radiated wave is slightly out of phase with the original light. So when you add those two waves together mathematically, the resulting combined wave has a shifted phase.
Which, on a macro level, manifests as a slower wave speed.
You got it. This is the physical origin of the index of refraction. It's the fundamental reason why light appears to slow down or bend when it enters a medium like glass or water.
But, I mean, in a highly rarefied gas, calculating that phase shift is a fairly straightforward exercise. It's like observing a massive ballroom where people are dancing entirely alone, widely spaced out from one another.
Right, lots of empty space.
Yeah, if you want to know how the music affects one dancer, you just look at the music in that specific dancer. But a dense solid is not a ballroom. It is a crowded, shoulder-to-shoulder rock concert.
That's a great way to put it.
So doesn't an atom get affected by all the radiating atoms bumping elbows with it?
Oh, absolutely. The density completely upends that simple calculation. You
Yeah.
have to introduce the concept of the local field.
The local field.
Yeah. The actual electric field operating on any single atom in a dense material is drastically stronger than the external light shining in. To visualize the math Feynman uses, you imagine removing one single atom from the dense crystal lattice.
Okay, so you just pluck one out.
Right, which leaves a microscopic spherical hole surrounded by all the other polarized atoms. And the electric dipoles of all those surrounding atoms point toward this cavity, creating a concentrated surface charge in the inside of the hole.
Wow, so they're all sort of aiming their fields right at that empty spot.
Exactly. And this amplifies the electric field significantly. Specifically, the sources note it's increased by a factor of p over 3 epsilon naught, where p is the total polarization.
Which means the actual force shaking our target atom is a combination of the external light and the amplified echo of millions of its neighbors.
Right, which makes the math incredibly messy. The lecture points out that early physicists actually really struggled to model this atomic polarization.
Yeah, because keeping track of millions of tiny springs is a nightmare.
Exactly. So rather than deal with the headache of calculating millions of microscopic bound charges shaking each other, they essentially invented an accounting trick.
Oh, you mean the D and H fields?
Yes. They created these secondary mathematical constructs, the D and H fields, to sweep the messy reality of bound charges right under the rug.
Just to focus on the macroscopic free charges they could easily measure?
Exactly. But Feynman makes a very deliberate point of rejecting that historical workaround. He insists on keeping the mathematics strictly grounded in fundamental quantities.
Meaning the raw electric and magnetic fields and the total charge density.
Right, which includes every single bound electron acting like a spring. Because relying on the D and H fields might make the macroscopic equations look cleaner on a blackboard, but it obscures the actual physical mechanism happening at the atomic level.
So by forcing the model to acknowledge the true local field, we get a highly accurate picture, but we also have to confront the reality of atomic friction.
Yes, because you can't have millions of springs packed tightly into a room without them dragging on each other.
Right. As these neighboring atoms interact so strongly, the natural frequencies of their atomic springs become heavily damped. The motion of the electron encounters actual resistance.
And this friction fundamentally alters how we calculate the index of refraction, which leads us to the Closey-Smisati equation.
I love that equation. It elegantly links the macroscopic index of refraction to the microscopic polarizability of the atoms, right? While fully accounting for the dense packing.
It does, and the mathematical consequence of introducing that damping or friction into the oscillator equation is that the index of refraction becomes a complex number.
Wait, imaginary numbers in physics usually mean something very real is happening to you, the observer. What does the imaginary part actually do to the light?
It's a great question. Because normally, instead of a simple real value that just tells you how much the light slows down, the index splits.
Yeah.
You have a real part and an imaginary part.
And the real part handles the standard behavior we expect, right?
Right.
The speed of the wave and how much it physically refracts.
Exactly. But the imaginary part represents the attenuation. It is the mathematical manifestation of the wave's energy being drained away by the friction of those atomic oscillators.
Basically converted into heat.
Right. The sources actually provide a striking visual for this in figure 32-1.
Oh yeah, the graph of the electric field.
Exactly. It graphs the strength of the electric field at a specific instant as a wave travels deeper into a dense material. Because of that imaginary component representing absorption, the amplitude of the wave doesn't just drop linearly.
It decays exponentially, right?
Yes, an exponential decay. With every microscopic step into the material, a percentage of the remaining wave energy is bled off by atomic friction. The wave is literally fading into nothingness the further it attempts to penetrate.
The mathematical derivation there is incredibly elegant, but, I mean, physics ultimately requires experimental proof. We need to verify that this complex index theory actually translates to the real world.
Oh, absolutely.
And the source material turns to a surprisingly mundane method for this proof, mixing a batch of sugar water.
Yeah, specifically taking empirical data from the Handbook of Chemistry and Physics for sucrose, dissolved in pure water at varying concentrations.
Which is amazing. You're proving high-level quantum-adjacent physics with a basic kitchen ingredient.
Exactly. And if the Clausius-Masati theory holds true, the total index of refraction for the mixture should be the exact mathematical sum of the individual polarizabilities of the water molecules and the sugar molecules.
But wait, this is where I have to question the setup a bit. When you dissolve sugar into water, you aren't just placing objects next to each other in a vacuum.
Right, there's a lot going on.
You're physically breaking intermolecular bonds in the sugar crystal. You have water molecules forming tight hydration shells around the sucrose molecules. It completely alters their local electromagnetic environment.
It's chemical chaos.
Yeah.
Yeah.
So given all that chemical chaos, how can the mathematical polarizability of the sugar remain perfectly identical to when it was a dry crystal?
What's fascinating here is that chemical interaction is exactly what makes the experimental results so compelling.
Really? How so?
Because the optical response, the actual shaking of the electrons that dictates the index of refraction, is predominantly driven by the tightly bound core electrons within the individual atoms of the sucrose molecule.
Ah, so not the ones on the outside.
Right. The dissolving process primarily affects the outermost valence electrons and the intermolecular bonds. The interatomic springs are largely isolated from the surrounding liquid environment.
That makes so much sense.
So when the lecture walks through the arithmetic, taking the index of the mixture, calculating the total polarizability, and then subtracting the known polarizability of pure water, the remaining value for the sucrose molecule is stunningly consistent.
Which proves the model is remarkably robust. By subtracting the water, the math shows the polarizability of the sugar molecule stays nearly identical, whether it's locked in a dry crystal or floating in a dilute solution.
Exactly. It's an intrinsic property.
Okay, so we've effectively mastered the behavior of bound electrons, the dielectrics like glass, water, and sugar. But to get to our transparent lithium, we have to take the training wheels off the model, right? We have to cut the atomic springs entirely.
Yes. Removing that restoring force transforms the material from an insulator into a conductor. We get metals.
Because the electrons are no longer bound to a specific nucleus.
Right. They become conduction electrons, free to move throughout the entire crystal lattice. So we adapt our equation by simply setting the restoring force to 0. But crucially, we maintain the term for resistance.
Because they still bump into things, which is illustrated in figure 32-2, right, too? It maps the trajectory of a free electron in a metal.
Yes, and it isn't a smooth, frictionless glide.
Not at all. The path is a jagged, erratic sequence of violent collisions. The electron accelerates freely in the electric field for a brief moment, but then it scatters off the vibrating atoms of the crystal lattice.
And those collisions create a massive amount of drag, acting as a powerful dissipative force on any wave trying to push the electrons.
But wait, if the electrons are completely free to move around without being tethered to a nucleus, wouldn't light just push them out of the way and shine straight through a piece of copper?
You'd think so. But the reality at lower frequencies is the exact opposite. Because the electrons have no restoring force tying them down, they are hyper-responsive.
Oh, so they move too fast.
Exactly. When a low-frequency electromagnetic wave hits the surface of a metal, the massive sea of free electrons surges instantaneously to counteract the incoming electric field.
They literally shift their positions.
Yes, and by shifting, they generate their own opposing electric field that perfectly and immediately cancels out the incoming wave.
They swarm the wave.
They swarm it. And this instantaneous cancellation introduces the phenomenon known as skin depth.
Because the wave is neutralized so quickly, it only manages to penetrate the very outermost skin of the metal.
Precisely. The sources use the specific example of a 10,000 megacycle microwave, which is the frequency of a standard 3-centimeter radar system striking a block of copper.
And the calculated skin depth is microscopic, right?
Yeah.
Like 6.7 times 10 to the -5 centimeters.
Exactly. And figure 32-3 graphs this rapid decay, showing the amplitude of the transverse wave dying out virtually the instant it makes contact with the metal surface.
Wow.
All of the energy is either absorbed by the erratic resistive collisions of the electrons, or it's reflected back out into space within a fraction of a millimeter.
Which dictates massive real-world engineering applications. I mean, when constructing a microwave cavity or a waveguide to channel these frequencies, building the entire structure out of solid silver or gold would be a staggering waste of money.
A huge waste.
Yeah.
Because the electromagnetic field literally never penetrates deeper than that microscopic skin depth.
So engineers simply build the bulk of the waveguide out of a cheaper, structurally sound material like brass or aluminum and plate the inside with a layer of gold just a few thousandths of an inch thick.
Right. All the complex electrical action, the reflection, the current flow, it all happens entirely within that tiny surface veneer.
We basically design our communication hardware around the limitations of the wave.
We do.
But here's where it gets really interesting. If a low-frequency wave gets blocked at the surface because the free electrons can instantly surge and cancel it out, what happens if we drastically crank up the frequency?
Like into the extreme ultraviolet or X-ray spectrum.
Yeah.
Well, this is where we cross the threshold into transparent metals.
Finally.
The physics fundamentally shifts because of inertia. Every electron, despite being unfathomably tiny, still possesses mass.
Right.
So as you push the frequency of the wave higher and higher into the petahertz range, the electric field is reversing direction millions of billions of times every single second.
And the electron simply has too much physical mass to reverse its momentum that quickly. The wave is oscillating so fast that the electron essentially stays still. It's akin to a bouncer guarding the door at a club. If a slow, low-energy wave wanders up to the entrance, the bouncer has more than enough time to step in front and stop it.
Right, that is the low frequency hitting the skin depth.
But if a super high-frequency wave comes sprinting at the door at Mach 10, the bouncer's physical mass prevents them from reacting. They can't even twitch a muscle before the wave has completely bypassed them and entered the club.
That's a perfect analogy. At these extreme frequencies, because the electrons barely move, the collisions and the resulting friction drop to zero. The dissipation term in our equation completely vanishes.
So the complex index of refraction loses its imaginary part.
Yes, and becomes a purely real number again. But crucially, because of the specific phase relationship between the fast waves and the tiny, lagging motion of the electrons, the calculated index of refraction becomes less than 1.
Wait, less than 1. An index of refraction less than 1 implies that the phase velocity of the wave inside the metal is actually faster than the speed of light in a vacuum. That usually sets off alarm bells in physics.
It absolutely does, but it doesn't actually violate relativity.
Oh, okay. Why not?
Because the phase velocity, the speed at which the crests of the wave appear to move, can exceed the speed of light. But the group velocity, which carries the actual energy and information of the wave, remains strictly below the speed of light.
Ah, okay. So no breaking the laws of the universe today.
Not today.
Mm-hmm.
But the critical takeaway here is that we reach a tipping point known as the plasma frequency. This is a specific mathematical threshold determined entirely by the density of the free electrons in the material.
So below the plasma frequency, the bouncers can react. The electrons swarm the wave, the index is complex, the metal acts like a metal, and it is completely opaque.
Exactly.
But the moment you push the wave's frequency above that specific plasma frequency, the electrons freeze. The dissipation vanishes. The wave passes through untouched, and the solid metal becomes completely transparent.
Yes, and the sources provide a table demonstrating how perfectly the theory aligns with experimental observation for alkaline metals.
Right, like lithium.
Yes. Lithium, due to its specific free electron density, has a plasma frequency that corresponds to a wavelength of 1,500 angstroms. Sodium sits at 2,100 angstroms.
So if you shine ultraviolet light at wavelengths shorter than those thresholds, the theory dictates the light will pass right through.
And laboratory experiments confirm it without fail.
So if you had optical receptors tuned to the extreme ultraviolet, a solid block of lithium would look identical to a block of clear glass. You could just read a book through it.
You really could.
And the implications of this equation extend far beyond laboratory metals, right? This precise mathematical relationship governs how electromagnetic waves travel through any cloud of free electrons.
Exactly. Which brings us to the Earth's ionosphere.
The upper atmosphere of our planet. It's basically a plasma, a massive swirling gas, heavily populated with free electrons stripped from atoms by solar radiation.
And the exact same local field calculations, the same resistance formulas, and the identical plasma frequency threshold that governed a brick of copper apply perfectly to the ionosphere.
This is the physics that makes global communication possible. I mean, AM radio signals are relatively long, low-frequency waves. They sit comfortably below the plasma frequency of the ionosphere.
Right. So when an AM radio wave travels up into the sky, the free electrons in the atmosphere have plenty of time to react.
They swarm the wave exactly like the surface of a metal and reflect it right back down to Earth.
Yep. This is why you can pick up an AM station from hundreds of miles away. The signal is literally bouncing off the sky.
But conversely, to communicate with a GPS satellite or the International Space Station, utilizing AM radio would be completely ineffective.
Totally useless. The signal would never leave the atmosphere.
Space communication relies on microwaves and other high-frequency bands that sit above the plasma frequency of the ionosphere.
Exactly. To those high-frequency waves, the ionosphere is completely transparent, just like the solid lithium was to the ultraviolet light.
The waves punch straight through the planetary bouncer and out into the vacuum of space. The universality here is just astounding.
It really is.
We initiated this deep dive by picturing microscopic hypothetical springs inside individual atoms. We validated the complex math governing those springs by analyzing a simple glass of sugar water. And by following the physical logic of removing those springs, we arrived at an equation that effortlessly explains both how solid metals turn transparent and how our satellites phone home through a shield of planetary plasma.
It really highlights the profound power of building physical models from fundamental truths.
Yeah.
By refusing to cheat with macroscopic variables, acknowledging the messy reality of dense local fields, and faithfully following the mathematics of friction and inertia, the theory elegantly bridges the microscopic behavior of a single electron with the macroscopic behavior of planetary atmospheres.
The exact same physical rules dictating the refraction of light in your morning cup of tea are dictating the propagation of light across the cosmos.
It's beautifully connected.
We now understand that every dense material possesses a specific plasma frequency, a hard threshold determining the exact moment it suddenly becomes transparent to an electromagnetic wave, and we know this threshold is governed by the density of the free electrons.
Right.
So as material science continues to rapidly advance our ability to manipulate matter at the atomic level, if we learn to precisely engineer the density of free electrons in new synthetic metamaterials, could we eventually design a macroscopic solid metal whose plasma frequency sits squarely at the bottom of the visible light spectrum?
That is the ultimate question.
Could we one day build a solid metal wall that is completely fundamentally invisible to the naked human eye? If you know exactly how fast to run, you might just slick right past the bouncers of the physical world.
So if you take standard, highly concentrated red ink,
Right.
and you let it dry into this thick film on a piece of glass, and then you shine a white light on it.
Just, regular white light.
Right, exactly. The reflection bouncing back to your eyes, it actually isn't red. It bounces back as this shining metallic golden green color.
Which is so counterintuitive.
It really is.
Right.
And today, we are going to use the raw hidden math of the universe to explain why the best light absorbers in the world are actually perfect mirrors.
Yeah, it's a wild concept.
Welcome to another deep dive. Today we're taking a journey into this really intense, brilliant piece of source material. We're looking at Volume 2, Chapter 33 of the legendary Feynman Lectures on Physics.
Oh, yeah. Reflection from surfaces. It's a classic.
It is. And our mission today isn't just to, accept the basic high school geometry of mirrors, like where light comes in at an angle and leaves the same angle.
Right. The stuff everyone just memorizes for a test.
Yeah. Exactly. We are going to uncover the physical tug-of-war happening at the atomic level, and we're going to use nothing but Maxwell's equations of electromagnetism to do it. Okay, let's unpack this, because to even begin understanding reflection, we first have to completely redefine what a surface actually is in physics.
Yeah, because we tend to think of reflection as this permanent property of an object. A mirror is reflective. A piece of wood is not.
But the source material immediately strips that idea away.
It does. It says reflection is not a property of the material itself, not like density or index of refraction. Reflection is strictly a boundary property.
Meaning it only happens under specific conditions at the edge.
Right. It only happens if the change between two materials, like, say, the transition from empty air into solid glass, is incredibly sudden. The text is actually very specific here. That change has to happen within the distance of a single wavelength of light.
Wow, okay. So how small is that?
Well, if we're talking about visible light, that is roughly 5,000 angstroms.
So we are talking about a transition that happens over just a few thousand atoms.
Exactly. It has to be that abrupt.
I like to think of it, and tell me if this analogy works.
Yeah.
Imagine you are driving a car and you hit a sudden steep speed bump.
Okay. Yeah.
That sharp, abrupt boundary makes your car violently bounce. And that physical bounce is essentially the equivalent of a reflection.
That's a great way to visualize it.
But if you take the exact same amount of asphalt that made up that speed bump and you stretch it out over like a 2-mile-long ramp, you don't even feel it.
Right, your car just glides seamlessly over it.
Exactly. There is no bounce. So if the properties of the air gradually blend into the properties of the glass over a distance of several wavelengths, there is almost no reflection at all. The light just passes right through.
And that stretched out speed bump principle, that is the exact mechanism behind anti-reflective coated lenses.
Wait, really? The coating on my glasses?
Yeah. When manufacturers want to stop glare on your glasses, they don't change the glass itself. They add these thin layers of extraneous material to the outside.
Oh, to soften the boundary.
Precisely. These layers create a transition zone that smooths out that abrupt boundary, which effectively tricks the light into gliding over the speed bump, reducing the reflected wave to almost zero for certain frequencies.
That is fascinating. But, I mean, the Feynman lectures don't stop at just describing the speed bump. The goal is to understand the actual physics of hitting it.
Right, the underlying mechanics.
Yeah, and to do that, we move away from clever, intuitive arguments. Like, if you are studying heat flow across a wall, you can intuitively argue that the heat flowing into the wall must equal the heat flowing out.
Makes logical sense, yeah.
But when dealing with the rapid, microscopic oscillation of electric and magnetic fields, human intuition completely fails. We have to rely on the differential forms of Maxwell's equations.
We have to look for what physicists call boundary conditions. And this is a really powerful shift in perspective, because Maxwell's equations aren't just abstract letters on a chalkboard.
They describe reality.
Yeah, they describe a physical, inescapable tug of war. The text uses this great visual, figure 33-5, to explain this. It looks at the tiny, squashed transition region between two materials. When an electric field hits the atoms in the glass, it physically yanks on the electrons.
And that yanking is called polarization, right?
Exactly. So in that microscopic sliver of space at the boundary, the electrons are being violently pulled in a new direction.
And because that transition is so sudden, our microscopic speed bump, the rate at which those electrons are yanked changes instantly.
Right, it's immediate.
So if you graph the mathematical derivative of that polarization, you get this towering, massive spike right at the boundary. I mean, the mathematical derivative is just a way of measuring the violence of that yank.
And here is the kicker. In a differential equation, everything must remain balanced. You cannot have a massive spike on one side of the equal sign without something matching it on the other side.
It's just a fundamental rule of math.
Yes. So if the electrons are being violently yanked, generating a massive spike in the material's polarization, Maxwell's equations demand that the electric field itself must experience an identical opposite spike.
The change in the electric field must perfectly counteract the yank of the electrons.
Exactly. It means the electric and magnetic fields on the left side of the boundary are physically locked to the fields on the right side of the boundary.
It cannot operate independently.
Right. The physical tug of war between the atoms and the fields chains them together, and that physical chain is what creates the light beams we actually see.
Let's put the listener in the middle of this. If you were to shrink down to the size of a photon and stand right on that atomic boundary, you would be caught in a three-way tug of war.
Yes, a very intense one.
The incoming wave is pulling you, the reflected wave is pulling you, and the transmitted wave is pulling you. And the text sets up a simple addition problem for this.
Okay.
The incident wave plus the reflected wave must exactly equal the transmitted wave.
What's fascinating here is the mathematical consequence of that simple addition. It's profound, because if you freeze time at the boundary, just set time to 0, you have two oscillating waves on one side, adding up to a third oscillating wave on the other.
Okay, I'm picturing it.
Now unfreeze time. The only physical way for those three waves to continue adding up perfectly every single microsecond into the future is if they are all oscillating at the exact same speed.
So they must share the identical frequency.
Exactly.
Wait, so we don't have to assume the colors stay the same. The math itself forces the frequency to be identical.
Yes. Otherwise, reality would basically break at the boundary. If the frequencies were even a tiny bit different, the waves would immediately slip out of sync.
The tug of war would become unbalanced.
Right. The boundary conditions would fail, and energy would either magically appear or disappear, which violates the laws of thermodynamics. The math forces the frequency to remain identical.
That is wild.
And this exact same physical logic applies to space. Waves don't just oscillate in time, they oscillate across space. We measure the spatial oscillation using wave numbers, which physicists call k-vectors.
Okay, k-vectors. So you can think of a wave number as how many ripples fit into a specific slice of space, right?
Yes, exactly. When the incoming wave hits the boundary at an angle, its ripples create a moving pattern of crests and troughs along the surface of the glass. And just like with the timing, the physical ripples of the reflected wave and the transmitted wave must perfectly align with that moving pattern on the surface.
They have to match the incoming wave's footprint perfectly.
Right. And because the speed of light changes when it enters the glass, the only physical way for the transmitted wave's ripples to perfectly match the footprint on the surface is if the wave changes its direction.
It'd have to bend.
Exactly. When you take the equations that force these ripples to align along the boundary, the math spits out Snell's law of refraction perfectly. And it proves, mathematically, that the angle of the incident wave must exactly match the angle of the reflected wave.
See, that just blows my mind. We didn't bring a protractor to this problem.
No, not at all.
We didn't inject the rules of high school geometry into the physics. We just took the raw equations of electromagnetism, observed that the physical tug-of-war must remain balanced at a sudden boundary, and the math naturally generated the geometry.
It's beautiful, isn't it?
It really is. The rule that light bounces off a mirror at the same angle it hits isn't some fundamental standalone law of the universe. It is merely a symptom of Maxwell's equations keeping the fields balanced. The geometry we see is just a shadow cast by the differential equations.
That's a poetic way to put it. So we have established how Maxwell's equations govern a transparent boundary like glass or water, where the atoms briefly tug on the wave but let it pass.
Right. But here's where it gets really interesting. What happens when the material actively tries to destroy the wave?
This raises an important question, because the most famous reflectors in the world are metals. Mirrors are just glass with a coating of silver or aluminum on the back.
And metals are completely opaque. You can't see through them at all.
Exactly. When we calculate the mathematical index of refraction for a transparent material like glass, we get a simple real number. But when we calculate the index of refraction for a metal, the math changes drastically.
How so?
The index of refraction gains a very large imaginary component.
Okay, let's ground what imaginary means here, because physics jargon can be really opaque. In the math of waves, an imaginary number is simply a tool used to describe a wave that is rapidly dying out.
Right, it represents a massive drain of energy.
So an imaginary index of refraction translates directly to one physical reality: extreme absorption. The material is rapidly devouring the light energy.
Which brings us to the paradox of reflection. If a metal is the ultimate absorber of light, devouring the energy almost instantly, we would logically expect a metal to be pitch black. It is eating all the light. So why are metals the shiniest, most perfectly reflective things we have?
I love this part. Okay, think of a nightclub bouncer standing at the door.
Okay, I'm with you.
The club is the piece of metal, the crowd is the incoming light wave, and the bouncer represents the absorption. Got it.
If the bouncer is just normally strict, some people get into the club and they are slowly absorbed into the crowd. That's like a dark tinted piece of glass.
Makes sense.
But if the bouncer is excessively, violently aggressive, so incredibly strong and fast that literally no one can take a single step past him, the crowd never even makes it inside the club to be absorbed. They hit the bouncer and immediately bounce right off the front door.
The physical reality in the metal matches that analogy perfectly. The electrons in a metal are incredibly free and mobile. When the incoming light hits the very first atomic layer of the metal, those free electrons respond so violently and rapidly that they instantly generate an opposing field.
Like the aggressive bouncer.
Exactly. This opposing field completely cancels out the forward-moving wave. The wave cannot penetrate even a fraction of a millimeter. And because it cannot penetrate, those strict boundary conditions we discussed earlier have nowhere else to put the energy.
They force 100% of the wave to reflect backward. Yes. The extreme violent absorption creates an impenetrable wall, resulting in a perfect mirror reflection.
Which brings us back to the dried red ink from the beginning of this deep dive. The text uses figure 33-8 to demonstrate this with concentrated dyes. Red ink looks red when it's in a bottle because it is a phenomenal absorber of green light.
Right. It lets the red frequencies pass through to your eye, but it aggressively devours the green frequencies.
So if you let a thick layer of that red ink dry on a glass plate and you shine a white light through it from behind, the light that successfully travels through the ink and reaches your eye is red.
But when you stand on the same side as the light source and look at the reflection bouncing off the front surface of the dried ink, you don't see red.
Because the ink is such a massive, violent absorber of green light, it acts exactly like the aggressive bouncer for that specific frequency.
Right. The green light hits that boundary, cannot penetrate because the absorption is too strong, and is violently rejected backward.
So the reflection off a puddle of dried red ink actually shines with a golden-green metallic gleam. You are manifesting a metal out of dye just by maximizing the absorption.
It's so cool. So we have established that a wave will bounce if the material in front of it is too hostile to absorb it. But what if the boundary isn't a wall? What if the boundary is a cliff edge?
What do you mean?
What happens when light is already inside a dense, transparent material like a block of glass and it tries to escape into nothingness into the air?
Okay. This is the phenomenon of total internal reflection. We see this when light tries to move from a high-index material like glass into a low-index material like air.
Yeah, according to the bending rules of Snell's law, as the light hits the inside boundary of the glass at steeper and steeper angles, the transmitted beam that escapes into the air bends closer and closer to the surface of the glass.
Right, and eventually you hit what is called the critical angle.
And at this exact trajectory, the math for the escaping wave breaks down completely. To calculate the angle of the escaping beam, the equation requires the sine of an angle to be greater than 1. In trigonometry, that is impossible for any real number.
So what does the math do? It generates an imaginary angle.
Exactly.
Wait, I have to stop you here and challenge this logic. You are telling me the math generates an imaginary angle, and reality just somehow translates that into a physical phenomenon.
I know, it sounds wrong.
Right. How does reality know how to interpret an imaginary number? If my calculator says error, my flashlight doesn't just stop existing. That sounds like a failure of our mathematical model, not a description of physics.
It is entirely counterintuitive, but reality interprets that mathematical error as an exponential decay. When the angle becomes imaginary, the physical wave cannot propagate as a beam of light anymore. But the energy doesn't just vanish cleanly at the glass border.
Because of the boundary conditions.
Exactly. The physical tug-of-war of the fields we talked about earlier prevents a clean break. Instead, a tiny, invisible tail of the wave bleeds out past the glass boundary and into the empty air.
So what does this all mean? Even though 100% of the visible light is bouncing off the inside of the glass block, there is still an invisible piece of the wave hanging out in the empty space outside the block.
Yes, it is an exponentially decaying field. Physicists often call it an evanescent wave. It is not a traveling beam of light. It's a localized, dying vibration of electromagnetic energy.
How far out does it go?
It extends into the empty air for only a microscopic distance, roughly the length of one single wavelength. For visible light, it fades to absolute zero within a fraction of a hair's breadth.
Okay, that brings up a massive question of causality for me. If it's an invisible, exponentially decaying tail of a wave that only sticks out a fraction of a millimeter into empty space, what is the practical consequence?
Oh, it does something miraculous. The text details this in a brilliant experiment using paraffin blocks in microwaves, which you can see in figures 3310 and 3311. They use microwaves because a microwave is just a light wave with a much longer wavelength, about 3 centimeters long.
Ah, okay, so because the wavelength is 3 centimeters long, this invisible tail bleeding out of the block isn't microscopic anymore.
Right, it stretches for several centimeters into thin air.
So what's the setup for the experiment?
The setup is this. You fire a microwave beam into a triangular prism of solid paraffin at a 45-degree angle. The beam hits the inside flat wall of the prism, experiences total internal reflection, and bounces completely away to the side.
Okay, so it's trapped.
Right. If you place a microwave detector in the empty air right outside that wall, it registers absolute zero transmitted energy. No beam is escaping. But that invisible exponential tail is currently sticking out 3 centimeters into the empty air outside the paraffin block.
Oh, man. Okay, so you take a second, completely separate piece of paraffin, and you slowly bring it close to the first block. You don't let them touch.
Right. There is still a physical gap of empty air between them.
You just move the second block into the space occupied by that invisible dying tail.
Yes. The decaying field is invisible, but it is still a physical electromagnetic force. When the second block enters that tail, the field interacts with the atoms in the new block. It begins yanking on the electrons in the second piece of paraffin.
And miraculously, that yanking generates a brand new propagating wave inside the second block.
Exactly. The totally reflected light literally jumps the empty gap and continues moving forward.
It bridges the void. Just by bringing a material close enough to feel the ghost of the wave, it pulls the wave back from the dead. It's basically macroscopic quantum tunneling.
It is a stunning validation of the boundary conditions. The wave was totally reflected, yet the energy found a way across the empty gap because the fields do not end cleanly at a surface. They fade. And if you introduce a new boundary before they fade to absolute zero, you resurrect the wave.
That is just incredible. You know, we started this deep dive thinking about simple mirrors, assuming reflection was just a clean, bouncing line of light. But by trusting the physical reality of Maxwell's equations, we've uncovered a microscopic landscape that is violently active.
Very active.
We've seen how the rapid yanking of electrons at a boundary physically chains waves together, forcing them to perfectly align their frequencies and their trajectories.
And we have unpacked the paradox of why extreme absorbers like metals and dried red ink shine with perfect reflections, acting like overly aggressive bouncers that refuse to let a wave penetrate even a millimeter.
Yeah. And we've seen how light can be completely trapped inside a dense block, yet still leak an invisible, dying tail of energy into the empty space beyond, just waiting for a new surface so it can jump across the void.
If we connect this to the bigger picture, the differential equations are always running. The math of a wave oscillating in 3 dimensions isn't just a textbook concept, it is an invariant physical truth.
It's the engine underneath it all.
It is the engine that governs everything. It dictates the glare on a puddle after a rainstorm, the metallic shine of a beetle shell, and the intricate optics of a camera lens. The fields are constantly balancing themselves every single microsecond across every boundary in the universe.
That leaves us with a final thought for you to take with you today. The next time you are holding a simple glass of water, tilt it slightly and look down into it.
Yeah, try it.
Look at the silver mirror-like reflection on the inside surface of the glass. That is total internal reflection happening right in your hand. The water and the glass are trapping the light. But now you know the hidden mechanism.
The invisible tail.
Exactly. Think about that invisible, exponential tail of light bleeding out completely through the glass and into the empty air around it. When you press your finger against the outside of the glass, right where that silver reflection is, your skin is actually entering that microscopic gap.
That's a wild thing to picture.
The atoms in your finger are interacting with that decaying, invisible light wave, giving it a physical place to jump to. You don't even realize it, but as you move through the world, you are constantly wading through invisible, dying fields of energy, fields that are just waiting for a gap to close.
You know, right now, as you are listening to this, you're just completely surrounded by magnets.
Oh, absolutely, everywhere.
And I don't just mean like the ceramic ones holding grocery lists to your fridge or, the heavy-duty motors in your car. I mean the actual chair you're sitting on.
Yeah.
Your phone. Like that random piece of aluminum foil sitting on your kitchen counter. Everything around you at a totally fundamental level is responding to magnetic fields.
Right, because we usually think of magnetism as this, this rare magical property that only belongs to a chunk of iron.
Exactly.
But the reality is far more universal. And honestly, it's a lot stranger. Every single piece of matter interacts with magnetism. We don't usually notice it because the forces are incredibly subtle.
Well, welcome to this custom deep dive. Today we are exploring a true classic in the world of physics. We're looking at Chapter 34 of Richard Feynman's legendary lectures, titled The Magnetism of Matter.
A fantastic chapter. It really is. And our mission for you today is to unpack what might be, well, one of the greatest fake-outs in the history of science.
Oh, the setup is just brilliant.
Yeah. We are going to look at how classical physics builds up this seemingly perfect explanation for why a simple magnet works, only to, like, mathematically destroy its own argument.
It completely dismantles it.
Right.
Right.
Forcing us to step into the bizarre, rule-breaking world of quantum mechanics to find the actual truth.
A source material really takes us on a journey. It builds up this beautiful, highly intuitive, classical model of orbiting electrons acting like tiny gyroscopes, right? It gets us nodding along, totally buying into it, and then it just pulls the rug entirely out from under us.
Yeah, it really does.
It is a masterclass in why human intuition is, frankly, completely inadequate for understanding the atomic world.
Okay, let's unpack this. Before we get to the great fake-out, we need to separate the heavy-duty magnetism of something like iron from the ordinary magnetism of everything else.
Right, crucial distinction. Because iron exhibits ferromagnetism, which is this intense, highly complicated quantum effect where atomic magnetic moments sort of lock together in these massive blocks.
Yeah, that's a completely different beast.
Exactly. We want to know what happens to ordinary matter when you expose it to a magnetic field.
So to visualize this, imagine a classic physics experiment. You take a powerful electromagnet with two poles facing each other. But instead of the poles being identical flat surfaces, you make one pole completely flat and you file the other pole down to a really sharp point.
Okay, so that sharp point is going to concentrate the magnetic field, right?
Right, exactly.
The field will be much stronger right next to the sharp tip than it is over by the flat surface, so you're creating a steep gradient.
Spot on. Now you suspend a small cylinder of metal called bismuth on a long string. You just let it hang right in the gap between those two poles.
Okay.
When you turn the power on, you'll see this very subtle reaction. The bismuth cylinder slowly pushes away from the sharply pointed high-field pole.
Wait, it repels.
It repelled.
That feels entirely counterintuitive, because when we play with everyday magnets, we usually observe attraction, right? Metals stick to magnet.
Right, but this repulsion is a universal property called diamagnetism.
Ah.
And the reason it happens is tied to Lenz's law. See, in materials like bismuth, the atoms don't actually have any permanent magnetic moment of their own.
Oh, really?
Yeah, all of their internal spinning and orbiting electrons, they perfectly balance each other out, leaving a net magnetism of zero.
But the moment you turn on that external magnetic field, you change the environment.
Exactly.
And a changing magnetic field induces little electric currents inside those atoms.
Right.
Because nature, it always tends to resist change. So those newly generated atomic currents flow in a direction that creates their own tiny magnetic fields to oppose the main field.
It's like the atom is trying to maintain the status quo. It senses this intrusive external field and just generates a microscopic shield to push back against it. Because it's pushing back, the entire piece of bismuth experiences a physical force pushing it away from the strongest part of the magnet.
And it's worth noting here, this diamagnetic pushing back effect doesn't care about the temperature of the room, does it?
No, not at all. It relies purely on the induced currents.
Right. But then the experiment takes a twist. We swap out the piece of bismuth for a small cylinder of aluminum. We hang the aluminum on the string, turn on the electromagnet, and it behaves completely differently.
Yeah, it's weakly attracted toward the pointed pole.
Which brings us to paramagnetism, because aluminum atoms are structured differently. Their internal electron orbits don't perfectly cancel out, which leaves each atom acting like a permanent microscopic compass needle.
Exactly.
When you turn on the big external magnetic field, those little atomic compasses try to physically line up with it. And that alignment creates a weak, attractive pull.
And this is where temperature plays a massive role.
Oh, right.
Like we said, in diamagnetism, heat doesn't matter. But for paramagnetism, the ambient heat of the material is basically the enemy of alignment.
I was trying to picture the mechanics of this, and it feels exactly like a mosh pit.
A mosh pit.
Yeah. Think of paramagnetism like a crowd of people, the atoms all trying to turn and face the main stage, which represents the magnetic field.
Okay, I'm with you.
If the crowd is standing completely still, which represents absolute zero temperature, it's effortless for everyone to face the stage. The alignment is perfect, and the magnetic attraction is incredibly strong.
Right.
But the reality is that everything has heat, which means thermal motion.
So the thermal motion is the music starting and everyone thrashing around.
Yes. The atoms are constantly colliding, violently bumping into one another, knocking themselves out of that perfect alignment with the magnetic field.
That's a great way to think about it. So the lower the temperature, the stronger the paramagnetic effect, simply because there's less chaotic bumping to disrupt the order.
Exactly.
And this helps clarify a major point. Diamagnetism that induced pushing back happens in absolutely every substance in the universe.
Everywhere.
Right. But in materials like aluminum, the paramagnetic lining up effect is vastly stronger, so it overpowers and masks the diamagnetic repulsion.
Okay, so we've established that atoms possess these tiny magnetic moments, but we shouldn't picture them just passively snapping into place like a compass needle on a table, right?
No, not at all. The classical model of the atom reveals a much more dynamic situation.
Let's visualize an electron moving in a circular orbit around an atomic nucleus. Because the electron has mass and is moving at a really high velocity, it has angular momentum, which is a property we denote as J.
Right, TJ.
At the same time, because it is a moving electric charge, it forms a tiny loop of current, which generates a magnetic moment denoted as mu.
And there is a rigid mathematical relationship tying those two properties together. The ratio of the magnetic moment to the angular momentum for this orbiting electron is a constant value.
Which is?
The electron's charge divided by twice its mass. Because the electron possesses that angular momentum, it physically resists being pushed around.
Right, because if you put a tiny magnet into a magnetic field, your first instinct is that it should immediately point straight north. But that angular momentum completely changes the behavior.
It does.
It acts like a spinning toy top. If you spin a top on a table, gravity is desperately trying to pull it flat, but the top doesn't just fall over.
Right, the spin gives it rigidity.
Exactly. Instead of falling, the axis of the top slowly traces a circle in the air.
What's fascinating here is how beautifully classical physics formalizes this atomic behavior. When you place that orbiting electron into a magnetic field, the field applies a torque, trying to twist the electron's orbit. But thanks to the angular momentum, the atom's magnetic moment precesses. It rotates around the axis of the magnetic field, just like the top, tracing a circle, instead of snapping to attention.
Physicists call this Larmor's theorem, right?
Yes.
It paints this incredibly elegant picture. If you have a complex system of electrons orbiting a nucleus, and you apply a weak magnetic field, the electrons don't freak out or change their orbital shapes.
No, they just keep doing their normal dance.
Yeah. The only difference is that the entire atomic system simply adds a uniform, slow rotation, the Larmor frequency, around the axis of the applied magnetic field.
You can almost see it in your mind's eye. Countless tiny orbiting gyroscopes, precessing in perfect harmony, generating the microscopic currents that explain diamagnetism and paramagnetism.
It's beautiful.
It feels like a complete, airtight explanation of how magnetism works in solid matter.
Which makes what happens next kind of hilarious.
It really is.
Because the source material spends pages getting us to visualize these gyroscopes, only to turn around and say, great job understanding all of that, now throw it in the trash.
Literally in the trash.
If you follow classical mechanics to its ultimate logical conclusion, it mathematically destroys the very magnetism we just observed in the bismuth and the aluminum. This is the great fake-out.
The author explicitly warns us that the classical arguments we just walked through are, quote, phony and not legal.
Not.
Right. If you apply the strict laws of classical statistical mechanics, magnetism should not exist.
Here's where it gets really interesting. How does a physics framework build such a perfect model and then prove itself wrong?
Well, let's reason this out.
Okay.
If I put a block of material inside a closed box, lock it down so the block itself can't spin, and let it reach a steady temperature, it achieves thermal equilibrium.
Under those conditions, classical statistical mechanics dictates a very strict rule. The probability of the atomic system being in any particular state of motion depends on only one thing, right?
Yes, it's total energy.
So if an atom is moving in a certain way, the likelihood of finding it in that exact state is dictated entirely by a combination of its kinetic energy, its motion, and its potential energy.
Okay, so the energy of the atoms acts like a master ledger, dictating how likely it is for the internal electrons to be swarming in specific patterns. Now, we flip the switch and turn on our massive magnetic field. And this exposes the fatal flaw in the classical model. A static magnetic field can never, ever do actual work on a moving electric charge.
Because the magnetic force operates perpendicularly to the direction the charge is moving.
Yes.
It's like driving a car and a giant hand pushes your car perfectly sideways from the passenger door.
That's a great image.
Thanks.
Hmm.
Like that push might steer you into a different lane, but it doesn't press the gas pedal or the brake. It changes your direction, but it cannot speed you up or slow you down.
Right.
Therefore, applying a magnetic field does absolutely nothing to the kinetic energy of the electrons in a classical system.
And if the external magnetic field cannot alter the kinetic energy of the electrons, then the total energy of the system remains identical.
Right.
And if the energy remains identical, then the statistical probabilities of all the different atomic motions must also remain identical.
Wow. So the probabilities of the electron motions are the exact same with the magnetic field turned on as they were when it was turned off. And an unmagnetized block of aluminum sitting on a table has an average net magnetic moment of exactly 0.
Carrying that logic to the end, if the motions don't change, the net magnetic moment must remain exactly 0.
No diamagnetism pushing back,
Nope.
no paramagnetism lining up, nothing.
Nothing at all. If classical physics were the whole truth, a magnet wouldn't pick up a paperclip.
That is wild. It's just a brilliant paradox. If you stop halfway through the classical argument, you trick yourself into thinking Larmor precession solves everything.
Right.
But carrying the classical laws to the bitter end proves the magnetic effects entirely cancel themselves out. It really makes you wonder why physicists bother teaching the classical gyroscopes in the first place.
Well, there are a few very pragmatic reasons. Physicists still study this because it has immense historical value. It shows us the stepping stones early scientists used to make sense of the world.
That's fair.
It also builds deep physical intuition for angular momentum. And practically speaking, classical rules do still apply in very specific non-equilibrium systems. For instance, a free-floating plasma in outer space, where the particles aren't trapped in a box bouncing off each other, that can exhibit classical diamagnetism.
Oh, interesting.
But to understand why the physical chair you were sitting on has magnetic properties, classical physics is a dead end. We have to introduce a completely new set of rules.
Enter the quantum rescue.
Yes.
To save magnetism, we have to abandon the smooth, continuous mechanics of the everyday world and rely on quantum mechanics. And the very first thing quantum mechanics does is completely redefine what angular momentum actually is.
Right, because classically, angular momentum is a smooth, continuous property. A spinning top can spin at any speed you like, and you can tilt its axis to point in literally any direction in a 360-degree sphere.
Yeah, that makes intuitive sense.
But in quantum mechanics, the angular momentum of an atomic system is strictly confined to a discrete, finite set of states.
So instead of a smooth volume knob that you can turn to any level, quantum angular momentum is like a heavy mechanical dial that only clicks into specific hard-coded notches.
That's the perfect way to put it. The system has a characteristic quantum number called its spin, denoted by the letter J.
Okay, J.
This spin J isn't just any number. It must be an integer, like 1 or 2, or a half integer, like 12 or 32.
Right.
And when you attempt to measure the component of that angular momentum along a specific axis, say the z-axis, which is the direction of your magnetic field, the measurement can't be just anything. It has to step down in precise integer increments.
Let's visualize a system with the spin of J. The absolute maximum angular momentum you can measure along the z-axis is J times a fundamental quantum constant.
Correct.
The next notch down on the dial isn't a tiny fraction lower. It is exactly 1 full unit less.
1 full unit.
And it keeps stepping down notch by notch until it hits negative J. So if an atom has a spin of 32, the only legally allowed values in the universe are positive 32, positive 12, negative 12, and negative 32.
Exactly. 4 distinct notches.
There is no intermediate state.
None. And this introduces a deeply strange geometric reality that breaks our spatial intuition. You might reasonably assume that in the very top notch, when the measurement along the z-axis hits the maximum value of J, the angular momentum vector is pointing 100% straight up the z-axis.
Yeah, that's what I would assume.
But the quantum math shows us that the total squared momentum of the system isn't simply J squared. It's actually J multiplied by the quantity of J plus 1.
Wait, meaning the total magnitude, the actual length of the angular momentum vector, is always slightly larger than the maximum possible measurement you can ever take along any single axis.
Exactly.
So the angular momentum can never point completely perfectly straight up?
Never.
It is always cocked at a slight angle, constantly bathed in an inescapable quantum uncertainty.
It is utterly alien compared to a spinning toy top. And this quantum weirdness doesn't just affect the geometry, it directly impacts the magnetic strength.
Right.
Earlier, we established the classical ratio of magnetic moment to angular momentum as the charge divided by twice the mass. But quantum systems require a correction multiplier called the Landé G factor.
Okay, the G factor. For an electron merely orbiting a nucleus, like a planet around the sun, the classical rules mostly hold up, and that G factor is exactly 1.
Right.
But an electron possesses an intrinsic fundamental property called spin. It doesn't just orbit. It acts as though it is rotating on its own axis.
And the G factor for the electron's intrinsic spin is 2.
2.
The magnetic moment generated by the electron's internal spin is twice as strong as classical physics says it should be.
It's as if the universe hard-coded a double-strength multiplier into the fabric of the electron. How do we even explain that?
This raises an important question. To find the explanation, physicists had to look beyond basic quantum mechanics. Paul Dirac formulated an equation that married quantum mechanics with Einstein's theory of special relativity.
Oh, wow.
Yeah. When you unify those two massive pillars of physics, the G factor of 2 naturally falls right out of the mathematics. It tells us that this double-strength magnetism is a fundamental consequence of how electrons exist in spacetime.
So we have angular momentum locked into specific quantum notches, and we have relativistic multipliers amplifying the magnetism.
Right.
But we still need to answer the core question. What physically happens to the atom's internal energy when we force it into a magnetic field?
Well, when you apply the magnetic field, it interacts with the atom's magnetic moment, trying to change its energy. But remember, the angular momentum can only exist in those specific locked notches.
Right, the dial.
Consequently, the magnetic energy can only take on specific, discrete values, too. The external magnetic field literally shatters the single original energy state of the atom into multiple distinct energy levels.
And the source notes that it splits into exactly 2J plus 1 levels.
Yes.
Taking a simple single electron with a spin of 12, 2 times 1/2 is 1 plus 1 is 2. The magnetic field forces that electron into exactly 2 energy states. In this magnetic environment, the electron spin can either be up, aligned with the external field, or down, opposing it. It creates 2 highly distinct energy lanes.
And the precise spacing between those energy lanes isn't random. It is determined by a fundamental unit called the Bohr magneton.
The Bohr magneton?
Right. It acts as the base currency of atomic magnetism. It is a constant calculated by combining the electron's charge, Planck's constant from quantum mechanics, and the electron's mass. Every single energy split we measure is built upon this specific quantum unit.
So what does this all mean?
Well,
When you pick up a strong magnet and sweep it over a piece of matter, you aren't just applying a mechanical pull. On an invisible microscopic scale, you are taking the internal energy states of trillions of atoms and fracturing them into distinct quantized lanes separated by the Bohr magneton.
exactly.
You are forcing the very fabric of the material into a multiple-choice reality where only highly specific quantized answers are permitted to exist.
If we connect this to the bigger picture, this splitting of energy levels isn't merely a theoretical, mathematical trick to fix the classical fake-out.
No.
It is the absolute foundation of how we measure the universe. When physicists observe how atoms absorb or emit light in the presence of a magnetic field, they are literally watching electrons jump between these very specific, magnetically created energy lanes.
That's incredible.
It is how we know what stars are made of, and it is the exact mechanism that powers MRI machines in hospitals. It is quantum mechanics made visible.
It requires a profound shift in how you view everyday objects. We started this deep dive just watching a tiny piece of bismuth gently push away from a magnet.
Right.
We tried to explain it with elegant classical gyroscopes, only to trace the math down a dead end where classical physics proves its own explanation is an illusion.
A complete illusion.
We had to completely abandon the smooth, continuous, common-sense world we experience every day and embrace the bizarre stepping stone spin-up and spin-down reality of the quantum realm to finally understand why magnets stick to things.
It is the ultimate triumph of quantum mechanics over our everyday intuition. The classical world is just an approximation. The quantum world is the actual reality running under the hood.
Before I let you go, there was one final, deeply weird detail in the source material regarding the neutron that I want you to explain to our listener.
Oh, yes.
Because it feels like the universe just throwing one last curveball at us.
It absolutely is. So the nucleus of an atom contains protons, which are positively charged, and neutrons. By its very name, the neutron tells us it is electrically neutral.
Right.
It has a net electrical charge of exactly 0. According to any classical logic, and frankly, even basic quantum logic, If you have no charge, you cannot have a moving electric current.
Makes sense?
And without a current, you cannot possibly generate a magnetic moment.
Yet the source provides us with the G factor for the neutron. It is approximately negative 1.91 multiplied by 2.
Despite having absolutely zero net electrical charge, the neutron possesses a robust magnetic moment. In fact, based on that negative sign, it behaves exactly like a rotating negative charge. It is a microscopic magnet in its own right, defying the basic requirement that you need an electric charge to create magnetism.
That is just incredible. It leaves you with this massive puzzle. I want you, the listener, to ponder that the next time you pick up your phone or tear a piece of aluminum foil. If the neutron has no overall electrical charge, what exactly is spinning around inside of it to create that magnetic moment?
It implies that the neutron isn't just a solid ball.
Right. There must be a whole hidden internal structure, a deeper layer of swirling, charged reality inside the particle just waiting to be uncovered.
It perfectly encapsulates the thrill of physics. Every time we solve a mystery, like replacing classical gyroscopes with quantum spin, we peel back a layer only to find another profound mystery waiting for us.
Beautifully said. Thank you for joining us on this deep dive into Feynman's lectures. And remember, the next time you see a magnet securely holding a piece of paper to the fridge, know that you aren't looking at classical physics at work. You're looking at a quantum miracle hiding in plain sight. So, right at the beginning of today's deep dive, there's a warning.
Oh, yeah. A pretty stark one, actually.
Yeah. It essentially tells you that when it comes to the tiny quantum world, understanding comes very slowly, if at all. It advises you not to expect your mind to ever feel completely comfortable with these rules because, well, the behavior of matter on a small scale is just utterly divorced from our everyday experience.
Complete.
But we are going to try anyway. Today we're going to unpack the shockingly weird ways that tiny atoms behave in magnetic fields, and then look at how scientists have actually harnessed that exact weirdness to do some mind-blowing things, like creating the coldest temperatures in the universe to mapping the invisible inner world of molecules.
It is quite a warning to start with. I mean, the quantum world is undeniably strange. It's this place where all of our classical physics assumptions just fail entirely. But, beneath that strangeness, there's a really profound elegance to it. We don't have to rely on classical intuition today. We just have to follow the evidence. And the actual rules governing this invisible realm become, honestly, incredibly clear.
Okay, let's unpack this. And let's start with the core concept driving all of this, which is quantized angular momentum. Or, as physicists usually call it, spin.
Right, spin.
To make this relatable to you, the listener, imagine you're holding a compass in your hand. In the classical macroscopic world that you and I live in, you can nudge that compass needle to point, say, slightly northeast or west, or really anywhere in a smooth, continuous 360-degree circle. It's fluid.
Exactly. You can pick any angle.
But a quantum compass, that thing is locked. It can only point straight up or straight down, or at very specific, discrete intervals in between. There is no smooth turning, no in-between states at all.
Yeah. And in the text we're looking at, this spin is represented by the letter J. And the strict rule is that J has to be an integer or a half integer.
Oh.
So for a system with a spin of, let's say, 3/2, the angular momentum along any axis can only take on the values of 3/2, 1/2, -1/2, and -3/2. That is it. 4 distinct states.
Wow, just those 4.
Just those 4. And when you place that atom into a magnetic field, the source shows how those structural states actually split into different energy levels. If you were to look at the first figure in the chapter, you'd see the energy splitting is directly proportional to the strength of the magnetic field.
Meaning the stronger the field.
The wider the gap between those discrete energy levels, exactly.
Which brings us to the moment where classical physics just completely slammed into a brick wall. The year is 1922, and we get the Stern-Gerlach experiment.
Oh, this is a classic.
It really is. It's one of those experiments that just sounds like mad science. So Otto Stern and Walther Gerlach wanted to measure the magnetic moment of individual silver atoms. So they set up an oven, they basically heat up silver until it vaporizes, and they shoot a beam of these silver atoms through a tiny slit into a vacuum. And then they pass this beam right between the poles of a very special magnet.
And the shape of that magnet is the crucial detail here. They didn't use a standard horseshoe magnet with, flat poles. They made one of the pole tips have a very sharp wedge-like edge, while the other was flat with a little groove in it.
Okay, why?
Well, this creates a strong magnetic field gradient. The field varies very rapidly depending on exactly where you are in the vertical space between the poles.
And that gradient is everything, right? Because if you just put a tiny magnet into a perfectly uniform magnetic field, the North Pole gets pulled one way and the South Pole gets pulled the exact opposite way with the exact same amount of force.
Right, they cancel out.
Yeah, the magnet might twist, but it won't actually travel anywhere.
Yeah.
But with that sharp edge, one pole of the atom is in a slightly stronger field than the other. That imbalance creates an actual physical force, pulling the atom either toward the sharp edge or pushing it away. So they shoot the beam through this weird magnet, and at the end of the line, they have a glass plate to catch the silver atoms. Based on classical physics, what were they assuming they'd find on that plate?
Well, classically, you have to assume those silver atoms are coming out of the oven just tumbling randomly. Their little internal magnets should be pointing in every conceivable direction.
Makes sense.
So as they pass through that magnetic gradient, some would be pulled strongly up, some slightly up, some not at all, some slightly down, and some strongly down. You'd absolutely expect to see a continuous vertical smear of silver deposited on the glass plate. A smooth line, basically, reflecting a smooth distribution of random starting angles.
But then they pull the glass plate out, and there was no smear.
Nope.
The plate showed two distinct, completely separate spots. The beam of silver atoms had split perfectly in two.
It's amazing. And the reason it's exactly two spots comes down to the atomic structure of silver. A silver atom has 47 electrons, but 46 of them form a closed, symmetrical inner core where all their magnetic moments just cancel each other out perfectly.
Leaving just one.
Leaving just one single unpaired electron in the outer shell. And an electron has a spin of 1/2. Following the quantum rules we talked about earlier, a spin of 1/2 only allows for two possible states along the axis of the magnetic field. Positive 1/2 or negative 1/2.
So spin up or spin down.
Spin up or spin down. There are literally no other options.
It is hard to overstate how miraculous that result must have felt. The atom's magnetic moment somehow knows that it's only allowed to take on certain specific components in the direction of the magnetic field. This wasn't a math error or some theoretical quirk. It was physical, undeniable proof sitting right there on a piece of glass.
Yeah, proof that the universe operates on discrete quantum rules, whether our human brains find it intuitive or not.
Exactly. So once we proved this discrete splitting happens, the next logical question was, well, can we control it? Which brings us to Irabi and his molecular beam method. And this is where the engineering gets unbelievably precise. We're moving from a smeared piece of glass to actively manipulating individual atomic states.
Yeah, Rabi and his collaborators basically took the core premise of Stern-Gerlach and built an entirely new way to probe the atom. It is such an elegant piece of experimental design.
Let me paint the picture of this gauntlet for you. You have an oven shooting out a beam of atoms, just like before. They enter magnet 1, which has that sharp edge, that strong gradient we talked about. This magnet acts as a sorter. It pushes the spin-up atoms downward and the spin-down atoms upward.
Okay, yep.
So the beam splits into two paths, flying through the vacuum. Let's call them path A and path B. Then they fly through a second magnet, magnet 2. And finally, they enter magnet 3. Now, magnet 3 is identical to magnet 1, but completely upside down. The field is inverted.
Right, it's flipped.
So whatever force magnet 1 applied, magnet 3 applies the exact opposite. Magnet 3 refocuses both path A and path B right onto a tiny hot tungsten wire, which acts as a detector.
That's the setup.
But wait, if magnet 1 pushes them apart and magnet 3 is completely upside down and pushes them right back together, aren't we just building a very expensive way to do absolutely nothing? The beam just goes back to where it started. What is magnet 2 actually doing in the middle?
Well, the middle step is the entire point of the machine. Magnet 2 is the laboratory where the actual manipulation happens. See, Magnet 2 has a very strong, completely uniform vertical magnetic field. Because it's uniform, as you mentioned earlier, it doesn't push the atoms up or down. They just fly straight through it without changing their trajectory.
Right.
But inside Magnet 2, Rabi added something else. He added a set of coils that produce a very weak, horizontally oscillating magnetic field. He is effectively tickling the atoms with microwaves or radio frequencies as they fly through that strong vertical field.
Tickling them. I love that. So you have the strong vertical field holding them at attention and this weak horizontal field buzzing at them.
Yeah, and this brings in the concept of precession. The source has some great diagrams comparing this to classical physics. If you have a toy gyroscope or a spinning top on a table and it starts to lean, it doesn't just fall over.
Right, spins around.
Exactly. Because of angular momentum, gravity pulls on it, and it precesses, it sweeps out a cone, rotating around the vertical axis. To actually change its angle relative to the table, you can't just push it straight over. You have to apply a force that perfectly matches its precession.
Oh, I see.
So in our quantum setup, the strong vertical field of magnet 2 causes the atom's magnetic moment to precess. If the weak horizontal field oscillates at the exact same frequency as that precession, it applies the right torque.
And when you hit that exact frequency boom, the atom absorbs a tiny quantum of energy from your microwave field, and its spin suddenly flips. An atom that was spin up just jumps to spin down.
Exactly. The classical gyroscope would smoothly change its angle. But in the quantum world, the atom makes an instantaneous jump from one discrete state to another. But the resonant frequency required to trigger that jump is exactly the same in both the classical and quantum models.
And here is where the trap of the gauntlet snaps shut. Because its spin flipped in the middle of the apparatus, when the atom enters magnet 3 is expecting a spin-up atom. Magnet 3 applies the force to refocus it, but because the atom is now spin down, it gets pushed the entirely wrong way.
It just flies off course.
It completely misses the tungsten wire detector.
And so the current on your meter suddenly drops. It's brilliant. You don't have to measure tiny deflections on a glass plate anymore. You just slowly turn the dial on your microwave frequency, and when you hit the exact quantum precession frequency of that specific atom, the detector current just plunges.
Wow.
It's an incredibly delicate and precise way to measure atomic properties, vastly more accurate than trying to measure the magnetic field itself.
Okay, so we've looked at single atoms flying through a vacuum. Let's scale this up. Let's move to the macroscopic world that you and I can actually see and touch. Bulk paramagnetism.
Right, when we talk about bulk materials like liquids, gases, crystals, we are dealing with a box full of countless atoms. Normally, in a molecule, the electrons pair up with opposite spins, and their magnetic moments completely cancel out. That is why, a piece of wood or a glass of water doesn't stick to your fridge magnet.
Right.
But certain atoms, specifically the transition elements like iron or chromium or the rare earth elements, they have unfilled inner electron shells. The spins don't cancel out entirely. So these atoms act like permanent, tiny little magnets.
But wait, if I have a crystal made of these tiny permanent magnets and I drop that whole chunk into a strong magnetic field, shouldn't it instantly become perfectly magnetized? Shouldn't every single atomic magnet snap to attention and line up perfectly with the field?
You'd think so, but you're forgetting about the environment they live in, which is heat. Temperature is just the random jiggling and shaking of atoms, so you have this constant tug of war happening. The external magnetic field is trying its hardest to pull all the atomic magnets into perfect alignment, but the thermal energy of the room is constantly kicking them around, randomizing their directions.
So it's a battle.
Exactly. At normal room temperatures, the amount of magnetization you get is just a compromise. It's roughly proportional to the field you apply. But if you apply a tremendously high magnetic field, or if you lower the temperature to almost absolute zero, you can achieve what's called saturation.
Meaning they all line up.
Yes. That occurs when the thermal jiggling is so incredibly weak, or the field is so dominant, that all the spins finally lock into the lowest possible energy state. They all line up.
And that concept of saturation leads to easily the coolest, literally the coldest practical application of these quantum rules in the text, adiabatic demagnetization, using magnets to build the ultimate deep freeze.
Walk me through the mechanics of this, because it sounds like actual magic. It is a phenomenal thermodynamic process. You start with a paramagnetic salt, something like praseodymium ammonium nitrate.
Catchy name.
Right. You cool it down the traditional way first, bathing it in liquid helium, which gets the salt down to maybe 1 or 2 degrees above absolute zero.
Which is already incredibly cold, but we want to go colder.
Way colder. So while it's sitting in that liquid helium bath, you turn on a massive electromagnet. Because the temperature is already quite low and the field is very strong, you achieve that saturation we just talked about. All the atomic magnets in the salt snap into alignment with the field.
Okay, they're locked in.
Once they're aligned, you thermally isolate the salt. You pump away the liquid helium, so the salt is suspended in a hard vacuum. It has absolutely no way to easily exchange heat with the outside world. And then you slowly turn off the magnetic field.
And the temperature of the salt plummets, but why? If I just flip a magnet off, why does the crystal physically get colder? Where does the heat go?
It goes back to that tug of war. When you start lowering the magnetic field, the thermal vibrations that are still left in the crystal, that 1 or 2 degrees of residual heat, they start trying to knock the atoms out of alignment. The spins naturally want to randomize.
Right.
But because there is still a lingering magnetic field present as you slowly dial it down, an atom has to do physical work to flip its spin against that field. It needs energy to jump from the aligned state to the higher misaligned energy state.
Oh, so it has to pay an energy toll to flip?
Okay.
And because it's in a vacuum, the only place it can get that energy is from the thermal vibrations of the crystal lattice itself?
Yes. It steals the energy directly from the lattice. Every time a spin gets knocked out of alignment, it absorbs a tiny bit of kinetic heat energy, effectively erasing that heat from the material. As you smoothly bring the magnetic field to zero, this internal energy theft drops the overall temperature of the salt from a few degrees down to a few thousandths of a degree above absolute zero.
You are using the internal structure of the atoms to freeze the atoms themselves. That is incredible. But scientists realized they could go even colder. Nature provided a secondary mechanism hidden even deeper inside the atom.
Yeah, we've been talking entirely about the magnetic moments of the electrons. But the nucleus of the atom, the protons and neutrons, also has a magnetic moment. They spin, too.
Which pivots us to nuclear magnetic resonance, or NMR. But if the nucleus is magnetic, why don't we just use that to cool things down from the start? Why bother with the electrons at all?
Because of the mass difference. Protons are almost 2,000 times heavier than electrons. And in the physics equations that govern this, mass sits in the denominator.
Yeah.
The larger the mass, the smaller the resulting magnetic moment. A proton's magnetic moment is roughly 1,000 times weaker than an electron's.
Which means if you want to use the nuclei to cool things down, a regular liquid helium bath isn't going to cut it. You have to start at 1,000th of a degree just to get the nuclear magnets to line up in the first place.
That is the trick. You use the electron stage to get the material down to 1,000th of a degree. Then you run the exact same demagnetization process a second time, but now utilizing the nuclear spins. When you demagnetize that second stage, the energy theft drops the temperature to within 1/1,000,000th of a degree of absolute zero.
1/1,000,000th of a degree. Just staggering. But this weak nuclear magnetism isn't just a parlor trick for freezing things. It actually allows us to look inside matter. The problem is, because it's 1,000 times weaker, observing it is a nightmare.
Oh, absolutely.
The source mentions that if you take a simple glass of water and put it in a strong magnetic field, the thermal jiggling is so dominant that the difference between protons pointing up with the field versus pointing down against it is incredibly slight. It's only about 1 part in the 100 million.
Right. For every 100 million protons pointing the wrong way, you have 100 million and one pointing the right way. That single extra proton is the only thing capable of absorbing a net amount of energy. It's your entire signal.
How on earth do you measure an energy absorption difference of 1 in 100 million?
You build an NMR apparatus. You take your sample of water and put it inside a small coil that blasts it with high-frequency radio waves. This whole setup is situated between the poles of a large electromagnet. But instead of constantly tuning the radio frequency to find the exact resonance like Robbie did with his atomic beams, you keep the radio frequency fixed.
Okay, so what changes?
Instead, you add auxiliary coils to the main magnet to slightly wobble the strength of the magnetic field itself.
Ah, you sweep the magnetic field back and forth across the resonance point. And when the field hits the exact right strength so that the precession frequency matches your radio frequency, those extra protons flip. They absorb energy from the coil, and you get a blip on an oscilloscope.
That's the idea.
But wait, if you're blasting it with radio waves and flipping that one extra proton to the higher energy state, doesn't it just get stuck up there? I mean, once you flipped enough of them so that the populations are perfectly equal, 50-50, the absorption would completely cancel out the emission. Wouldn't the signal just vanish entirely?
In perfectly pure water, yes, it would vanish almost instantly. The protons in water molecules are deeply insulated within their electron clouds. They have almost no thermal contact with the macroscopic vibrations of the water. Once they flip to the upper state, they can't easily shed that energy back into the environment. They get stuck. The populations equalize, and your 1 in 100 million signal disappears.
So how do you keep the signal alive so you can actually observe it on a monitor?
You introduce a microscopic flaw. You add a little bit of iron oxide to the water.
You just add rust to it.
Essentially, yeah.
Uh-huh.
Iron atoms, as we discussed with the crystals, are very strong atomic magnets. As these iron ions jiggle around in the water due to thermal heat, they create tiny, rapidly changing magnetic fields. These highly localized varying fields act as a bridge, a thermal coupling between the insulated proton magnets and the heat of the water bath.
Oh, I see.
They constantly jostle the protons, allowing them to lose their extra energy back to the thermal bath, resetting them to the lower state. Because of this added iron oxide, the protons can keep absorbing energy from your radio coil, cycle after cycle, keeping the signal alive on your screen.
You have to literally dirty the water to see the quantum mechanics working. And the signal you get on the oscilloscope isn't just a clean, simple bell curve either.
No, it's quite complex. Because you are constantly wobbling the main magnetic field back and forth, the precession frequency of the protons is also constantly changing. As you sweep through resonance, you force a whole bunch of protons to start precessing synchronously together. They act like a tiny radio transmitter, inducing a voltage back into your receiving coil.
Right.
But a microsecond later, your magnetic field is swept slightly higher, so the protons are now spinning at a slightly different frequency than your fixed oscillator. The two frequencies go in and out of phase, creating an interference pattern. We call it a beat note.
Oh, it's exactly like when you're sitting at a red light and the blinker of the car in front of you slowly syncs up perfectly with the clicking of your own blinker. And for a few seconds they're in perfect harmony, but then they slowly drift apart and fall completely out of sync again.
That is a brilliant analogy. The protons in the oscillator sync up, the signal spikes, and then as the field sweeps on, they drift out of phase, the waves interfere, and the signal creates a rippling pattern until the protons eventually fall completely out of sync with each other, and the signal fades into the background noise.
Let's take a breath and just look at the journey we went on today. We started with the strange, rigid rules of the quantum compass. The fact that spin is locked into discrete states. We saw how Stern and Gerlach proved it by splitting a silver beam into two spots on a glass plate. We saw how Rabi built magnetic tracks to actively measure and flip those states with microwaves. We learned how to manipulate that exact same quantum weirdness to freeze matter to a millionth of a degree by stealing heat energy from a crystal lattice. And finally, we saw how we can listen to the faint 1 in 100 million whispers of spinning protons to look right inside a glass of water.
It's a lot to take in, but the real-world impact of all this is profound. This isn't just abstract physics confined to the 1930s and 40s. That NMR technology we just described is the foundation of modern chemistry and medicine. It is exactly how modern chemists map the complex three-dimensional structures of organic molecules, because nearby atoms shift the resonance frequency slightly, giving each molecule a unique signature. It's how they hunt for free radicals to understand chemical reactions in real time. And of course, it's the exact same principle behind every MRI machine in every hospital in the world, using magnetic resonance to image the tissues of the human body.
It really makes you think. If the mere act of tickling invisible quantum spins with radio waves has given us the ability to freeze reality to a millionth of a degree, to map the chemical building blocks of life, and to look inside the human body, what other invisible quantum phenomena are sitting right in front of us right now, just waiting for someone to find the exact right frequency to tune into?
If you want to completely break the laws of classical physics, you really don't need a billion-dollar particle accelerator.
No, not at all. You just need, well, a fridge magnet.
Exactly. Just the little magnet holding up a grocery list on your refrigerator.
Yeah.
Because when you look closely at that standard everyday object, the tidy, predictable machine of classical physics just grinds to a halt.
It completely falls apart. I mean, the equations don't merely get a little messy. They miss reality by a factor of over 2,000.
Which is just insane. So, welcome to the deep dive. We are getting into some truly fascinating territory today.
We really are. We're pulling from Chapter 36 of Volume 2 of the Feynman Lectures on Physics.
Yeah, and our mission today is to thoroughly unpack this famously dense source. Because what Feynman does here is he takes this mundane phenomenon, ferromagnetism.
Right, the incredibly strong magnetism you find in materials like iron.
Exactly. And he uses it to completely dismantle our assumptions about how the physical world operates.
He really does.
So if you've ever tried to read a spec sheet for an electric motor, or maybe you were just, insanely curious about how a junkyard magnet can lift a whole car, you've probably hit a wall of alphabet soup and conflicting terminology.
Oh, the terminology is a nightmare.
It is. So we're going to decode that for you today.
Right.
Start inside the atom to bust a very old myth about magnetic poles, wade through the historical unit confusion, look at how metal actually remembers its past, and end with that massive, humbling scientific error classical physics made.
Right. And to understand ferromagnetism properly, where the magnetic moments are just enormous, We first have to demolish a really common misunderstanding about what a magnet actually is.
Myth, basically.
Yeah, a myth. Because for a very long time, people believed in literal magnetic poles.
Like physical things.
Exactly. They pictured physical concentrations of magnetic charge sitting at the north and south ends of a bar magnet, acting just like positive and negative electric charges.
But Feynman points out there is no such thing as magnetic charge in the physical world, right? It's a phantom.
Completely made up. The reality of magnetism in matter comes entirely from circulating currents.
Specifically, atomic currents.
Yes. We are talking about electrons spinning or orbiting inside the atom. You sometimes hear these called Amperian currents.
Going back to André Marie Ampère, right?
Right.
Who was the first to suggest that magnetism was just electricity traveling in tiny circles.
Right, exactly. So think about a cross-section of a simple magnetized iron rod.
Okay.
Deep inside that material, you have millions and millions of these tiny circular atomic currents just sitting side by side.
I was actually trying to visualize how this creates a macroscopic magnet earlier. Like, imagine a massive room, right?
Right.
Totally packed wall to wall with people, and everyone is spinning in place with their arms stretched out.
That's a great way to picture it.
Yeah, so in the middle of the room, nobody can actually complete a full spin. They keep bumping hands with the person next to them, effectively canceling out their momentum. One person's hand swipes up, the neighboring person's hand swipes down. The motion just cancels out completely.
Right, taking that room analogy a step further, deep inside the iron rod, those internal atomic currents perfectly cancel each other out in the exact same way.
So there's no net movement.
There's absolutely no net current in the middle of the material.
But at the very edges of the room, the people spinning along the walls have no one on the outside to bump into.
Exactly.
Their hands just swipe freely along the wall in one continuous direction. So around the entire perimeter of the room, you get this unbroken wave of motion.
And that's exactly what happens at the outer surface of the iron rod. Those atomic loops have nothing to cancel against. They combine to form one massive, continuous surface current wrapping around the entire rod.
Oh, wow.
Yeah, so a uniformly magnetized rod is physically equivalent to a long wire coil carrying a continuous electric current around its surface. That is what a magnet fundamentally is.
I have to admit some confusion on the math here, though.
Sure, what's tripping you up?
Well, if there's no such thing as magnetic charge, and it's all just these spinning atomic currents canceling out or creating edge currents, why do physicists still use math that looks exactly like the math for electric charges? Like Feynman shows them using a mathematical tool, the divergence of the material's magnetization, to calculate a magnetic charge density. Why are we using the math of a myth?
It really comes down to separating physical reality from mathematical convenience.
Okay, how so?
Calculating the exact microscopic reality of billions of tiny canceling atomic loops is an absolute nightmare.
Right.
It is simply too complex to be useful.
Right, impossible algebra.
But mathematically, if you pretend the material is filled with a density of magnetic poles, the equations suddenly look exactly like electrostatics.
Oh, I see.
Physicists had already spent decades solving incredibly complex equations for electric fields. By pretending magnetic charges exist purely for the math, they could take all those solved equations and just swap the variables.
So it's just a giant shortcut. They recycled the math.
Exactly. It's a macroscopic shorthand. But Feynman warns us that this shorthand created a massive historical mess of terminology.
Oh, the alphabet soup.
Yes. Because we abstracted the physical reality into vectors and hypothetical poles, we ended up with this alphabet soup that continues to confuse anyone working with magnetics.
Let's get into that alphabet soup then, because a few years ago, I was looking at a spec sheet for a little hobbyist electric motor I wanted to buy, and I was immediately lost in the terminology.
I don't blame you.
It's incredibly validating to hear a Nobel laureate basically admit that standard textbook terminology is a disaster.
Let's define the key players so anyone looking at those spec sheets can actually navigate them. There are three main vectors you'll encounter. First is B.
Okay, B?
You can think of B as the fundamental magnetic field. It represents the physical reality of the field itself.
So B is the real deal, the actual magnetic field in the room.
Exactly. Then we have M, which stands for magnetization. M represents those atomic currents we just talked about.
The spinning people.
Right. Think of M as the material's internal magnetic density. How many of those tiny spinning atomic currents are actively packed into a specific chunk of the metal and lined up?
So B is the total field, and M is the material's internal magnetic state.
Perfect. And finally, we have H.
Yeah.
Keeping track of external conduction currents, like the electricity you push through a wire from a battery, and the material's internal atomic currents simultaneously was just too messy.
Too much to calculate.
So physicists created a derived field called H. Essentially, H is just B minus M, adjusting for some fundamental constants.
The conceptual anchor I use for this is thinking of H as the magnetizing effort.
Oh, I like that.
Yeah, it's the external current you are intentionally applying through a wire. And B is the total result you actually get, which includes both your external effort and the material's internal reaction.
Framing it as effort versus result makes the mechanics much clearer. But here's the horrible thing Feynman explicitly points out about the history of these terms.
The unit confusion.
Yes, it involves the unit systems. In physics, we often use the MKS system, meters, kilograms, seconds. In that system, B and H are both measured in the exact same units, called Webers per square meter, or Gauss.
Which makes sense. Just for context, 10,000 gas equals 1 Weber per square meter.
Right. And since they're both fields, giving them the same physical unit makes perfect sense.
But engineering textbooks mess this up, don't they?
Big time. Many engineering textbooks define H differently, giving it the units of amperes per meter. They measure B in Gauss and H in amperes per meter. To make it infinitely worse, some systems give D and H the exact same mathematical dimensions, but call the unit for B Gauss and the unit for H Ørsted.
Wait, which means they're the exact same physical unit, just given completely different names.
Yes.
If you're reading a chart and one axis is Gauss and the other is Ørsted's, you are looking at the same underlying measurement. It's like measuring your height in feet and your width in vertical inches.
That is a perfect way to put it.
It serves no purpose other than to be confusing.
It was done historically to keep track of whether they were talking about the effort or the result, but it ended up tormenting generations of students.
I bet.
But if we push past the terrible naming conventions, the relationship between our magnetizing effort, H, and our total result, B, reveals something almost magical about metals.
Let's talk about what actually happens when you apply that effort to a piece of iron. Because the reaction is not a simple, straightforward, straight line.
No, it's not.
It's really a story of memory.
Feynman sets up a classic conceptual experiment here. Imagine taking a solid donut of soft iron, a torus, and wrapping it tightly in insulated copper wire.
Okay, got the visual.
When you run an electric current through that wire, you are applying H. You are applying your magnetizing effort.
And because of the iron donut inside the wire, the resulting field, B, goes absolutely wild. You don't just get the weak magnetic field from the copper wire.
Right. The little atomic slave magnets inside the iron wake up, they line up with the field you applied, and they produce a magnetic result vastly larger than the current alone could ever achieve.
So if you plot this on a graph, starting with completely unmagnetized iron, as you increase your effort, H, the result, B, shoots up rapidly.
It skyrockets, but eventually the curve levels off. It flattens out completely into what we call saturation.
Because there are only so many atomic loops in that piece of iron, right?
Right.
Once they are all lined up, that's it. You can push 10 times more current through the wire, but the iron has no more help to give.
Exactly. The crucial revelation happens when you slowly turn that wire current back down to zero.
This is the mind-blowing part.
The classical expectation is that the graph should just trace perfectly backward. Zero effort from the wire should equal a zero magnetic field result.
But when your effort H reaches zero, the result, B, does not go back to zero. The iron remains magnetized.
It has essentially become a permanent magnet.
The state of the iron depends on its history, not just what is happening to it in the present moment.
Right.
If you actually want to force the magnetic field back to zero, you have to run a negative current in the opposite direction to scramble those atomic loops again.
Right, and this looping, lagging behavior is called hysteresis.
Hysteresis.
Yes. If you trace that entire process, pushing the iron to saturation, bringing the current to zero, pushing it negative until it saturates the other way, and bringing it back again, you draw a wide, continuous loop on the graph. This is the hysteresis curve.
Pushing those internal atomic loops back and forth isn't free, though, is it?
No, the energy required to constantly flip those internal magnetic domains back and forth is lost from the electrical circuit. It turns directly into heat inside the iron.
Heat.
This is known as hysteresis loss.
From a practical standpoint, if hysteresis causes heat loss, are engineers always trying to find metals with no memory? Do we always want to avoid it?
Well, it depends entirely on what you were trying to build.
Okay, give me an example.
If you are building a power transformer for the electrical grid or an audio amplifier, you are flipping that alternating current back and forth 60 times a second or more. In that scenario, you absolutely must minimize hysteresis loss, or your transformer will physically melt from the heat. So engineers develop special transformer iron alloys mixed with silicon to create a material with a very narrow hysteresis loop. It forgets its history easily, so it doesn't heat up.
But if I want to make a permanent magnet for an electric motor, or just for the refrigerator, I want an incredibly stubborn metal. I want a massive, wide hysteresis loop so it never forgets.
Exactly. You would use specific alloys like Alnico V for that. You pump it full of current, exactly ones at the factory, and it holds onto that magnetic field with everything it has.
So we have this metal whose behavior constantly shifts based on its history. How do engineers actually design machines around a material that is constantly moving the goalposts?
It's a great question.
And Feynman's explanation here is a masterclass in problem solving. We could look at how they design a classic electromagnet to see this in action.
Right. Imagine a giant C-shaped piece of iron, exactly like the massive magnets you see at a junkyard attached to a crane. There is a thick wire coil wrapped around the back of the iron C, and there's an air gap between the two open ends.
That air gap is where you put the scrap metal you want to lift. But that gap creates a mathematical paradox.
It does. The physical rule is that the total magnetic field, B, has to be continuous across the gap. The magnetic flux coming out of the top iron face has to equal the flux traveling through the air to the bottom face.
Makes sense.
But your effort, H, is completely different in the air versus inside the iron. And to make it seemingly impossible, we just established that the field inside the iron depends on its entire unpredictable hysteresis history.
So you are dealing with multiple unknowns and a moody material.
Algebraically, you cannot solve this directly.
The way they bypass the impossible algebra is with a graphical solution. It's essentially a contract negotiation between the electrical wire circuit and the iron core.
I love that analogy. The wire is the strict client with a fixed budget, and the iron is the moody contractor who changes their price based on what happened yesterday.
Exactly. You draw a graph. The battery and the wire have a strict mathematical formula. They say, based on this voltage, the length of the wire, and the size of this air gap, here is the linear relationship between effort and result we require.
Right.
You draw that as a straight line on the graph.
Because the electrical circuit demands a linear relationship.
Then, you look at your moody contractor. You overlay the iron's curved looping hysteresis graph on top of the straight line. That curve is what the iron is actually willing to provide based on its memory.
And where the straight line of the circuit intersects with the curved loop of the iron.
That intersection is the compromise. That single point tells you exactly what the magnetic field in the air gap will be. You don't solve the messy algebra, you just find where the demands of the wire meet the willingness of the iron.
It is a stunningly elegant visual solution to a severely nonlinear problem.
It really is.
But Feynman takes us deeper than the engineering. We know how to build an electromagnet, and we know how the iron behaves macroscopically. But why do these atomic magnets line up in the first place?
Oh, man. When classical physics tried to answer that specific why, it hit a brick wall at 1,000 miles an hour.
A huge brick wall. There is a microscopic battle constantly raging inside the iron. On one side, you have the magnetic field trying to force all the spinning electron moments to line up perfectly parallel with each other.
Okay.
On the other side, you have thermal motion. The ambient heat energy of the material causes the atoms to constantly jiggle and vibrate, which tries to randomize the electrons and knock them out of alignment.
Order fighting against chaos.
Exactly. The goal for physicists was to calculate the Curie temperature. This is the specific temperature where the thermal chaos drops low enough that spontaneous magnetization sets in.
So it's the point where the atoms overpower the heat and lock together into a permanent magnet on their own.
Right. And to figure this out using classical physics, they used an analogy from the study of dielectrics. They couldn't just look at the average field. They had to know what a single, solitary atom was feeling.
So they imagined carving out a tiny microscopic spherical hole inside the material.
They did. They calculated the macroscopic field from the rest of the metal and then tried to add back the localized field from the immediate neighboring atoms surrounding that hole.
And using the known magnetic moment of a single electron, they ran the classical equations to calculate the theoretical Curie temperature for nickel.
And classical magnetic theory predicted that nickel would spontaneously magnetize at a temperature of 0.24 kelvins.
Wait, 0.24 kelvins.
0.24 kelvins.
That is a fraction of a degree above absolute zero. That is unimaginably freezing cold.
The actual observed Curie temperature for nickel, the temperature where it becomes a magnet in the real world, is 631 kelvins.
Classical physics predicted 0.24 kelvins. The reality is 631 kelvins. That calculation is off by a factor of 2600.
It is a catastrophic failure of the classical model. To make the classical equations work, you would have to assume the local magnetic field interacting between the atoms was thousands of times stronger than it actually is.
Wow.
Classical magnetism simply cannot generate a force strong enough to overcome room temperature thermal jiggling.
Feynman does not mince words here.
Mm-hmm.
He calls classical magnetic theory a dismal failure when applied to this problem.
Because the force causing these electrons to line up so powerfully isn't a magnetic interaction at all.
Wait, ferromagnetism isn't magnetic?
No, the magnetic interaction between neighboring atoms is incredibly weak. The force that actually locks them together into a permanent fridge magnet is a purely quantum mechanical effect.
Really?
Specifically, it is driven by the Pauli exclusion principle.
How does a quantum rule about excluding things create a magnet? I'm trying to wrap my head around this.
Okay, so the Pauli exclusion principle dictates that two electrons cannot occupy the exact same quantum state simultaneously.
Right.
If two neighboring electrons have parallel spins, meaning they are spinning in the exact same direction, the quantum rules forbid them from being in the same physical space. They are strongly forced to space themselves out.
So because they have the same spin, they physically push away from each other.
Well, more accurately, they are prevented from getting close. And because they are kept further apart, the standard electrostatic repulsion between their negative charges decreases.
Oh, I see.
This spacing out lowers their overall energy, and the universe always prefers the lowest energy state. This effect, where parallel spins force spatial separation and lower the electrostatic energy, is called the exchange interaction.
Wow.
It is essentially an electrostatic force guided by quantum spatial rules, masquerading as a massive magnetic force.
That is mind-blowing. The magnet on my fridge isn't working because of classical magnetism. It's a quantum mechanical exchange interaction overpowering room temperature.
It really is.
But wait, that raises a massive question.
What's that?
If iron spontaneously magnetizes at anything below its Curie temperature, and the Curie temperature for iron is over 1,000 kelvins, then room temperature is drastically below the Curie point.
Right.
Why isn't every single chunk of iron, like every nail I pick up off the ground, already a strong, permanent magnet?
That's the trick. On a microscopic scale, inside any piece of iron at room temperature, it actually is completely and permanently magnetized.
But I've held unmagnetized iron nails. They do not stick to each other.
That is because of magnetic domains.
Domains.
Yeah. The iron is perfectly magnetized internally, but to minimize its overall external energy, the material naturally fractures itself into millions of microscopic chunks called domains. In one domain, all the atoms are perfectly aligned pointing north.
Yep.
In the domain right next to it, they're perfectly aligned pointing south. The next one points east. They organize themselves into a patchwork of random directions.
Oh, so they are internally fully magnetized, but externally they cancel each other out.
Yeah.
Just like the spinning people in the middle of our crowded room earlier.
Exactly. It isn't until you apply an external magnetizing effort, our old friend H, that you sweep through the material, force all those microscopic domain boundaries to shift and merge and align all those chunks in the exact same direction.
And that is when the macroscopic magnet is revealed to the outside world.
You've got it.
That perfectly ties the entire journey together. We started by busting the myth of physical magnetic poles, realizing that magnetism is all about microscopic Amperian currents swiping past each other.
We navigated the frustrating alphabet soup of B, M, and H, and explored why engineers were so tormented by unit confusion between Gauss and Orsted's.
We visualize the memory of metal through the hysteresis loop, seeing how iron holds on to its past and how engineers use graphical contract negotiations to deal with stubborn electromagnets.
And finally, we exposed the limits of the classical spherical hole model, realizing that the overwhelming strength of a permanent magnet fundamentally requires the quantum mechanical Pauli exclusion principle to exist.
We opened this discussion talking about the comforting predictability of classical physics. But ferromagnetism breaks that tidy machine. It forces us into a world of stubborn materials, unit chaos, and quantum rules.
It really is a completely different world.
So the very next time you pin a piece of paper to your refrigerator, look closely at that magnet. You are not holding a simple classical tool. You are holding a macroscopic manifestation of a deeply mysterious quantum mechanical interaction that absolutely baffled the greatest minds of the 20th century. resting right there in the palm of your hand.
That's a great way to think about it.
It makes you wonder, what other simple, mundane objects sitting around your house are hiding profound quantum secrets in plain sight. Keep wondering. Thanks for taking this deep dive with us.
If you take a heavy, solid iron bar and, hang it completely still from a thin string and simply flip the invisible magnetic fields inside of it, the entire metal bar will physically twist in midair.
It's just wild to think about.
It really is. So welcome to the deep dive. Today we are taking on an absolute classic piece of science. We're looking at chapter 37 of the Feynman lectures on physics.
The one on magnetic materials, right?
Exactly. And our mission today is to completely dismantle that grade school explanation of magnetism you probably learned as a kid. Because what is actually happening when you stick a magnet to your fridge is a beautifully bizarre, sometimes highly inefficient quantum reality.
Yeah, we're so used to experiencing magnetism as this smooth, macroscopic force, right? Like when you hold two magnets, you feel that invisible cushion pushing back.
It feels completely solid.
Right, but to really understand what's happening, the source text demands we abandon that illusion entirely. We have to look at it from a gross average point of view of millions of atomic currents whirling around.
Which means we're diving completely into the very counterintuitive world of quantum mechanics.
We have to. There's no other way to find its true origin.
Well, right off the bat, my first question reading through this was just, why is anything magnetic in the first place? And the text points out this massive, very common misunderstanding right out of the gate.
Oh, the exchange force.
Yes. It comes down to something physicists originally called the exchange force, which it turns out isn't actually a force at all.
Not even slightly. I mean, exchange force is a terrible, highly misleading name. It is not a force like gravity, and it's not a magnetic pull.
So what is it?
It is strictly a rule of quantum mechanics. Specifically, it's the exclusion principle. The rule just states that two electrons cannot occupy the exact same state.
So they can't be in the exact same location while possessing the exact same spin orientation.
Exactly.
Okay, so it's like organizing a high society dinner party. You have two extremely particular guests, and they absolutely refuse to sit next to each other if they are wearing the exact same outfit.
That's a great start, yeah. But let's take that dinner party analogy further. Imagine these two guests are forced to share a tiny love seat.
Like electrons sharing a chemical bond.
Right. To avoid breaking the rules of the party, one of them literally has to change their outfit. In the quantum world, that means one electron must flip upside down. They have to adopt opposite spins.
Oh, I see. So the universe naturally forces them to be opposites.
It does. Because of this exclusion principle, electrons naturally balance each other out with opposite spins. Having parallel spins in close proximity breaks the quantum law, unless you forcefully separate them.
And if you try to smash them together anyway.
Their energy skyrockets. So this dynamic acts like a force trying to turn the spins opposite to one another. And honestly, this is the fundamental reason why almost everything in the world around you is not magnetic.
Right, because the free electrons on the outside of most atoms naturally balance out in opposite directions, totally canceling their magnetic moments.
Exactly. Most materials are just perfectly balanced.
But then we look at things like iron, nickel, and cobalt, the classic magnetic materials. In those metals, the electrons seem to desperately want to wear the same outfit. They want to be parallel.
Yes, and this is where the text dropped a piece of physics history that completely shocked me.
The mathematical failure from 1927.
Yeah, it was a massive crisis for physics. When scientists used the standard foundational equations to calculate the interaction energy between neighboring electrons in iron, specifically using what's called the lambda term, in equation 37.1, they get the wrong sign.
Wait, meaning what exactly? Like, they just forgot to carry a minus sign.
Oh, no, it's much worse than a typo.
Yeah.
Getting the wrong sign means the fundamental equations governing the universe predict that the electrons in iron should want to be opposite.
Which means iron shouldn't be magnetic.
According to the direct math, iron should not be magnetic at all.
Wow. So the equations say fridge magnets just shouldn't exist. How did science patch that hole?
Well, they had to totally rethink the mechanism. The prevailing theory today is that it's not a direct interaction between two neighboring intermagnetic electrons.
So what's bridging the gap?
Conduction electrons. The ones flying freely around the outer edge of the atoms act as intermediaries.
Like microscopic messengers carrying a quantum rule from one atom to the next.
Precisely. Imagine an intermagnetic electron forcing a passing conduction electron to take an opposite spin. That conduction electron flies over to the neighboring atom, carrying this built-in prejudice.
And when it arrives?
It forces the next intermagnetic electron to be opposite to it. Because both inner electrons are forced to be opposite of the same messenger, they end up parallel to each other.
That is just brilliant.
It is. But I have to emphasize, even with this theory, nobody can perfectly calculate this just by knowing iron is number 26 on the periodic table.
That is wild to me. The foundation of our everyday technology is built on this strange, patched-together quantum messenger system.
Yeah, nature is messy.
But it makes me wonder, if these electron spins in iron are so strictly locked together by this exclusion rule, what does it take to break that rule? Like, can you just overpower the quantum math with raw physical energy, say heat?
You absolutely can, and it brings us to the Curie temperature. The text describes a remarkably simple experiment to visualize this.
The heated nickel wire.
Right. Imagine taking a piece of standard magnetic nickel wire at room temperature. It's strongly attracted to a magnet. But if you take a gas flame and heat that wire, the thermal energy starts warring against the quantum alignment.
The heat literally shakes the spins out of alignment.
Exactly. And the moment it crosses a critical thermal threshold, its Curie temperature, it completely loses its magnetism. The wire just drops away from the magnet.
But if you leave it near the magnet while it cools down,
The exact instant it falls back below that critical temperature, the quantum rules take over again, and it violently snaps back to the magnet.
the text charts this out in figures 37 to 1 and 37 to 2, and it's fascinating.
It's a great visual.
Yeah, because if you try to predict how a magnet loses its power as it gets hotter, using classical physics, assuming atomic magnets just gradually point in random directions as they warm up the curve you draw is totally wrong.
Classical physics fails completely there.
Right. But quantum theory predicts a very specific curve. The magnetization holds strong and steady, fighting the heat, until it takes a sudden, sharp nosedive to zero right at the Curie point.
And if we connect that to the broader thermodynamic picture, that sharp drop in magnetization perfectly mirrors a sudden drop in the material's specific heat.
Because it requires a specific amount of energy to finally shatter that quantum lock.
Exactly. But honestly, the most profound physical proof of this entire quantum spin system is the spinning magnet experiment you brought up at the very beginning.
Oh, yes. Figure 37 to 3, the hanging iron bar. When I read that, I couldn't visualize how flipping invisible microscopic spins translates into a heavy piece of metal physically moving.
It feels like magic.
It really does. How does that leap from the quantum scale to the macroscopic scale actually happen?
Well, it is a direct, undeniable demonstration of the conservation of angular momentum. We have to remember that quantum spin isn't just a metaphor.
Right, these tiny electrons possess real physical angular momentum.
Exactly. So when you surround that hanging bar magnet with an electrical coil and use it to force billions of atomic magnets to flip their spin direction from up to down.
That angular momentum has to go somewhere.
Exactly. The universe demands that the total angular momentum of the system remains conserved. If billions of electrons suddenly spin one way, the entire macroscopic chunk of solid metal must rotate the opposite way to balance the cosmic ledger.
So the invisible quantum spin physically kicks the bar.
It physically imparts momentum to it.
Okay, my mind is thoroughly blown by that. But it leads me to a glaring, obvious question.
Which is?
If iron atoms desperately want to pool their magnetic power and align their spins, why isn't every random iron nail on the ground a powerful magnet?
Yeah.
Like, why are most nails totally dead, magnetically speaking?
That is the perfect question, and it takes us straight into the microscopic architecture of the metal. It's all about domains.
Which they show in figure 37 to 4.
Yes. Imagine a single, perfect crystal of iron. If all its atoms aligned in one exact direction, it would project a massive magnetic field out into the surrounding room.
Right.
But in physics, creating a large external field in empty space costs a tremendous amount of energy, and nature is inherently frugal. It always seeks the lowest possible energy state.
So the crystal has to compromise. To lower the energy bill, it splits itself up.
Exactly. It divides its internal structure into microscopic regions called domains. One domain points its magnetic field up. The one immediately next to it points down.
Oh, so by alternating directions, the magnetic fields loop back on themselves tightly within the metal itself, rather than projecting out into the room.
You got it. The external field is effectively canceled out.
But wait, earlier we established that electrons in iron want to be parallel. If you have a domain pointing up right next to a domain pointing down, the boundary between them, the wall, has neighboring electrons pointing in opposite directions.
Right, at the very edge.
Isn't that breaking the rule we just talked about? Doesn't that cost energy?
It does. The text refers to it as wall energy. It's a strict economic balancing act by nature.
So it's a trade-off.
Completely. Creating a boundary wall costs energy, but it saves external field energy. A piece of iron will continually split itself into smaller and smaller domains until the energy it costs to build one more microscopic wall is exactly equal to the energy it saves by reducing the external field.
That's incredibly elegant.
Yeah.
But building those domain walls introduces another incredibly weird mechanical problem called magnetostriction, right?
Oh, yes. Magnetostriction is bizarre.
The text explains that when a crystal becomes magnetized, it actually changes its physical dimensions. Like it stretches out along the direction of the magnetization and squashes in the other direction.
The crystal lattice literally deforms.
So, going back to our analogies, imagine trying to pack a bunch of oddly shaped expanding suitcases into the trunk of a small car.
That sounds like a nightmare.
Right. If all those suitcases decide to expand in the exact same vertical direction, they're going to pop the trunk open. That's pure mechanical stress.
I like this. And to avoid popping the trunk, you have to organize them carefully.
Exactly. You pack some vertically, some horizontally, and that's what the domains are doing inside the iron crystal. They arrange themselves in these complex microscopic triangles and checkerboard patterns.
They are desperately trying to balance the magnetic energy of their spins with the crushing mechanical stress of their changing shapes.
And that perfectly balanced, highly stressed, internally neutralized puzzle is what is sitting inside an ordinary unmagnetized iron nail.
Yes. Which brings us to the chaos of real life.
Okay, lay it on me.
What happens inside that perfectly balanced nail when we force it to become magnetized? Say we bring a strong external magnet close to it.
You have to force those perfectly packed domains to shift.
Right. We do. And figures 37, 5, 6, and 7 show that this isn't easy because crystals have easy and hard directions to magnetize.
Oh, right. Iron prefers the 100 direction and nickel prefers the 111 direction.
Exactly. They have geometric preferences. But figure 3710 shows us that a real, everyday iron nail is not a perfect, single laboratory crystal.
It's an absolute mess.
A total mess. It's polycrystalline. It is packed full of impurities, bits of dirt, internal physical strains, and crystal dislocations.
So it's not a smooth grid at all.
Not even close. So when you apply an external magnetic field, the domains that happen to be aligned with your field try to grow. They do this by pushing their boundary walls outward, eating up the neighboring domains.
Like a microscopic land grab.
Right. But as those boundary walls move through the metal, they get physically snagged on the impurities.
They get stuck on a piece of microscopic dirt. So the external magnetic field keeps pulling, building up tension, like pulling back a rubber band.
Yes. The tension builds and builds on the stuck wall until finally snap. The wall breaks free and jerks violently forward through the crystal until it hits the next impurity.
Oh, wow.
So the magnetization of a real piece of iron does not happen in a smooth, continuous flow. It happens in thousands of microscopic, violent, jagged jerks.
And the most amazing part is that you can actually hear this happening. The text describes the Barkhausen effect in figure 3711.
It's such a brilliant experiment.
If you take a piece of silicon steel, wrap a coil of wire around it, connect that coil to an amplifier and a loudspeaker, and then just slowly bring a magnet near the steel, you do not hear a smooth hum.
No, the author describes it beautifully. It sounds like a rush of distinct clicks, almost like sand grains sliding down a tilted tin can.
So every single click you hear is a microscopic domain wall violently snapping past an impurity inside the metal.
Exactly. You are listening to the crystal structure snagging.
Okay, let me piece this together, because if these walls are violently snapping and jerking around, those jerky motions must cause rapidly changing local magnetic fields.
Which does what?
Well, in a metal, changing fields create tiny electrical eddy currents. And those electrical currents bleed away energy in the form of heat.
You're tracking perfectly.
So if you've ever touched the power brick for your laptop after it's been plugged in for a while and notice it's warm, is that what I'm feeling? Is that energy loss what we call hysteresis?
You nailed it. Hysteresis is quite literally the friction of domain walls dragging and snapping across the imperfections of the crystal lattice.
And that's why it gets hot.
Yeah, because of that friction, magnetizing and demagnetizing a piece of iron is not a perfectly reversible, efficient loop. You permanently lose energy as heat every single time a wall snaps.
That's a huge problem for engineering, isn't it?
It is, but once we understand that mechanism, we can see how engineers brilliantly exploit this exact friction to create modern technology. Because iron isn't just one monolithic material we use for everything.
Right. The text points out that its behavior depends completely on its crystal structure. Like stainless steel is mostly iron, but because it has a face-centered cubic lattice instead of a body-centered one, it's virtually non-magnetic.
So structure is everything.
Absolutely.
So how do we exploit it?
Well, say you are an engineer trying to design a permanent magnet like the ones holding menus to your fridge, or the heavy magnet driving the cone in a loudspeaker. You want a material with an incredibly wide hysteresis loop.
Meaning you want it to be very hard to magnetize in the first place.
Exactly. But once you finally force those domains into alignment, you want them to stay locked in that position forever.
Oh, I see. You want to maximize the snags. You want those domain walls trapped in a prison of dirt and stress.
You've got it. Figure 3712 details a material called alnico V to show how hard this is. Making this magnet requires immense metallurgical violence.
Violence.
Yeah. Engineers deliberately mix 5 different metals: iron, aluminum, nickel, cobalt, and copper. As it cools from a liquid, a completely separate phase of material precipitates out into tiny grains, creating massive internal physical strains.
Right. They even have to cool it while it's sitting inside a strong external magnetic field so the crystals grow with a built-in directional bias.
That sounds incredibly tedious.
It is, but the result is a hard magnetic material where the domain walls are virtually locked in place by impurities and internal stress.
Okay, but what if you were an engineer building a power transformer for the electrical grid? You absolutely do not want locked walls.
Not at all. A transformer operates on alternating current. Its magnetic field is flipping back and forth dozens of times a second.
So if you built a transformer out of alnico V, the sheer friction of those walls snapping back and forth would generate so much heat the transformer would literally melt.
It would be a disaster. So you need the exact opposite. You need a magnetically soft material where the walls glide effortlessly.
Which brings us to the permalloys.
And to the permalloys. These are meticulously pure mixtures, typically about 70 to 80% nickel and the rest iron. By mixing them in exact ratios, engineers manage to cancel out the crystal anisotropy.
Meaning the alloy no longer cares which direction it's magnetized in.
Right. But even more brilliantly, the magnetostriction effects the expanding suitcase problem of iron and nickel have opposite mathematical signs.
Wait, really? So at the right ratio, they just cancel each other out?
Exactly. At about 80% nickel, the material simply stops changing shape when magnetized. No mechanical stress at all.
So the domain walls just glide through the material like ice on glass?
They do, but it comes with a major caveat. Because it relies on such flawless crystalline purity, permalloys are incredibly delicate.
How delicate are we talking?
If you take a piece of permalloy and just bend it with your bare hands, you introduce physical dislocations into the crystal lattice.
Oh, wow. So you ruin its perfect structure.
Yep. The domain walls start snagging on the creases you just made, and its magnetic permeability is completely destroyed.
It's amazing how we've managed to manipulate iron and nickel into these perfectly tailored, hard and soft materials.
It really is an engineering marvel.
But the text doesn't stop there. It gets into some incredibly exotic materials, where those quantum rules we talked about at the beginning, the exclusion principle forcing alternating spins, actually works perfectly.
Right. Materials where the wrong sign math actually functions like it's supposed to. A great example is chromium.
Figure 3713, right.
Yes. In chromium, the quantum exchange rule works exactly as predicted. The atomic spins perfectly alternate up, down, atom by microscopic atom.
So every single spin perfectly cancels out its neighbor?
Exactly. Because of that, chromium projects absolutely zero external magnetic field. It's a class of material we call anti-ferromagnetic.
So it's fiercely magnetic on the inside, but completely invisible on the outside.
Correct. But then nature throws us a curveball with a class of materials called ferrites, shown in figure 3714.
The text uses the mineral spinel as the prototype for this.
Yeah, imagine a crystal lattice with 2 entirely different kinds of metal atoms. Let's call them A atoms and B atoms. The strongest quantum interaction forces all the A atoms to spin up and all the B atoms to spin down.
So they perfectly alternate, just like chromium.
Right.
So they should cancel out and be invisible too, right?
You would logically think so. But in ferrites, the magnetic moment of the A atom is physically much stronger than the B atom.
Oh, so it's uneven.
It's a microscopic tug of war, where one side is inherently beefier. Even though they perfectly alternate, there is a leftover net magnetic force. The material as a whole is completely ferromagnetic.
That's fascinating. But why does that matter for modern technology?
Because here is the critical kicker. Unlike iron, which is a highly conductive metal, Ferrites are electrical insulators.
Oh, and because they are insulators, electricity can't flow through them, which means no eddy currents.
And no eddy currents means?
No heat loss from that specific kind of friction.
Exactly. If you put a solid piece of iron in a high-frequency microwave field, the rapidly changing fields generate massive electrical eddy currents on the surface. Those currents act like a solid shield, violently bouncing the microwaves away.
But because ferrites are insulators, microwaves pass right through them without generating currents.
Yes. This exact property makes ferrites absolutely essential for the modern world. Without them, microwave communication systems and radars simply wouldn't work.
It's like nature provided the exact quirky puzzle piece we needed for telecommunications.
The nature's full of those quirky puzzles.
Speaking of quirks, though, I have to bring up the yttrium iron garnet the text mentions. Because as I was reading it, the physics sounded completely backwards.
Ah, the garnets. Yes, this is where quantum mechanics really flexes its complexity.
Right. In these specific garnet crystals, the quantum rules force the electron spins of the iron atoms and the yttrium atoms to be strictly opposite to each other.
Standard quantum rules, yeah.
But the text points out that yttrium is a rare earth element, and its magnetism isn't just about spin. A huge portion of its magnetic field comes from the actual physical orbital motion of the electrons circling the nucleus.
Orbital moment, yes.
And here is where I got confused. The text says yttrium's orbital motion is not only physically larger than its spin effect, but it points in the opposite direction of its own spin.
It's a bit of a brain teaser.
So if the quantum rule forces the spins to be opposite, how do they actually interact?
It's a double negative scenario.
Yeah.
The quantum math forces the yttrium spin to point down, away from the iron. But because the yttrium's massive orbital motion points opposite to its own spin, the orbital motion points up.
Ooh.
So the total dominant magnetic moment of the yttrium ends up pointing completely parallel to the iron. The orbital loop completely overpowers the spin rule.
It's a perfect example of how wildly complex these atomic interactions get. And if you really want complex, the text briefly touches on rare earth metals, where the atomic layers don't just point strictly up or down.
The spirals.
Yeah, as you move from one atomic layer to the next, deep inside the crystal, the magnetic moment physically rotates slightly. It creates a literal three-dimensional spiral of magnetism through the metal.
Some of them even angle outward as they rotate, mapping out a microscopic cone shape.
The geometry of the quantum world is endlessly fascinating.
It really is.
So let's step back and look at the journey this text took us on today. We started by dismantling the misunderstanding of the exchange force, realizing it's really the exclusion principle forcing electrons into a high-stakes dinner party seating arrangement.
A very strict seating arrangement.
Exactly. We saw how raw thermal heat shatters that arrangement at the Curie point, and how flipping invisible spins can literally twist a suspended bar of heavy metal in midair.
The conservation of angular momentum in action.
We explored the economy of nature, how domains act like oddly expanding suitcases, and how their boundary walls, snagging on microscopic dirt, creates the clicks of the Barkhausen effect.
Which gives us the friction of his stasis, heating up our laptop chargers.
Right. And finally, we saw how engineers harness all of this chaos to freeze domains for permanent alnico magnets, or create perfectly pure permalloys for the power grid, and leverage insulating ferrites to make microwaves possible.
It is a stunning, comprehensive display of human ingenuity. We've managed to map the microscopic quantum world and harness it to build a modern electrical grid.
We really have.
But, you know, what I find most beautiful about this particular chapter is the grand irony the author leaves us with at the very end. It is a profound moment of scientific humility.
How so?
Well, think about everything we just discussed.
Yeah.
We have developed this wildly complex quantum mechanics. We can calculate spins, map out domains, balance wall energies, and engineer crystal lattices to the percentage point.
We're manipulating high-frequency microwaves.
Exactly. Yet the entire field of physics and magnetism started centuries ago by humans just observing simple natural lodestone and rubbing pieces of amber.
Right, the absolute basics.
And the author points out that even with all our quantum equations today, nobody really knows where the Earth's massive magnetic field actually comes from.
Wait, really?
Yeah, we have good geodynamo guesses, but no mathematical certainty. And even worse, we still do not fully understand the exact geological mechanism of why a piece of lodestone sitting in the dirt is naturally magnetized to begin with.
That is incredible. We can build supercomputers using quantum materials, but we still can't fully explain a magic rock we found in the dirt thousands of years ago. I absolutely love that.
It keeps us humble.
It definitely does. And it leaves me with a final, highly provocative thought for you to mull over.
Let's hear it.
The text explicitly mentions that calculating the exact interconnected correlations of atoms right at the edge of the Curie point, the exact mathematical moment those millions of skins transition from perfect order to thermal chaos, is a statistical problem that has baffled the greatest minds in physics.
It currently remains totally unsolved. It is a beautifully complex mystery of statistical mechanics.
Exactly. So what if the next massive technological revolution, say room temperature superconductors or perfectly efficient zero-loss energy transfer, isn't waiting for us in some undiscovered exotic rare earth metal?
That's an interesting thought.
What if the secret to the next century of technology is simply hidden inside the unsolved math of that exact phase transition? The answers might already be sitting right in front of us, trapped in the math.
We just have to solve it.
Right. So the next time you pick up a magnet to stick a menu to your fridge, or notice your laptop charger getting warm, I hope you look at that invisible cushion of force with a newfound respect. It's not just a physical quirk of nature, it is a literal window into the deepest unsolved mysteries of the quantum world. When you stand on the sidewalk, right, and you look up at a towering skyscraper, or maybe you drive across a massive steel suspension bridge, there's this incredibly comforting illusion of, well, absolute permanence.
Oh, yeah, completely.
You look at those gigantic steel girders and thick concrete pillars, and they just seem totally unyielding. Like, you push a structural wall, the wall pushes back, and absolutely nothing moves.
Right.
We completely take for granted that the floor isn't going to sink or shift when we step on it. It feels very binary. Either the building is standing firm or it's broken.
Well, the human scale is deceiving that way. We experience those structures as totally rigid because our senses just aren't in tune to see what's happening at the microscopic level.
Yeah.
But the moment you zoom in and start tracking the invisible forces acting inside those materials, I mean, that illusion of a solid, unbending world completely shatters.
And that shattering is exactly what we are focusing on for today's deep dive. We are taking you on a masterclass into these invisible forces, specifically unpacking Chapter 38 of the famous physics lectures, titled simply Elasticity.
A great chapter.
Really is. Our mission is to explore the hidden rules governing how seemingly solid substances deform, stretch, squish, and then bounce back.
But bouncing back is key here.
Exactly. We're going to see how the mathematics of that bounce apply to everything from, metal drive shafts and wooden blocks to the architectural foundations around you and even the deep interior of the Earth.
So to set some parameters for you as we dive in, we are looking specifically at the elastic behavior of homogeneous isotropic materials.
Right.
And that basically means we're dealing with non-crystalline substances that look and behave the exact same way no matter which direction you test them. So think of a block of pure steel or glass, rather than, say, a piece of wood that has a specific grain to it.
That makes sense.
Furthermore, we are only looking at what happens when they give under relatively small forces and then perfectly return to their original shape.
So we're skipping the extreme stuff. We aren't looking at what engineers call plasticity, where a metal beam permanently bends out of shape.
Right, no permanent damage.
And we definitely aren't looking at fracture, where things just violently snap in half. We are staying purely in the bouncy zone.
The bouncy zone, exactly.
And what I found so compelling about this source material is that it doesn't read like a dry engineering manual. It's a brilliant exercise in logic.
It really is.
We're going to strip away the complexity of a skyscraper and distill the invisible forces inside everyday objects down to just a couple of fundamental constants.
Which means starting with the absolute simplest scenario possible. I mean, before anyone can design an airplane wing or calculate the load on a suspension bridge, we have to understand the mechanics of grabbing a simple rectangular block of material by the ends and just pulling.
Let's unpack the mechanics of that pull.
Go ahead.
If you take that block and pull on it, it stretches. Pull a little harder, it stretches a little more.
Right.
For these small extensions we're talking about, the force you apply is directly proportional to how much it stretches. That's Hooke's law.
The classic Hooke's law.
It's the foundational rule of elasticity. But the text immediately introduces a roadblock, which is that simply knowing the total force you applied and the total distance the block stretched doesn't actually tell you anything fundamental about the material itself.
No, it really doesn't.
It mostly just tells you about the specific shape of the block you happen to be holding, right?
Exactly. If you think about, say, cementing two identical rubber blocks end to end to make one long block, Pulling them with the same force will result in a total stretch that is twice as big.
Oh, right, because there's twice as much material to stretch.
Yep. The actual rubber material hasn't changed its properties at all, but your measurement is completely different. Alternatively, if you put those two blocks side by side, creating a block twice as thick, you would suddenly need double the force just to get the original amount of stretch.
Okay, so to get around that, engineers and physicists had to standardize the math. They needed a number that describes the inherent stiffness of the material itself.
Right, whether it's aluminum or brass or bone.
Right, completely independent of whether it's shaped like a thick cube or a super long wire.
And they solved this by introducing two standardized metrics, stress and strain. So instead of looking at the total force, we calculate the force per unit of cross-sectional area. That is the stress.
Okay.
And instead of looking at the total physical stretch in inches or centimeters, we look at the fractional stretch. We take the amount of stretch and divide it by the original length of the block.
So it's like a percentage?
Exactly. That percentage of change is the strain.
And combining those gives us our first major constant, which is that stress equals Young's modulus times strain.
That's the one.
Young's modulus is that magic number. It tells you exactly how inherently stiff a specific material is. If I know the Young's modulus of a type of steel, I can predict how it will behave, whether I'm building a needle or a flagpole.
Spot on.
But as I was reading, I immediately hit a conceptual wall. Right after introducing Young's modulus, the text introduces a second constant Poisson's ratio. It points out that when you stretch a block lengthwise, it doesn't just get longer, it also contracts at right angles, like the sides get thinner.
The material sucks inward. The ratio of that sideways shrinking to the lengthwise stretching is what we call Poisson's ratio.
I picture pulling a piece of bread dough or like a thick piece of taffy. As you pull your hands apart, it gets longer, but it also visibly cinches in at the waistline.
That's a perfect analogy.
But my instinct reading this was to push back on the math a bit. Why are both of these constants necessary? I mean, if Young's modulus tells us how the material handles the applied force, shouldn't that be the whole story?
Well, if we lived in a purely one-dimensional universe where materials only existed as infinitely thin mathematical lines, yeah, Young's modulus would be the entire story.
Okay.
But materials exist in a three-dimensional world, and their atoms are linked together in a complex three-dimensional lattice.
Right, everything is connected.
Exactly. When you grab a block and apply tension along the z-axis, you are distorting those atomic bonds, and those bonds are connected to the atoms on the x and y-axis. The material's response basically cascades into those other dimensions because volume and shape are intrinsically linked by that internal structure.
Wow. Okay.
So you cannot fully define the elastic properties of an isotropic solid with just one number. You need Young's modulus to dictate the resistance to the direct pull, and you need Poisson's ratio to govern how that pull translates into sideways deformation. Together they form the complete DNA of the material's elasticity.
That makes a lot of sense. All right, so we've pulled the block in one direction and watched its sides shrink inward. But my immediate curiosity is, well, what happens if you trap the block?
Oh, like confine it.
Yeah. What if
Yeah.
you squeeze it so the sides literally have nowhere to go? What happens if we apply force to all sides at the exact same time?
That shifts us from linear tension into uniform hydrostatic pressure. Picture taking that same rectangular block and dropping it into a high-pressure water tank.
Like plunging it deep into the ocean.
Exactly. Now, instead of a localized pull, water pressure is pushing inward on every single face of the block simultaneously. Top, bottom, left, right, front, and back.
And the text handles calculating this in a way that I found so incredibly clever, using something called the superposition principle.
Oh, it's brilliant.
Because the elasticity of these materials behaves predictably and linearly in this bouncy zone, we can actually sort of cheat the math. Instead of trying to invent a horribly complex 3D spherical calculus problem, we can just calculate the squeeze in one direction, then the next, and basically stack them on top of each other like building blocks.
It is a supremely elegant workaround. You first calculate the compression from just the top and bottom pushing inward. Then you mathematically add the compression from just the left and right sides. Then you add the front and back.
Right.
But the crucial detail here is that Poisson's ratio is actively interfering during every single step of that stack. Well, when the top and bottom push in, Poisson's ratio means the sides are trying to bulge outward. But the left and right forces are simultaneously pushing inward, fighting that bulge. So you are constantly balancing a direct inward push on one axis against the sideways outward bulge caused by the compression on the other axis.
That sounds like a chaotic tug of war inside the block.
It really is.
And when you sum all of those competing pushes and bulges up, you get the volume strain, which is how much the total volume of the block physically shrinks.
Right.
The ratio of that volume stress to the volume strain gives us a brand new property, which is the bulk modulus. It's essentially the ultimate measure of how hard it is to shrink an object's total volume.
Exactly.
But here is where I want to linger, because the math leads to a truly mind-bending consequence. I was looking at the formula for the bulk modulus, and it involves Poisson's ratio in the denominator.
It does.
Specifically, the denominator has the term 1 minus 2 times Poisson's ratio. And the text casually mentions that because of this specific mathematical relationship, Poisson's ratio must be less than 1/2.
Yeah, in reality, for almost all practical materials you interact with, it sits comfortably between 0 and 1/3, maybe getting close to a half for rubber.
But I couldn't help but run the thought experiment. What if it wasn't? What if we found a strange alien material where Poisson's ratio was, say, 0.6?
Okay, let's run the numbers.
If you plug 0.6 into that formula, 2 times 0.6 is 1.2. 1 minus 1.2 is negative 0.2.
Right.
The denominator becomes negative, which means the entire bulk modulus becomes a negative number. What does a negative bulk modulus even look like in the physical world?
It's a fantastic thought experiment because it actually reveals the boundaries of physics. If a material had a negative bulk modulus, it would mean that as you increase the inward pressure on the block, like as you squeeze it harder and harder from all sides, the volume of the block would actually expand against that pressure.
Wait, so if I try to crush it in my hands, it pushes back harder and gets bigger?
Yes.
That's insane.
And the implications of that are universe-breaking. If it started to expand against pressure, it would continue expanding all by itself, releasing mechanical energy.
Oh, wow.
You could hook any random chunk of this material up to a turbine, give it a little squeeze, and it would do work for you indefinitely. You would have essentially created a perpetual motion machine.
I mean, I could power a whole city with a weird block of metal just by squeezing it. But of course, that completely violates the fundamental laws of thermodynamics. You can't get free energy from nowhere.
Exactly. Which tells us that such a material would be in a state of unstable equilibrium. It couldn't exist. It would spontaneously blow itself apart the moment it formed.
That's wild.
This is the beauty of the math. It proves that for any material to exist stably in our universe, its Poisson's ratio simply must be less than 1/2. Thermodynamics demands it.
That is just brilliant. Okay, so we've thoroughly covered changing the volume of a block under hydrostatic pressure. Now let's pivot and look at forces that change a material's shape without changing its volume at all. Physicists call this specific distortion shear.
Right. To visualize shear, picture a thick gel or a rubber cube resting on a table. The bottom face is glued down.
Okay, got it.
If you press your hand flat against the top face and push horizontally, the cube distorts. The vertical sides tilt. So that perfect square profile turns into a leaning parallelogram.
Okay, yeah.
That sliding distortion is pure shear.
What's wild is that the text offers an incredible geometric equivalence here. It proves that this sliding shearing stress isn't actually a unique force.
It's not.
It is mathematically identical to a combination of pulling and pushing the cube at 45-degree angles to its faces.
It can be tricky to visualize in an audio format. But think of a square sandwich. If you push on the top left corner and the bottom right corner at the same time, you are squishing it diagonally.
Right.
Simultaneously, the top right and bottom left corners are going to bulge outward, stretching that opposite diagonal. A shear force, that horizontal sliding motion, is really just tension and compression hiding in disguise, operating on a 45-degree tilt relative to the square.
It's all the same internal atomic tug of war, just viewed from a tilted perspective.
Beautifully put.
And just like we had Young's modulus for basic stretching, we have the shear modulus for this twisting and sliding. And this brings us perfectly to the concept of torsion.
Torsion is everywhere in engineering.
Yeah, which is twisting a rod, like the cylindrical drive shaft transferring power under a car. The torque needed to twist that shaft is proportional to the angle of the twist. But here is the incredibly practical takeaway for you listening. The math reveals that the torque required to twist a solid rod is proportional to the fourth power of the radius.
That fourth power completely redefines how engineers design machinery. It is an exponential relationship, not a linear one.
If you are an amateur mechanic and you want to upgrade an engine so it can handle more torque, you might look at the drive shaft and think, I'll just make the steel rod twice as thick, it'll be twice as strong.
Which seems logical.
Right. But because the resistance is tied to the radius to the fourth power, making it twice as thick doesn't make it twice as stiff. 2 times 2 times 2 times 2. Upgrading that radius makes the shaft 16 times stiffer.
To understand the physical mechanism behind that massive jump, you have to picture the solid rod not as a single cylinder, but as a series of nested, extremely thin concentric tubes, like the layers of an onion.
Oh, that's a cool way to look at it.
When you twist the rod, the material right at the dead center axis is barely moving at all. It's just rotating in place.
Right, it has nowhere to go.
Exactly. But the material on the very outside edge is being swept through a massive arc. That outer layer is experiencing a huge amount of shear strain.
Wow, okay.
Furthermore, because that outer layer is located physically further from the center axis, it has a longer lever arm. Just like using a longer wrench makes it easier to turn a bolt, the material further out has vastly more leverage to resist the twisting torque.
So it's doing way more work.
Oh, substantially more. When you make a rod thicker, you aren't just adding more metal. You are adding metal at the absolute most effective mathematical location, the extreme outer edge, where its lever arm allows it to do the maximum possible work.
That makes so much sense. Now, let's inject some reality into this model.
Yeah.
Up to this point, we've treated all these pushes and twists as static scenarios. We pull, it stretches, we twist, it resists.
The static world.
Right. But here is a real-world problem. When I step on the gas pedal of a car, the engine twists the front end of that drive shaft instantly. But does that torque reach the rear wheels at that exact same millisecond, or does the steel literally have to catch up?
The steel absolutely has to catch up. Nothing in the physical universe happens instantly. When we apply sudden forces, we transition from the realm of static elasticity into the world of elastic waves.
Elastic waves?
Yeah. If you abruptly twist one end of a long rod, you create a torsional wave, a traveling front of shear stress that physically works its way down the atomic lattice of the rod.
The formula for calculating the speed of that twisting wave is fascinating. The speed depends on the shear modulus of the material, which is how stiff it is, and the density of the material, which is how heavy it is. But impressively, the math proves the speed does not depend on the diameter of the rod.
That usually surprises people.
It shocked me. A twist will travel down a hair-thin steel wire at the exact same speed as it travels down a massive, solid steel pillar.
You might instinctively think a thicker, stiffer rod would snap the wave down faster. And, well, it does provide more restoring force.
Right, it's stiffer.
But a thicker rod is also proportionally more massive, which provides more inertia that actively slows the atomic movement down. Those two competing factors, the increased stiffness and the increased mass, perfectly cancel each other out in the equation.
That's incredible.
The geometry of the rod becomes completely irrelevant. The wave speed is dictated purely by the inherent nature of the material itself.
Now that covers a twisting shear wave, but you can also have a compressional wave where you just smash the end of a block with a hammer, much like a sound wave traveling through a solid wall.
In physics, we call that a longitudinal wave.
Yeah.
Unlike a shear wave that twists sideways, the atomic displacement in a longitudinal wave moves in the exact same forward direction that the wave itself is traveling.
Yeah.
It's compressing and expanding the material as it goes.
Right.
The speed of this wave depends on a slightly different property, called the longitudinal modulus.
And this brings us to a universal speed limit for solids outlined in the text. The math dictates that for any stable material, the longitudinal modulus is inherently mathematically greater than the shear modulus, always.
Which has huge real-world implications.
Exactly, because it means that longitudinal waves, those compressional smash waves, will always, unequivocally, travel faster than shear waves.
A mathematical rule that is monumental when you step outside the laboratory and look at the Earth itself.
This is exactly what I wanted to get to. Let's apply this to a massive planetary scale. This universal speed limit isn't just a quirk of metal rods. It is the entire foundation of how we understand the deep interior of our planet. How does this connect to seismology?
Well, it is the absolute bedrock of earthquake tracking. When an earthquake occurs, it is essentially a sudden, violent rupture in the Earth's crust.
A huge snap.
Exactly. That massive snap creates both types of elastic waves we just discussed, and they radiate outward in all directions through the rock. It creates longitudinal compressional waves, which seismologists call P waves or primary waves.
Okay.
And it creates the slower sliding shear waves, which they call S waves or secondary waves.
Yeah, because of that mathematical speed limit dictated by the moduli of the rock.
The P waves always win the race. They travel faster through the Earth's crust and mantle, arriving at a distant seismic monitoring station first.
The S waves lag significantly behind. If you are a seismologist watching the needle on a readout, you see a sudden, sharp jolt when that fast P wave hits. Then the needle quiets down and you wait.
Anticipation.
Exactly. It could be a few seconds, or maybe a full minute later you see a second, distinct jolt when the slower S wave finally arrives.
Wait, because geologists know the exact speeds these elastic waves travel through crustal rock, the time gap between those two jolts acts as a natural stopwatch.
You nailed it.
It's exactly like seeing a flash of lightning and counting the seconds until you hear the thunder.
That's the perfect analogy.
The longer the delay, the further away the storm is. With just one single seismic station, by measuring that simple time gap between the P and S waves, you instantly know the exact distance to the earthquake's epicenter.
It is a stunning example of how microscopic, atomic-level rules of elasticity scale up to dictate massive planetary phenomena.
It really is. Okay, we've zoomed all the way out to the size of the Earth. Now let's zoom back in to the buildings, tools, and objects right around you. Let's look at what happens when you combine these stretching and squeezing forces by taking a straight beam and bending it.
All right, grab a straight metal bar and bend it into a U shape, and you create a highly complex internal environment. The material on the inside curve of that bend is being forcefully compressed, essentially pushed together.
Okay.
Simultaneously, the material on the outside curve is being aggressively stretched apart.
But right in the middle of the bar, trapped between the outer stretching and the inner swishing, there is a boundary layer. The text refers to it as the neutral surface.
Right, the neutral surface.
It's a plane of material running right through the center of the beam that is neither stretched nor compressed. It experiences zero stress. It just goes along for the ride.
This concept leads us to the moment of inertia for a geometric cross-section. The stiffness of any bent beam depends heavily on how far away its physical material is located from that zero-stress neutral surface.
So location matters.
Massively. The material positioned far away on the extreme top and bottom edges is doing all the heavy lifting. It is doing the massive work of resisting the extreme stretching and extreme compressing.
Which perfectly explains one of the most common sights in modern construction, the I-beam. You look up at any unfinished skyscraper or bridge and you see thick steel beams shaped like a capital letter I.
It's an iconic shape.
It's not just an arbitrary design choice.
Yeah.
Engineers deliberately hollow out the entire middle section of the beam right where that neutral surface lives, because any steel placed there isn't actually doing any structural work.
It's literally just dead weight.
Exactly. Instead, they take all that math and push it to the extreme top and bottom flanges. By moving the material as far from the neutral surface as possible, they maximize the beam's stiffness while saving a staggering amount of weight and manufacturing cost.
It is pure structural efficiency, born directly out of the equations of elasticity.
And before we move on from bending, there's a brilliant tactile example in the text that you can try yourself, the rubber eraser experiment.
Oh, I love this one.
If you take a standard thick rubber eraser and bend it into a severe U-shape, the flat sides don't stay flat. The bottom inside curve, where the material is being compressed, visibly bulges outward.
Right, and it happens because rubber has a Poisson's ratio very close to 1/2, meaning it is practically incompressible. It flat out refuses to change its volume.
Right.
Since the inside curve is being forced into a smaller space, that physical volume must go somewhere else to compensate. So it literally squirts out the sides, creating a bulge you can feel with your fingers.
It bridges the gap between giant steel I-beams and a piece of stationery on your desk.
It really does.
But bending a beam horizontally is only half the architectural battle. What happens if you take a column and push it straight down from the top, like a pillar holding up a massive stone ceiling?
When you compress a perfectly straight column from both ends, it will hold strong and resist that compression up to a very specific critical threshold known as the Euler force.
Now, here's where I actually had to stop and reread the text. It states that for small bends, the force required to buckle a beam is completely independent of the bending displacement.
Right.
That absolutely defied my common sense. Shouldn't a beam be easier to keep bending once it starts to bow out?
Yeah.
Think about holding a long plastic ruler vertically and pressing down. Once it finally starts to bow out to the side, it feels like it just instantly gives way.
It is deeply counterintuitive, but the mechanism behind it is fascinating. When a column is perfectly mathematically straight, the load you place on it is purely compressing the atomic bonds.
Atoms fiercely resist being pushed closer together. It requires an immense amount of energy.
So the column stays straight.
Exactly.
Yeah.
But the moment it bows even a fraction of a millimeter outward, the geometry of the forces shifts.
Yes.
Suddenly, the downward load has a lever arm. It is no longer just compressing the column, it is bending it.
Oh.
And as we just discussed with beams, bending a material takes vastly less energy than purely compressing it.
So it's essentially an energy pathway problem.
Exactly. Up to the Euler limit, the column stubbornly resists compression. But the moment the load exceeds that critical force, the energy finds an easier path. The mathematical threshold is crossed, and the column basically chooses to bend rather than compress.
Wow.
It doesn't slowly increase resistance. It hits a mechanical cliff. It catastrophically gives way and buckles instantly.
That is terrifying for an architect. And as the text points out, it is a massive, persistent headache for aerospace engineers building space rockets. Because a space rocket is essentially just a giant hollow column sitting vertically on a launch pad.
A column that must be incredibly light to escape Earth's gravity, meaning the metal skin of the rocket must be engineered to be as paper-thin as absolutely possible.
Right.
Yet that razor-thin skin has to hold up hundreds of tons of liquid fuel, the payload, and withstand the massive g-forces of acceleration.
So much pressure.
If the structural load ever exceeds the Euler force for that specific cylinder, the entire rocket won't just slowly dent. It will instantly buckle and crumple like a stepped-on soda can before it even clears the launch tower.
That's a terrifyingly delicate balancing act of elasticity.
Very delicate.
We've covered a massive amount of conceptual ground today. We started by questioning the permanence of a skyscraper, and we've seen how simple, microscopic concepts like Young's modulus and Poisson's ratio basically cascade into macro-world reality.
Absolutely.
They dictate the mathematical impossibility of perpetual motion machines. They provide the stopwatch that allows us to track earthquakes across the globe. They dictate the iconic hollowed-out shape of the I-beams holding up the room you're sitting in right now. And they determine the razor's edge of whether a rocket reaches orbit or crumples on the pad.
It is a profound testament to the universality of physics. The laws of elasticity don't care if they are acting on a rubber eraser or a tectonic plate. The math remains perfectly consistent.
We started out by talking about how rigid and permanent a building seems. But if you look closely enough at the math keeping those structures standing, you find a weird, almost poetic secret at the very end of this chapter.
Oh, the elastic.
Yes. We just talked about that critical Euler force and how a column buckles when you push it too hard. If you take a beam and push it far past that critical limit, forcing it into a large sweeping bow, it forms a very specific geometric curve. Mathematicians call that curve the elastica.
Right. And to find the exact shape of that sweeping curve, you have to write out a pretty complex differential equation mapping its angles.
Right. But here's the magic trick. If you look at that differential equation describing the static, frozen physical curve of a bent piece of metal, it is perfectly, term for term, identical to the differential equation that governs the large amplitude swings of a grandfather clock's pendulum.
Yes. The spatial curve of a bent stationary rod is mathematically indistinguishable from the dynamic moving curve of time and motion in a swinging weight.
It is the universe recycling its absolute best math. It's taking the geometry of physical space and using it to perfectly map the geometry of time.
Beautifully symmetric.
So the next time you look at a towering skyscraper or a suspension bridge or just a simple bent piece of plastic on your desk, don't just see a boring, unyielding solid object. See the hidden dynamic dance of springs, waves, and beautifully recycled mathematics holding our reality together.
The solid world is infinitely more flexible and alive than it appears.
Thanks for taking the plunge into the bouncy zone with us today.
Welcome to the deep dive. Today we have a really fascinating stack of source material in front of us.
Yeah, we are getting into some deeply fundamental physics today.
We really are. Specifically, we're focusing on Chapter 39 of a classic physics text, which covers the elastic properties of materials.
Right, which sounds a bit dry at first, but it's actually incredibly relatable.
Exactly.
Yeah.
Our mission here is to take these dense theoretical concepts and figure out how the microscopic world of atomic forces, the really tiny stuff, dictates the macroscopic world of bending steel, bouncing rubber, and breaking chalk.
We want to understand the hidden, generalized rules of stress and strain inside literally any elastic body.
And that is the core challenge, right? Because
Yeah.
we are stepping way beyond the simple physics of stretching a basic rubber band in a straight line.
Oh, absolutely. We are looking at what happens when forces get complicated, multi-directional, and just generally messy. I mean, every single object you interact with today is secretly playing by these invisible rules of elasticity.
Which actually brings me to a visual I've been thinking about to kind of ground this whole discussion for you listening.
Yeah.
Picture a giant, perfectly cubic block of Jell-O sitting on a plate.
Okay, a giant block of Jell-O. I like it.
Now imagine pressing your hand flat on the top of that cube
Yeah.
and giving it a really hard grinding twist.
Oh, man.
Right? You can probably visualize the immediate chaos there. The sides bulge out, the top spirals, the whole thing shudders and warps into this incredibly complicated shape.
It does.
And mathematically describing exactly what is happening inside that squashed Jell-O is a profound problem because, well, the distortion isn't uniform.
No, not at all. It varies from point to point. Like, the squish at the top corner is completely different from the squish dead center.
Exactly.
So to even begin analyzing this, we need a way to track that local distortion anywhere inside the material. So returning to your Jell-O cube, imagine a microscopic speck of dirt embedded right in the middle, before you apply any pressure.
Okay, I have my little speck of dirt at point P.
Right, point P. Now you apply the twist. The Jell-O warps, and the dirt is dragged to a completely new location. Let's call it point P prime.
Got it.
The distance and direction it moved gives us a displacement vector. Now, if we were just uniformly stretching the Jell-O, the math is super straightforward. The movement of any speck is just proportional to its distance from the center.
But my twist creates, like, local variations all over the place.
Exactly. To handle this, the source text measures the strain by looking at the partial derivatives of those displacements.
Okay, let me just stop you right there. For those of us who haven't opened a calculus book in a decade, partial derivatives sounds a bit intimidating.
Fair enough.
You just mean we're looking at how the stretch changes as we take a tiny microscopic step left, right, up, or down, right.
That is a perfect way to translate it. Yeah, we are defining the strain at any specific microscopic point as a local percentage of stretch in X, Y, and Z directions.
Okay.
And we are also looking at the shear.
The shear.
Yeah, how much a tiny, theoretical, perfect cube of Jell-O gets skewed into, like, a slanted parallelogram shape. By calculating these tiny local changes across 3 dimensions, we build what is called the strain tensor.
Okay, I see the word tensor pop up constantly in this material. It sounds like a comic book villain, but if I'm understanding it, it's really just a mathematical tool.
Pretty much.
Like if a vector is a single arrow showing one direction, a tensor is more like a multidimensional translation matrix.
That's a great way to put it.
It maps an entire 3D input, like my hand twisting the Jell-O, into an entire 3D output of internal distortion.
You have the concept down perfectly. However, the text points out a really tricky mathematical trap when defining this strain tensor.
Uh-oh. A trap.
Yeah, imagine taking a little cubic section of your Jell-O, and instead of squashing it or skewing it, you just rotate it. You just spin that little cube a few degrees in space.
Okay, well, if we are tracking the specks of dirt inside that little cube, they have definitely moved to new coordinates.
They have. And if our mathematical definition of strain just looked blindly at displacement changes, it would look at those new coordinates and register a massive shear strain.
Wait, really?
Yes. Our equations would predict that this simply spinning object is under massive internal stress. But the atoms inside that rotated cube haven't changed their positions relative to each other at all.
Oh, I see.
The Jell-O isn't distorted. It is literally just facing a different direction.
Okay, I see the trap now. If the math accidentally flags pure rotation as physical strain, an engineer might calculate that a spinning airplane propeller is ripping itself apart from shear forces just by turning.
Exactly. Which obviously isn't happening.
So how do we engineer the math to ignore pure rotation?
We rely on the brilliance of a symmetric tensor, which basically fixes the problem through averaging.
Averaging. How so?
Let's look at the shear in the X and Y directions. The revised mathematical definition of this shear strain averages 2 specific things. First, how much the Y displacements change as you move along the X-axis. And second, how much the X displacements change as you move along the axis.
Let me think about that for a second. If the material is undergoing a pure rigid rotation, those 2 changes will be exactly equal, but pushing in opposite directions.
Yes, exactly.
Because one coordinate is gaining value while the other is losing it.
Right, which means one is mathematically positive and the other is negative.
Oh, I get it.
So when you add them together to find the average, they perfectly cancel out to 0.
That is a very clever workaround.
Wow.
By forcing the math to average those cross-directional movements, a pure rotation just completely vanishes from the equation.
Exactly. We get a foolproof grid of numbers, the strain tensor, that exclusively describes genuine physical squish and skew.
No fake rotational strain sneaking in.
None at all. So we now have a solid mathematical rulebook for describing the shape change. But here's the thing. If you strain an elastic material, it stresses. It pushes back.
All right.
That brings us to generalizing Hooke's law. The basic version of Hooke's law states that the stresses inside a material are proportional to the strains.
Sure, pull a spring twice as hard, it stretches twice as far. Linear and simple.
Simple for a 1D spring. But inside our complex 3D jello, both stress and strain are tensors with 9 components each.
Oh boy.
Yeah. To relate every possible direction of squish to every possible direction of pushback, we need an elasticity tensor. Mapping 9 components to 9 components requires an elasticity tensor with a whopping 81 possible coefficients.
Wait, 81 constants. Just to figure out how a single block of material pushes back.
Yep, 81.
How could any physicist or engineer work with that? If I'm designing a steel support beam measuring 81 different properties just to know if it will hold up, seems literally impossible.
It would be, but nature provides a massive simplification through symmetry.
Symmetry.
Okay. Think about a cubic crystal, which is essentially a microscopic 3D grid of atoms. Because it's a perfect cube, it has geometric symmetries. If you take that crystal and rotate it exactly 90 degrees, its physical structure doesn't change at all.
Because looking down the rows of atoms, the grid looks identical from both angles.
Exactly. It has the exact same atomic stiffness facing north as it does facing east. Mathematically, this means if we swap the x and y coordinates in our energy equations, the total energy must remain identical.
Right.
We can also reflect it in a mirror, changing a positive direction to a negative direction, and the crystal behaves the exact same way.
So mirror symmetry zeroes out a bunch of those constants.
Huge sections of them. Any mathematical term that involves an odd number of directional shifts, like 3 x's and 1 y, must be perfectly balanced by its negative counterpart. Therefore, it has to equal 0.
So all those weird asymmetrical pushback forces just zero out because the crystalline structure itself doesn't favor one side over the other.
You got it. By applying the rules of a cubic crystal symmetry, that overwhelming list of 81 constants drops down to only 3 non-zero possibilities.
That is a massive drop. 81 to 3.
Right. We only need 3 numbers to completely describe the elasticity of a cubic crystal. And actually, the news gets even better for isotropic materials.
Remind me, isotropic means what again?
These are materials where the atoms are randomly jumbled together, like in glass or plastic, rather than in a neat crystalline grid.
I would assume a random jumble makes the math harder, not easier.
It's counterintuitive, but it actually increases the symmetry.
Really?
Yeah, a random uniform jumble looks the same from absolutely any angle, not just rigid 90-degree turns. Because of this infinite rotational symmetry, the list of constants for isotropic materials drops from 81 down to just 2.
Just 2 numbers. Wow. The source text refers to these as the Lamé constants, right?
Yes, the Lamé constants.
What do those 2 numbers actually represent in the physical world? Like, what are they measuring?
They represent the 2 fundamental ways a material can deform. The first, Lamé constant, often associated with the bulk modulus, measures how much the material resists a change in volume.
Like trying to squeeze a bowling ball into a smaller sphere.
Exactly. The second constant, the shear modulus, measures how much it resists a change in shape without changing volume.
Like our jello skewing into a parallelogram.
Right. Those 2 simple numbers completely define how a standard isotropic material bounces back.
Okay, so we've gone from an impossible 81-dimensional problem to just 2 numbers. That's incredible.
It really is an elegant mathematical solution.
But this whole rulebook assumes the object is sitting in perfect equilibrium, right? It's squished, it's pushing back, everything is balanced and still.
Sure.
But the world is dynamic. What happens when we take that balanced jello and, flick it?
Then we enter the realm of dynamics, which requires writing out what the source text affectionately calls the horrible equation of motion for an elastic solid.
The horrible equation of motion. I love that.
It's horrible because when an object is moving or vibrating, it's no longer just internal stresses balancing out. We have to combine those internal stress forces with any external forces, like gravity, and equate the whole thing to mass times acceleration.
So we are basically applying Newton's second law, but scaling it down to every microscopic point inside a continuous solid.
Precisely.
And when you turn the crank on that math, what do we actually learn about the motion?
The math separates out into two distinct wave equations. This tells us that energy ripples through a solid material in two highly specific ways.
Okay, what are they?
First, you get compressional waves. These push and pull the atoms closer together and further apart, changing the local density of the material, but there's no shearing.
So like an accordion squeezing in and out as the energy passes through.
Great analogy. The second type are transverse waves. In these waves, the material shears side to side, but the overall density doesn't change.
Like shaking a rope up and down. No part of the rope is getting compressed, it's just waving.
Exactly. And what is crucial here is that these two waves travel at different speeds through the same material, and those speeds are dictated entirely by density and our two friends, the Lemay constants.
Let me see if I have the causality right here. The compressional wave, the accordion, is changing the volume of the material as it moves, but it's also stretching it lengthwise.
Right.
So it has to fight against both Lemay constants, the volume resistance, and the shear resistance.
Correct.
But the transverse wave is just sliding the material side to side without changing the volume, so it only has to fight the shear constant.
Your intuition is spot on. Because the compressional wave is resisted by a combination of both stiffness properties, it travels significantly faster.
Oh, wow.
This is actually why in an earthquake, seismologists always detect the compressional P waves before the transverse S waves arrive. The math perfectly dictates the physical reality.
That makes total sense.
Oh.
Okay, I followed the wave math when we were talking about a giant, simple block of uniform material. But if I'm engineering a crane hook to lift shipping containers, or like a car's crankshaft, I'm dealing with curves, sharp notches, weird geometries.
Very messy shapes.
Yeah. The text implies that calculating these wave and stress equations analytically for complex shapes is basically impossible on paper. So how do we figure out the internal stresses of these weird shapes before they break and drop a shipping container?
Physics relies on brilliant experimental tricks when the analytical math hits a wall. Instead of trying to solve the equation for a steel crane hook, engineers build a physical scale model.
Okay.
But they build it out of a clear, isotropic plastic like lucite.
Wait, I would think testing plastic doesn't tell you much about steel. They're completely different.
It doesn't tell you about the strength, but it tells you everything about the geometry of the stress.
Oh, I see.
Clear plastics have a property called birefringence. When they are at rest, they're perfectly isotropic. But when put under stress, the internal structure stretches, and it actually changes how light travels through it. If you shine polarized light through this clear plastic model while you are pulling it, the plane of the light's polarization rotates.
And the amount of optical rotation maps directly to the amount of physical stress.
Exactly. So when you look at the plastic model through a polarized filter, you literally see the stress. It shows up as these glowing, highly concentrated bands of light and dark fringes.
That is wild.
You can hang a weight on a plastic crane hook and immediately see exactly where the stress is concentrating, usually around the sharp inside curves, without doing a single piece of complex math. You make the invisible stress patterns visible.
That is like giving engineers X-ray vision. That's amazing.
It is a beautiful trick.
But of course, all of this elegant math, the wave equations, the glowing plastic, it all assumes that the material behaves perfectly elastically.
It does.
It assumes Hooke's law holds, and the material bounces back exactly to where it started. But real life tells us that if you pull something hard enough, it stops stretching and it just snaps.
Right. We have to address non-elastic behavior and the ultimate breakdown of Hooke's law. Because understanding how materials fail is just as important as understanding how they bend.
The source text uses a great example here that anyone can visualize. Think about holding a normal, straight cylinder of blackboard chalk.
Okay.
If you grab both ends and pull straight outputting under pure tension, it breaks straight across the middle. A clean, flat break perpendicular to the force.
Makes sense.
That makes intuitive sense because chalk's basically just compacted powder. It's weak in tension. You pull the particles, they separate.
Exactly.
But the text asks what happens if, instead of pulling, you grab the ends of the chalk and twist it like you were wringing out a towel.
And it doesn't break straight across. It breaks along a complicated spiral surface, forming a perfect 45-degree angle to the axis of the chalk.
Why would twisting a straight rod cause it to shatter at a diagonal? That seems so weird.
This brings us back to the strain tensor we talked about earlier. Twisting the chalk applies a pure shear stress. You are trying to slide the planes of chalk over each other.
Right.
And chalk particles are actually quite stubborn about sliding past each other. However, the math of the tensor reveals that a pure shear stress is completely physically equivalent to a combination of tension and compression acting at a 45-degree angle.
Wait, so the rotational geometry of the twist is secretly creating a massive diagonal stretching force.
It is. It's an indirect tensile force exactly at 45 degrees. Since we already know chalk is incredibly weak against tension, the chalk fails right there.
Wow.
It simply pulls itself apart along that 45-degree line of maximum tension before the shear forces ever get a chance to overcome the friction of the particles.
The math exposes the hidden pull. That's fascinating.
It's all connected.
Now, the text brings up another weird material behavior that breaks the rules. If you take a sheet of saran wrap, crumple it up into a tight ball, and throw it on the table, it doesn't stay a ball.
No, it doesn't.
But it also doesn't immediately pop back into a flat sheet like a perfect spring. It just slowly, kind of creepily, unfurls itself over several minutes.
The first assumption might be inertia, that the plastic is just too heavy to move quickly. But a simple calculation shows the mass of that plastic is far too small for inertia to cause that kind of delay.
So what's actually happening?
The slow unfolding points to a complex internal structure, which we describe using a viscous model.
A viscous model, like trying to move through thick syrup.
Right.
So if I'm trying to invent a mental model for this, instead of thinking of the plastic as a single solid sheet, maybe it's more like a cheap memory foam mattress or like a sponge soaked in thick honey.
The honey sponge is an excellent analogy. Picture the material as a network of long, stiff, flexible fibers tangled up with tiny hollow cells filled with a thick, viscous fluid.
Okay, I'm picturing it.
There are microscopic pathways between these cells. When you violently crumple the plastic, you bend those stiff fibers, but you also forcibly squeeze that thick fluid out of some cells and into others.
Oh, I see. So when I let go of the crumpled ball, the stiff fibers, the springs, desperately want to snap back to being flat. But they can't.
They can't because they have to drag that thick, viscous fluid back through the tiny microscopic pathways to restore the original shape.
Wow.
The stiff fibers are pulling hard, but the fluid acts like a brake, slowly leaking back. The macroscopic unfolding you see on the table is the visible result of the internal springs fighting the slow ooze of the fluid.
That perfectly explains why, if you take that crumpled ball of saran wrap and hit it with a hot hairdryer, it unfurls way faster.
Exactly.
The heat thins out the viscous fluid inside, turning the honey into water, so the internal springs can push it through the pathways with almost no resistance.
The macroscopic behavior is entirely driven by a microscopic tug of war.
So the real world is full of messy fluids, weird 45-degree breaks, and 81-dimensional mathematical nightmares. It kind of begs a fundamental question.
Which is?
Why does Hooke's law, the simple idea that stress is perfectly linearly proportional to strain, why does that work at all in the first place?
It's a fair question. The text answers that by taking us down to the atomic level. Mathematically, Hooke's law can be derived using a Taylor expansion of the strain energy.
A Taylor expansion. Again, let's strip away the jargon for a second.
Sure.
You're saying that if we don't know the exact, crazy, complex mathematical curve of how a material stores energy, we can just estimate it by breaking it into a series of chunks. A linear chunk, a squared chunk, a cubed chunk.
That is the essence of it, yes. If you assume the energy of a distorted material is some complex function of how much you bend it, you expand that function into a series.
Right.
For very, very tiny microscopic distortions, all the higher power terms mathematically shrink into insignificance. They just drop off. The simplest term, the linear squared relationship between energy and strain, completely dominates the equation.
So as long as the movement is tiny, the math naturally flattens out into a simple straight line. But a Taylor expansion is still just a mathematical trick for estimating. It doesn't tell us what the atoms are actually physically doing. The source text goes further and calculates these elastic constants directly from atomic properties, right?
It does. And this is where the physics truly synthesizes. Let's build a mental model of an atomic lattice. Imagine a flat, 2D grid of atoms, like a checkerboard.
Got my checkerboard.
Instead of abstract electrical forces, let's pretend every single atom is connected to its nearest neighbors up, down, left, right by tiny, perfectly linear physical springs. We'll call the stiffness of these primary springs K1.
A checkerboard of atoms connected by K1 springs.
Okay. That grid isn't structurally stable enough on its own, so we also connect the diagonal neighbors across the corners of the squares with a different set of springs. We'll call their stiffness K2.
Right, for diagonal support.
Now, we apply a bulk strain to the entire grid. We basically squish the whole checkerboard.
So all the atoms shift slightly closer together based on the strain tensor we talked about at the beginning.
Exactly. Because we know exactly how far the whole macroscopic material strained, we can calculate exactly how much every single microscopic K1 and K2 spring was forced to stretch or compress.
Oh, wow.
We calculate the tiny bit of energy stored in every single one of those microscopic springs, add it all up, and average it over the volume. By doing this, we can mathematically derive the macroscopic Lemay constants entirely from the stiffness of the microscopic K1 and K2 springs.
I am always skeptical of perfect theoretical models like this. I mean, invisible springs connecting dots on a grid makes for a great textbook homework problem.
It does.
But if we go into a lab and measure a real crystal, does the math from our little K1 and K2 spring model actually match real-world measurements?
Well, the ultimate test of any model is reality. The text provides the answer in Table 39-2.
Okay, let's look at the table.
The simple spring model mathematically predicts a highly specific relationship for simple cubic crystals. It dictates that two of the macroscopic elastic constants, specifically Cxxyy and Cxyxy, must be mathematically identical. Are they? If you look at the table for ionic crystals, like sodium chloride basic table salt, it works beautifully. The measured value for Cxxy is 0.127 and Cxyxy is 0.128.
They are essentially identical.
Yep. The microscopic spring model perfectly predicts the macroscopic behavior of a simple grain of table salt.
That is a massive triumph for the theory. That's
Yeah.
incredible. But scanning that same table in the text, it definitely doesn't work for everything.
Well, no, it doesn't. And where a model fails is often more illuminating than where it succeeds. If you look at the measurements for a diamond crystal, the model fails spectacularly.
Yeah, the constants aren't even close to being equal. One is 1.25 and the other is 5.76.
Exactly.
Why the discrepancy? Table salt and diamond are both highly organized crystalline structures. Why does one follow the spring rules while the other totally ignores them?
It comes down to the fundamental nature of their atomic bonds. Table salt is an ionic crystal. The sodium and chloride atoms are held together by pure electrical attraction positive and negative charges pulling directly toward each other along a straight line.
Oh, so they act exactly like the simple straight-line theoretical Colerain springs in our model.
Precisely. Diamond, however, is completely different. Diamond is held together by covalent bonds.
Covalent bonds involve sharing electrons in very specific orbits, right?
Yes. And because of how those electrons are shared, covalent bonds are highly directional. They don't just pull straight in, they prefer very specific, rigid geometric angles.
I see where this is going.
If you try to shear a diamond crystal, the covalent bonds don't just compress like a spring. They exert massive sideways pushes to maintain their preferred angles, almost like a structural beam resisting being bent out of shape.
So our simple straight-line spring model completely failed to account for sideways angular forces, so it completely breaks down for diamond.
Exactly. The model was too simple for covalent bonds.
Man, the macro world is genuinely just a blown-up reflection of the micro world. We started this discussion by tracking a single speck of dirt in a twisting block of jello.
They did.
We used averaging to dodge the trap of pure rotation, and we used crystal symmetry to shrink 81 impossible constants down to a manageable few. We separated wave speeds based on volume and shear, we visualized stress using glowing lucite, and we learned that twisting chalk breaks it with a hidden diagonal pull.
It's a lot to cover.
And finally, we built a grain of salt from the ground up using microscopic atomic springs.
The core takeaway that ties all of this together is that the microscopic rules of how our world bends, bounces, and breaks are not arbitrary.
Right.
They are strictly dictated by the microscopic geometry and the specific electrical forces of the atoms within them.
That is just so profound. So next time you break a piece of chalk or watch a crumpled piece of plastic slowly unfurl on your counter, realize you are witnessing a massive microscopic tug of war.
Millions of tiny atomic structures fighting for equilibrium.
Millions of them. And if the visible world is just an expression of these invisible forces,
Yeah.
what happens when we eventually figure out how to engineer materials from the bottom up?
It changes everything.
Think about it. If we can custom design the placement of every ionic spring and covalent angle to perfectly resist shear and strain, the materials of the future will be virtually indestructible. Something to think about. Thanks for joining us on this deep dive. If you think back to when you were a kid,
There's this almost universal memory I feel like we all share.
Oh, yeah. Like what?
Well, it usually involves like a rainstorm, maybe a really good mud puddle, or just a stream of water running down the gutter in the street. You look at that water, and what do you instinctively do?
You try to block it. You build a dam.
Exactly. You pile up rocks, mud, maybe some sticks, just trying to hold that water back. You're trying to force it to do what you want. And for a second, it actually works.
Right, but only for a second.
Yeah, inevitably, the water finds a way. It does something completely unpredictable. It breaks right through your little dam, and it escapes. And that childhood realization that water basically has a mind of its own is exactly what we're trying to decode in today's deep dive.
It's a great analogy because scientists have basically been doing the exact same thing, just with math.
Right. We're looking at some legendary physics notes from Richard Feynman today, specifically Volume II, Chapter 40 of his lectures on physics. It's all about his attempt to build a mathematical dam, a way to perfectly capture the flow of fluids using equations.
And it is a beautiful but also a deeply frustrating endeavor. Because to build that mathematical dam, physicists actually had to invent something that, well, it doesn't exist.
Which sounds crazy. What did they invent?
We're exploring a concept that the brilliant physicist John von Neumann cheekily called dry water.
Dry water. I mean, it sounds like a total oxymoron.
It completely is. Dry water is this perfectly idealized, non-viscous liquid. The whole mission here is to build the physical rules of this imaginary fluid, look at the truly mesmerizing things it can perfectly explain, and then
Discover how real water ruins it.
exactly. Discover exactly how real, messy water manages to break our mathematical dam and just escape all those elegant equations.
Okay, so before we can get this dry water flowing, we have to, establish the ground rules for water just sitting there.
Yeah.
Puddles before they become streams, right?
Right. In physics, the study of fluids at rest is called hydrostatics. And the defining feature of any fluid, whether we're talking about water, air, or, honey, as opposed to a solid block of wood, is its internal structure when it faces a sideways force.
A sideways force, so like pushing on it from the side.
Yeah. We call that shear stress.
Right.
So if you put a block of wood on a table and push the top of it sideways, the internal structure of the wood resists you. It holds its shape.
Right. It doesn't just flop over.
Exactly. But a fluid cannot maintain a shear stress. If you imagine a fluid like a freshly opened deck of slippery playing cards, pushing sideways just causes the layers to slide continuously over one another. It yields, it flows.
Which means if a fluid is perfectly static and not flowing at all, there are absolutely no sideways forces happening inside of it. The force is entirely perpendicular to the surface it's touching.
Spot on. And we call that perpendicular force pressure. And a really fascinating consequence of this is that pressure in a static fluid must be exactly the same in all directions.
Okay, let's visualize that for a second. So imagine a tiny microscopic cube of water just hanging out, right? Suspended right in the middle of a glass of water.
A perfect little cube.
Yeah. For that cube to remain perfectly still, the water surrounding it has to be squeezing it with the exact same amount of force from the top, the bottom, the left, and the right.
Because if there were any imbalance, literally any at all, the cube would just squirt away in the direction of the weaker push.
Right. So the only way that little cube of water experiences a net force is if the pressure varies from one side of the cube to the other. And that difference is what we call a pressure gradient.
Yes. If the pressure is higher on the left side than the right, the cube gets pushed to the right. So to stay perfectly still in the real world, that pressure gradient has to be perfectly balanced by something else.
Like gravity.
Exactly.
Yeah.
Gravity pulling it down while the pressure from the deeper, heavier water pushes it up.
But that is the messy reality. To make the math for all of this actually elegant, to build our dam, we have to introduce those dry water approximations we talked about.
Right, we have to strip away the complex properties of real fluids.
So first rule of dry water. We assume the fluid is completely incompressible, meaning no matter how hard you squeeze it, its density remains completely constant. You just can't pack more of it into a smaller space.
Which real water mostly adheres to, but the second rule is the big one. We completely ignore viscosity.
No stickiness.
None. We pretend the internal sticky friction of the fluid, that resistance, when those layers of playing cards slide past each other, we pretend it doesn't exist at all. We assume it flows with zero resistance.
It's an incredibly powerful simplification.
But, I mean, we essentially lose the wetness of the water just to gain a framework that lets us actually calculate how it moves.
It's a trade-off,
Yeah.
but it's a trade-off that lets us actually get things moving mathematically.
So let's get it moving. Transitioning from static puddles to flowing streams relies on, like, a foundational rule of the universe, right? The
Yeah.
conservation of matter.
Yes. In the realm of fluid dynamics, we call this the continuity equation. It's the mathematical expression of a really simple idea. If fluid flows away from a specific point, the amount of fluid left behind has to decrease.
But wait, because our dry water is perfectly incompressible, its density is constant. You can't squeeze it down, and it can't expand to fill empty space.
Right.
So if you picture a completely packed subway tunnel where people are shoulder to shoulder, the only way a new person can step into the tunnel on one end is if someone else instantly steps out of the tunnel on the exact opposite end.
That is a perfect analogy. That completely describes what physicists mean when they say the divergence of the fluid's velocity is zero. What goes into a defined space must equal what comes out, instantly and continuously.
No piling up, no empty spaces.
Exactly. There is no accumulation and no depletion.
Okay, so this sets up the flow beautifully. But the way this perfectly continuous fluid actually accelerates is, well, it's highly counterintuitive.
It trips a lot of people up.
Yeah. When I was first reading through Feynman's notes on this, I had to stop and reread a specific section like 3 times.
Whirlpool paradox.
Yes. Okay, so let's say a fluid is flowing steadily in a perfect circle, like a whirlpool. The whirlpool is in a steady state, meaning if you point a radar gun at any fixed spot in that whirlpool, the speed of the water passing that exact spot never ever changes.
It's totally constant.
Right. So the paradox is, how can the fluid be accelerating if the speed at any fixed point in space is completely unchanging?
It's a brilliant paradox, and resolving it requires understanding one of the biggest subtleties in all of fluid dynamics. It comes down to 2 totally different ways of observing a flow.
Okay, break those down for me.
They're often called the Eulerian perspective versus the Lagrangian perspective.
Words.
Yeah, but simple concepts. The Eulerian perspective is like standing on a bridge, pointing your radar gun at one specific fixed coordinate in the river beneath you, and just watching what happens at that exact spot.
And in our steady whirlpool, that Eulerian fixed point velocity never changes. It's always reading, say, 5 miles per hour.
Exactly. But fluids are made of matter. And matter is what actually experiences forces and accelerates. To understand acceleration, you have to shift to the Lagrangian perspective.
Which means tracking the actual material itself.
Yes. You have to track a specific piece of the fluid as it moves through space. So imagine hovering over that whirlpool with an eyedropper, and you squeeze a single tiny drop of bright red dye into the water.
Okay, I see it. Now, instead of staring at a fixed point in the tank, my eyes are locked onto that specific red drop as it sweeps around the circle.
And as you watch that specific red drop, even though its forward speed might be a constant 5 miles per hour, it is constantly changing direction to navigate the curve of the whirlpool.
Because it's moving in a circle.
Right. And in physics, velocity is a vector. It has both speed and direction. A change in direction is a change in velocity. And a change in velocity over time is the literal definition of acceleration.
Wow. So it's experiencing centripetal acceleration. It's being pulled toward the center just to keep it moving in that circle.
Exactly. So even in a perfectly steady, unchanging flow field, when you look at it with your radar gun, the physical fluid particles themselves are constantly accelerating, decelerating, and changing direction as they navigate.
They're constantly working just to get around the curves and constrictions of their environment.
Which brings us to the energy required to do all that navigating. If the fluid's particles are constantly accelerating to get through pipes and around obstacles, that requires a dynamic energy budget.
And that brings us to how a fluid manages that exact budget. Bernoulli's theorem, which is one of those concepts that sounds intimidating, but it's actually incredibly elegant.
It really is. It is simply the conservation of energy applied to a steady flow.
So imagine a fluid flowing so smoothly that its path forms these fixed invisible lines, which we call streamlines.
Okay, I'm picturing them.
Bernoulli's theorem states that along any given streamline, if you add up the pressure of the fluid, its kinetic energy, which is just the energy of its motion, and its potential energy, like its height due to gravity, that total sum remains completely constant.
It is a zero-sum game. If the fluid gains speed, meaning it increases its kinetic energy, it has to pay for that energy by dropping its pressure or its height.
You can see this trade-off super clearly in a water tower, or even just a large tank of water with a hole at the bottom. The water shooting out of that hole at the bottom has a specific measurable speed.
Right, because it's trading its potential energy, its height in the tank for pure speed.
Yeah, so that water jet exits the hole at the exact same velocity as if you had taken a drop of water from the very top surface of the tank and literally dropped it in free fall down to the level of the hole.
The math lines up perfectly, but the way the water physically leaves the tank contains a bizarre and really fascinating mechanism.
Oh, the contraction thing.
Yes. When that jet of water shoots out of a standard hole, it doesn't just flow straight out like a perfect straight cylinder. The stream actually contracts. It gets narrower than the physical hole it's exiting from.
Which is so weird to picture. And Feynman details a specific extreme version of this in the notes called a reentrant tube.
Right. So picture the drain pipe not just flush with the bottom of the tank, but actually pushed inward, so it's sticking up into the water inside the tank.
Like a little straw poking up from the bottom.
Exactly. The math for our dry water shows that the stream of water shooting out of that reentrant tube contracts to exactly 50% of the hole's area. It squeezes down to precisely half its size.
Wait, exactly half? That's so specific. Why does it squeeze down so much?
To understand why it's exactly half, we have to look at the momentum of the water inside the tank.
Okay.
The water far away from the hole, near the walls of the tank, isn't moving very much, so it has very high static pressure. As the water approaches that reentrant tube, it isn't just coming from straight above it.
Right, because the tube is poking up.
Yeah, the water is rushing in from all sides, including from the areas near the walls, and it has to sweep around the lip of the tube to get out.
So you have water particles basically hooking around the edge of the tube, carrying all this horizontal momentum inward right toward the center of the hole. They are practically colliding from all sides as they try to exit simultaneously.
Exactly. And that inward horizontal momentum doesn't just disappear. As the water turns the corner to shoot down the tube, that inward pressure from the surrounding fluid physically squeezes the exiting jet.
Wow.
The geometry of the reentrant tube means the pressure pushing on the walls perfectly balances the momentum pouring out of the jet. The result is a stream that is mathematically forced to contract to exactly half the area of the opening.
It is a stunning display of momentum conservation. But we can actually see this same energy and momentum balancing act in a much more common scenario, too.
Oh, definitely. Like a constricted pipe.
Yes. Imagine a horizontal pipe that carries water, but right in the middle, the pipe pinches down and becomes much narrower before widening back out again.
Well, since the pipe is horizontal, the potential energy, the height, doesn't change at all. We're only balancing pressure and speed.
Right. And because of the continuity equation, the subway tunnel rule, we know that to get the exact same volume of water through that narrow pinch in the same amount of time, the water has to speed up.
It has to move faster to get through the bottleneck.
Exactly. Which means for the water to accelerate through that pinched section, the pressure behind the water has to be higher than the pressure inside the pinch. You need that pressure difference to create the physical push that speeds the water up.
The inescapable conclusion of Bernoulli's theorem is that the faster the fluid moves, the lower its pressure drops. The pressure in the narrow, fast-moving part of the pipe is actually lower than in the wide, slow-moving part.
It totally defies our physical intuition. We naturally assume a narrow, restrictive pipe would be highly pressurized.
Yeah, like squeezing a massive crowd of people into a tiny hallway. You expect the pressure to spike, but in fluid dynamics, it's the exact opposite.
If you grab two flexible sheets of paper and hold them vertically right in front of your face, maybe an inch apart, you can actually see this happen.
Oh, this is a great experiment.
Yeah, if you blow a fast, concentrated stream of air right down the middle, between the two sheets. Common sense says your breath should wedge the papers apart. Right. You're forcing extra air between them.
That's what you'd think.
But if you actually do it, they snap together.
Because the air you are blowing between them is moving much faster than the still air on the outside of the papers.
Exactly. Faster moving fluid means a sudden drop in pressure. So the normal everyday room pressure on the outside of the papers is now higher than the pressure between them, and it literally pushes the sheets together.
That is the physical reality of Bernoulli's theorem. And what's wild is that the underlying mathematics of this dry water, a fluid where divergence is zero and there is no internal friction, it's so fundamentally sound that it transcends water entirely.
What do you mean?
The equations governing ideal fluid flow are the exact same mathematical framework used to describe electric and magnetic fields in empty space.
Wait, really? The exact same math?
Variable for variable. An ideal fluid flow with zero rotation maps perfectly onto an electrostatic field with zero charge.
That is incredible. And this mapping is incredibly useful when we try to figure out how things fly, right? Like aerodynamic lift.
Absolutely. If we want to understand how an airplane wing generates the upward force to stay in the sky, we can use these overlapping mathematical fields. We can take two different simple flow patterns and literally superimpose them.
Just laying them on top of each other to see the combined result.
Right. So let's apply this to a cylinder in a wind tunnel. First, you calculate the ideal straight flow of air moving left to right past the cylinder.
Okay, and on its own, the air just parts symmetrically around the top and bottom,
Yeah.
right? Creating zero net force.
Exactly. Second, you calculate a separate flow. Air moving in a perfect, continuous circle around that same cylinder like a localized cyclone.
Oh, I see where this is going. When you superimpose them, when you add the straight wind and the cyclone together, the symmetry completely breaks.
It does. On the top of the cylinder, the straight wind and the swirling wind are moving in the exact same direction. Their velocities add up, creating a region of a very fast-moving air.
But on the bottom of the cylinder, the swirling wind is pointing backwards. It's fighting against the straight wind. So they cancel each other out, resulting in a region of very slow-moving air.
And Bernoulli taught us exactly what happens next.
Higher speed means lower pressure. So the fast air sweeping over the top creates a low-pressure zone, and the slow air sluggishly moving across the bottom maintains a high-pressure zone.
And that high pressure on the bottom pushes the cylinder up into the low pressure on top. That upward push is lift.
That's amazing. So without that circular flow, that circulation around the object, the pressures would be perfectly equal. A completely dry, ideal fluid could never actually lift an airplane off the runway without it.
Precisely. And speaking of circular flow, we can use these exact same principles to decode a phenomenon everyone has stared at, the classic bathtub drain.
Oh man, watching water plunge down a drain is mesmerizing. But its shape is dictated by, like, a strict geometric interplay of velocities, isn't it?
It is. To understand the spin, think of an Olympic ice skater. When she spins with her arms outstretched, she rotates at a certain speed. Then when she pulls her arms in, tight to her chest.
She suddenly spins much faster, conservation of angular momentum.
Exactly. The draining water does the exact same thing. As the water at the outer edge of the tub is pulled inward toward the tiny drain hole in the center, its rotation has to speed up. The closer it gets to the center, the faster its tangential velocity, its spinning speed becomes.
At the same time, though, we have to account for the continuity equation.
Right, the subway tunnel rule again.
Yeah. As the water gets closer to the drain, the circumference of its path gets smaller. Imagine a multi-lane roundabout where cars on the inner lanes have to squeeze closer together to get through.
So for the water to maintain a constant flow rate through these shrinking inner circles, its radial velocity, the speed it is being sucked inward toward the center, must also increase.
So both the spinning speed and the inward sucking speed are increasing at the exact same rate as the water gets closer to the hole.
And because these two velocities scale together geometrically, the path of any individual water drop traces out a very specific curve. It gets pulled in and swept around in a perfect equiangular spiral.
Also called a logarithmic spiral, right?
Yes. Millions of drops following these spiral paths simultaneously are what carve out that beautiful, plunging funnel shape on the surface of the draining water.
It is a stunning example of how basic conservation laws shape our physical world.
Mhm.
But everything we've discussed so far assumes the flow is smooth and continuous.
Ah, yes. Things get significantly more complex when we introduce localized spin into the fluid itself. We have to talk about vorticity.
And a concept formulated by the physicist Hermann von Helmholtz, vortex lines.
Right. If you've ever seen diagrams of magnetic fields, where invisible lines loop from the North Pole to the South Pole of a magnet, vortex lines are basically the fluid dynamics equivalent of that, but for spin.
And Helmholtz proved mathematically that in our frictionless dry water, these vortex lines move with the fluid. Wherever the fluid particles go, the invisible lines of spin are permanently attached to them, acting like closed, unbreakable loops.
The spin is essentially baked right into the DNA of that specific pocket of water.
Which is wild. And this permanent attachment of spin leads to one of the most visually stunning mechanical experiments in the Feynman lectures, the smoke ring cannon.
Oh, I love this experiment. The apparatus is brilliantly simple.
Right. You take a cylindrical drum, maybe 2 feet across, you stretch a thick elastic rubber sheet over one end, and on the other solid end, you just cut a small 3-inch circular hole.
And then you fill the inside of the drum with dense smoke so you can actually trace the airflow.
Yeah. And if you slap the rubber sheet on the back of the drum with your hand, an invisible package of air shoots out of the hole with such coherence and stability that it can travel across a room and literally blow out a candle 20 feet away.
And the smoke reveals that this package of air is a perfect traveling vortex ring, a smoke ring.
The anatomy of a smoke ring is a marvel. It is a torus, a donut shape made entirely of those closed loops of vortex lines bundled together.
But how does a donut made of air propel itself across a room? The secret is in its circulation.
Because the vortex lines are spinning.
Exactly. On the inside of the donut hole, the air is circulating in a way that continually pushes forward right in the direction the ring is traveling.
And because Helmholtz proved that the vortex lines are permanently stuck to the fluid, that forward-pushing circulation on the inside of the ring drags the entire bundle of vortex lines forward.
The ring is basically driving itself through the air, rolling over its own internal circulation like a continuous tank tread made of smoke.
It is such a profound demonstration of fluid mechanics. But this exact demonstration is also where we hit a massive insurmountable wall. This is where the dam we built out of mathematics completely breaks.
Yeah, it all falls apart right here.
We spent this entire time building this elegant mathematical framework based on dry water. We assumed constant density, and crucially, we assumed zero viscosity, no internal friction.
And here is the fatal flaw. The rigorous math of dry water dictates something very strict about vorticity. It mathematically proves that if a fluid starts with exactly zero spin, it must remain at zero spin forever.
Wait, forever?
Forever! In a perfectly frictionless fluid, it is physically impossible to create rotation out of stillness. It is a mathematical absolute.
Which creates a glaring paradox.
A huge one.
Right, because before I slapped the rubber sheet on that drum, the air inside was completely still. It had zero spin. And just by hitting it, I created a smoke ring, which is an intensely concentrated bundle of spin.
Or think of a perfectly still lake. Zero vorticity. You stick a canoe paddle in the water and pull it toward you, and you instantly leave a spinning whirlpool swirling off the edge of the paddle.
We create vorticity all the time, so how do we reconcile this?
The reality is our perfect model is fundamentally incomplete because we ignored friction. In our dry water model, we assumed fluid could slide perfectly along the solid boundaries of the drum or the edge of the canoe paddle without any resistance at all.
But in the real world, water and air are sticky. At the exact microscopic boundary where a fluid touches a solid object, the velocity of the fluid drops to absolute zero. It literally clings to the surface.
This is a huge concept. It's called the no-slip condition.
So when you pull that paddle through the water molecules right next to the wood are dragged along at the exact speed of the paddle. But the water, just a fraction of an inch away, is still stationary.
Right. You have two layers of water incredibly close together, moving at vastly different speeds. It creates an intense shear stress.
The best way to visualize it is to imagine a person walking quickly on a smooth floor, and their foot suddenly catches the edge of a heavy rug.
Oh, that's good.
Their foot stops instantly because of the friction, but the top half of their body keeps moving forward with its original momentum. What happens? They tumble head over heels.
That tumble is exactly what happens to the fluid. The friction at the boundary causes the layers of water to trip over themselves, rolling up into a spinning vortex.
So the sticky, messy friction that we tried so hard to mathematically erase is the exact mechanism that gives birth to the whirlpool, the smoke ring, and the circulation required for an airplane to fly.
Yes. To truly understand how the physical world operates, we eventually have to abandon the elegant safety of dry water and embrace the messy, chaotic reality of wet water.
The mathematical dam breaks, and the water escapes exactly because of the friction we ignored. Which leaves us with a really fascinating thought to take away from all of this.
What's that?
Well, if our most mathematically elegant, pristine models of physics completely fall apart at the exact boundaries where they touch the friction of the real world, what other perfect systems or theories in our everyday lives, whether in economics and how we structure our organizations or even how we plan our own lives, are giving us an illusion of total control simply because we've conveniently decided to ignore the friction?
That is a brilliant point. The friction is where life actually happens.
Exactly. Next time you see a kid trying to dam up a puddle in the street, remember?
Yeah.
Sooner or later, the messy reality always breaks through. You know, there's this everyday mystery. that I think we've all noticed but probably never really questioned?
Oh, yeah? What's that?
Well, you look up at a ceiling fan, or maybe you look really closely at the blades of a desk fan, and there is always, and I mean always, this thick, fuzzy layer of dust clinging right to the leading edge of the blade.
Right, right.
And that fan has been churning at top speed, blasting air across the room for months. So logically, the dust should be blown into the next county, you know, but it just stays there.
It's totally counterintuitive. I mean, the assumption is that a blade slicing through the air at high speed would be subjected to, like, hurricane force winds right at its surface.
Exactly. It feels like it should be the cleanest part of the house.
Yeah, practically power washed by the air it's moving. But as you're pointing out, it's definitely not.
No, it's not. And that simple, annoying household thing is actually our gateway into a fundamental truth about how the physical universe works. So welcome to today's deep dive into an absolutely incredible piece of physics. We're looking at Richard Feynman's analysis of what he called the flow of wet water.
It is such a brilliant chapter.
It really is. And our mission for you today is to explore what happens when we take a beautifully simple theoretical model of the world and add just one tiny microscopic dose of reality to it, which is friction.
Yeah, because doing that, adding that friction, it completely shatters our understanding of everything. I mean, from a simple glass of water to the fundamental equations of life itself.
It really does. So to really understand that dusty fan blade, I guess we have to bridge the gap between the idealized mathematical fluid that physicists like to imagine.
Right, that dry water.
Yeah, dry water with zero internal friction. We have to bridge that with the messy, viscous, wet water we actually interact with every day.
Well, physicists love those clean equations, you know. In theoretical dry water, if fluid flows past a solid surface, it just slides perfectly along the boundary.
So no drag at all.
Nope. No drag, no pulling, no resistance. It just glides perfectly. But when we test real fluids, we hit this microscopic reality that completely defies that clean math.
Okay, so what actually happens down at the molecular level?
Well, whether we're measuring water flowing through an industrial pipe or, air rushing over that plastic fan blade, we find something astonishing. The velocity of the fluid relative to a solid surface is exactly zero right at the boundary.
Wait, exactly zero?
Exactly zero. The molecules of air touching the fan blade are trapped in the microscopic geography of the surface, so they aren't moving at all relative to the blade.
Okay, let's unpack this, because that's wild. Does that mean even on something slicing through the air at incredible speeds like a commercial jet wing or a wind tunnel fan, there's a microscopic layer of perfectly still air permanently clinging to it?
Yep, that boundary layer is absolute. Right at the surface, the relative speed is zero. So those microscopic dust particles on your ceiling fan, they're sitting in a zone of absolute dead calm.
Wow. Even while the rest of the room is getting blasted with air.
Exactly. But as you move even slightly away from the surface, the fluid is moving. So you have a stationary layer of air right next to a moving layer of air.
And I'm guessing they don't play nicely together?
Not at all. The moving layer tugs on the stationary layer, and that creates shear forces. It's essentially layers of fluid dragging against each other. And that internal friction, that's what we call viscosity.
Right, viscosity. And Feynman used that classic parallel plates experiment to visualize this, didn't he?
He did, yeah. It's a great way to picture it.
So imagine two flat plates with a layer of water trapped between them. You keep the bottom plate perfectly still, and you slide the top plate forward.
Right.
Because of that zero velocity rule you just mentioned, the water touching the bottom plate is anchored, and the water touching the top plate is moving at the exact speed of the top plate.
Precisely. So the layers of water in between have to slide over each other. It's kind of like a deck of cards being fanned out across a table.
I love that analogy.
Yeah.
But fanning that deck of cards requires mechanical force, right?
Oh, definitely. And the force required to keep that top plate moving depends on a few things. The speed you're moving it, the distance between the plates, and this specific metric called the coefficient of viscosity.
And every fluid has its own coefficient, right?
Yeah, it measures how aggressively the fluid resists that sliding, shearing motion.
You know, I was actually amazed to learn how volatile that coefficient can be. I mean, you'd kind of just assume a fluid's viscosity is a fixed permanent trait.
Oh, not at all. It's heavily dependent on temperature.
Right. Like water just above freezing is actually 1.8 times more viscous than water sitting at room temperature.
It's incredible, isn't it?
It's practically twice as thick, which, drastically alters how ocean currents mix and how marine biology operates in cold versus warm water.
Yeah, and there's also a secondary, arguably more crucial way physicists measure this, which is called kinematic viscosity.
Okay, what's the difference there?
So kinematic viscosity is the ratio of a fluid's absolute viscosity divided by its density. So we're looking at the internal friction compared to the actual mass of the fluid being pushed around.
Got it. So factoring in how heavy it is.
Exactly. And when you view it through that ratio, air and water aren't actually wildly different substances dynamically.
Wait, really? Air and water?
Yeah. I mean, air is incredibly light, its density is very low, so its internal friction has an outsized effect on how it moves. The kinematic viscosity of air is only about 15 times that of water.
That is way closer than I would have thought.
Right. But it makes the math really complicated.
Well, yeah, fluid dynamics equations are famously brutal. I mean, they involve second derivatives of velocity, complex shear strains, pressure gradients.
A lot.
It's a ton. And if viscosity changes with temperature, and changes depending on specific fluid, and changes based on the speed and size of the object, it just feels like engineers would need a million different bespoke equations for every single real-world scenario.
That's the nightmare scenario, yeah.
Like, a submarine in cold water would need a totally different mathematical model than a drone flying in warm air.
And on the surface, the math does look like an unsolvable mess.
Right.
We have 4 primary variables dictating any flow.
Okay, let's list them out.
You've got the fluid's viscosity, its density, the physical diameter of the object it's flowing past, and the velocity of the flow itself.
4 variables just constantly interacting.
Exactly. But, and this is where it gets beautiful, through a profound mathematical symmetry, those 4 variables actually condense into a single master metric, the Reynolds number.
Ah, the Reynolds number, the magic number.
It really is magic.
So the way I understand it, the Reynolds number basically represents a literal tug of war happening inside the fluid.
That's a perfect way to put it.
So on one side, you have the inertial forces, that's the fluid's density and velocity pushing it forward, wanting to keep momentum going.
Right.
And on the other side, you have the viscous forces, the internal friction trying to drag the fluid to a halt. So the Reynolds number is just the ratio of those two competing forces.
Exactly. When you divide the inertial forces by the viscous forces, you get a dimensionless number. And this is the singular key to modern aerodynamics and fluid engineering.
And for you listening, this is exactly why scale models work in wind tunnels, which is just fascinating.
Oh, it saves so much money and time.
Seriously. You don't need to build a full-size Boeing 747 and throw it in the sky to see how air flows over the wings. You could just build a 1-foot scale model.
Because the fluid doesn't actually care about absolute size.
Right. As long as you adjust the velocity of the air or use a fluid with a different density so that the ratio, the Reynolds number, matches the full-size airplane, the flow will look exactly the same.
The physical flow patterns scale perfectly. It's why a giant ocean liner can be tested in a small model basin, or a massive pipeline can be modeled with a tiny tube.
Now, there is a tiny caveat, though, right? For compressible fluids.
Yeah, good catch. For compressible fluids like air, if you approach the speed of sound, you also have to match the Mach number to account for the air compressing ahead of the object.
Right, because you're basically squishing the air at that point.
Exactly. But for standard flow, the Reynolds number dictates everything. If the number is the same, the fluid behaves the same.
Okay, let's track that behavior by setting up a simple physical scenario. Let's take a round cylinder and just place it in a stream of water.
Okay, perfect.
So as we slowly increase the Reynolds number, meaning we're letting the inertial momentum win the tug of war against the viscous friction, the fluid doesn't just linearly speed up. It undergoes these radical, almost alien transformations.
It really does.
Yeah.
So let's start at the absolute bottom end, a Reynolds number of less than 1.
Where the viscous forces are completely dominating.
Right. Here, the fluid acts like thick honey. Because the internal friction is so overwhelmingly strong compared to the forward momentum, the flow just parts smoothly around the front of the cylinder and seamlessly rejoins behind it in these perfect, steady lines.
Very orderly.
Completely orderly. This domain is governed by Stokes' law, which allows us to calculate the exact drag on microscopic spheres.
Oh, so that's like how fine dirt settles in sedimentation tanks.
Exactly. Or how a centrifuge separates heavy particles from blood. The viscosity dictates a smooth, predictable terminal velocity for those tiny particles.
Okay, so it's perfectly predictable. But as we push the Reynolds number up to, say, somewhere between 10 and 30,
The momentum starts overpowering that honey-like friction.
Yeah, things start to get a little weird.
The fluid is moving too fast to perfectly hug the backside of the cylinder, so it overshoots slightly and the weight curls back on itself.
And that creates two swirling vortices forming directly behind the cylinder, just sitting there, statically in place.
Like trap whirlpools.
Yeah, exactly like trap whirlpools. But as we push the Reynolds number past 40, those static whirlpools actually lose their physical grip on the back of the cylinder.
This is where it gets really visually stunning.
Oh, it's beautiful. One of the vortices stretches out, breaks off entirely, and just drifts downstream with the current. And the moment it snaps away, the fluid on the opposite side of the cylinder curls around into the low pressure zone and forms a new vortex to replace it.
And then that one peels off.
Right. They detach alternately, left, right, left, right.
And it creates this rhythmic, zigzagging trail of whirlpools called a Kármán vortex street.
It's one of the most famous patterns in fluid dynamics.
You can actually see this phenomenon from space. When wind blows past a round volcanic island out in the ocean, the clouds form these massive alternating swirls, stretching for hundreds of miles downwind. Nature just defaults to this alternating rhythm.
It does. But of course, if we keep pushing the Reynolds number up, say to 100,000 or 10 million, that beautiful rhythm shatters.
Chaos enters the chat.
Exactly. The region of irregular flow, that boundary layer we talked about earlier, it pushes farther and farther forward on the cylinder. And turbulence completely dominates. The flow just twists and turns wildly in all three dimensions.
But there's a really weird quirk here, right?
Oh, yeah. Curiously, right as this completely turbulent boundary layer forms, the drag force on the cylinder actually drops significantly.
Which makes no sense.
I know, it drops before rising again as violent, chaotic oscillations just take over the entire wake.
Okay, let's pause on the math of that chaos for a second, because there is a paradox hidden in these formulas that I think trips a lot of people up.
Oh, the infinity paradox.
Yeah. So we defined the Reynolds number as the fluid's momentum divided by its viscosity, meaning it's proportional to 1 over viscosity. So that mathematically means as a fluid's viscosity gets smaller and smaller, heading towards 0, the Reynolds number gets larger and larger, heading toward infinity.
Right, that's just basic division.
Right. But we started today by defining 0 viscosity as dry water, perfectly smooth, frictionless potential flow. So why doesn't an infinitely high Reynolds number just look like smooth, perfectly gliding dry water? Why does it turn into violent turbulence?
It's such a brilliant contradiction on paper, and honestly, it's an incredibly common misunderstanding.
It seems like a glitch in the math.
It does. You would assume that as the viscosity coefficient shrinks to near 0, that whole friction term in the equation just vanishes, leaving us with smooth mathematical gliding. But that ignores the actual physical reality of the fluid itself.
Okay, so what's the physical reality doing?
Well, at high Reynolds numbers, we get incredibly rapid variations of vorticity right near the surface of the object.
And vorticity is the localized twist or spin of the fluid particles, right?
Exactly. So even if the overall viscosity multiplier is tiny, the localized twist is so violently extreme that they basically balance each other out in the equation.
Oh, wow. So the rapid variations compensate for the tiny coefficient.
Yes. The product simply does not go to 0. And the really fascinating mechanism here is that vorticity actually amplifies itself.
How does a twist amplify itself?
Well, when you twist a fluid, the vortex lines get carried along with the flow. They get distorted, they get pulled closer together, and they knot up. Imagine a thick bundle of rubber bands getting twisted tighter and tighter.
Oh, okay. So the physical strength of the twist increases locally.
Exactly. The turbulence generates its own chaotic noise. It sustains itself through self-amplification, even when the overall viscosity of the fluid is virtually non-existent.
The chaos literally feeds itself.
It does.
And Feynman highlighted this brilliant experimental setup to isolate this shearing behavior and really, look at the chaos. It's called Couette flow.
Oh, Couette flow is such a neat experiment.
It's so cool. So picture this. Imagine 2 clear concentric glass cylinders. So basically a glass tube sitting inside a slightly larger glass tube.
Right.
The narrow space between them is filled with fluid. Usually it's like an oil mixed with fine aluminum powder, so you can actually see the flow pattern shimmering.
Yeah, that powder is key because otherwise you're just staring at clear oil. So it isolates the fluid between 2 walls. Now, if you hold the inner cylinder perfectly still and you slowly rotate the outer cylinder, nothing weird happens.
Just normal spinning fluid.
Yeah. Centrifugal force pushes the moving fluid outward against the stable outer glass wall. It's completely stable, It operates kind of like a room where the hot air is trapped at the ceiling. There's nowhere for the fluid to go, so it just achieves an equilibrium.
But if you hold the outer cylinder still and you rotate the inner one, things get crazy.
Things get very crazy.
Because the fluid touching the inner glass wants to fly outward due to centrifugal force. But the slower-moving outer layers of oil are blocking its path.
Right, it's trapped.
Exactly.
Yes.
The fluid can't all move out at once, so it spontaneously organizes itself into distinct, stacked horizontal bands.
It looks like a stack of shimmering donuts wrapped around the inner tube. They're called Taylor vortices.
Shimmering donuts. And it's circulating, much like convection currents, in a room where hot air at the bottom has to bubble up through the cold air.
Yeah, it is the spontaneous creation of structure out of a completely uniform fluid. But then, as you speed up that inner cylinder further, those stacked donut bands don't just spin faster in place.
No, they become physically wavy. And those waves actually begin traveling around the circumference of the cylinder.
And here is the unsolved mystery that even baffled Feynman.
This blew my mind. If you measure the speed of those waves traveling around the cylinder, they move at exactly 1/3 the speed of the inner cylinder.
Exactly 1/3.
Why 1/3? No one knows.
Nobody knows.
We are observing steady, measurable laminar flow. We have the exact Navier-Stokes equations governing the oil. We know every single physical rule the fluid is following. Yet this simple fraction, 1/3, emerges from the fluid with absolutely no known mathematical explanation.
It's wild. We simply cannot predict or explain that behavior from the math we possess. And it gets even weirder. If you take that same Couette flow experiment and spin the outer cylinder backward at the same time, the wave pattern shatters.
And what do you get instead?
You get a barber pole spiral pattern. It's a literal spiral stripe of chaotic, turbulent fluid wrapping around the cylinder, alternating perfectly with a spiral stripe of quiet, smooth fluid.
A barber pole of alternating chaos and calm.
Yes.
That isn't just a quirky physics trick. It really exposes a massive limitation in human mathematics.
It really does.
Because we just saw that one simple set of equations, the equations of viscous fluid flow, contains Kármán vortex streets, spontaneous stacked donuts, barber pole spirals, and unexplained 1/3 speed limits. The sheer complexity hidden in a few variables is staggering.
It's humbling. We have the exact equations for water, but we are completely blind to the barber pole structure hidden inside them until we run the physical experiment. We lack the mathematical power to solve the equations and foresee the spiral.
And you can scale that limitation up to astronomy, right?
Absolutely. Think about the sun. We have the exact equations for hydrogen gas. We know precisely how it behaves mechanically, but we cannot mathematically extract a sunspot or a solar flare or the swirling dynamics of a coronal mass ejection from those equations yet.
We know the mechanics for sunspots are locked inside those simple formulas, but we just can't see them on the chalkboard.
Exactly. We know they're in there, we just can't prove it mathematically.
And Feynman posed this incredible provocation based on this exact limitation. When people look at the infinite complexities of the world, they often assume that simple physics could never write an equation for life.
Right. They think life is too complex for math.
Yeah. But look at quantum mechanics. Look at Schrödinger's equation. Does it contain frogs? Does it contain musical composers? Or human morality?
Historically, scientists and philosophers saw the immense variety of the natural world and concluded that mere equations could never account for it all. They assumed something external, some additional set of complex rules, was absolutely required to generate life and consciousness.
But fluid dynamics teaches us that we simply lack the method to understand the qualitative content of equations.
Right. The complexity of a frog or a sunspot doesn't necessarily require a new set of rules. It is an emergent property of incredibly simple rules interacting millions of times over.
The infinite variety is already baked right into the math. Think about all the seemingly dead planets out there. The rocky terrestrial balls in our solar system alone were agglomerated from the exact same dust cloud, obeying the exact same physical laws as Earth.
That's right.
The identical physics that generates our thunderstorms, our volcanoes, and our colorful sunsets are quietly generating infinite, unpredictable novelties on every one of those dead worlds. The universe doesn't need impossibly complex equations to be beautiful. It just needs simple equations to have a tiny little bit of friction.
That's beautifully put. And, the next great era of human intellect might not be about discovering entirely new equations at all. It might just be about discovering a mathematical method to actually understand the sprawling emergent phenomena already hidden inside the equations we have had for centuries.
I love that. And I want to leave you with a final thought to mull over regarding how these physical forces interact with the world around them. We talked earlier about vorticity, that chaotic twist in a fluid, and how it self-amplifies.
Right.
But it also diffuses. If you blow a smoke ring, which is simply a vortex moving through the air, and you shoot it through a cloud of static hanging smoke,
Yeah.
it actually picks up some of that static smoke.
Oh, yeah. It absorbs it.
The ring emerges as a thicker, hollow shell. The physical twist of the fluid literally diffuses outward, permanently altering and transferring its motion into the previously still particles it passes through.
It shares its twist.
Exactly. So if the literal physical twist of a fluid can rub off on its environment, transferring its motion into still air, what other invisible, chaotic properties of nature are constantly rubbing off on us in the turbulent boundary layers of our everyday lives?
That's a great question.
We are walking through invisible Kármán vortex streets every time we step outside into a breeze. We are surrounded by barber pole spirals of air every time a car drives past us on the street. The world is churning with an invisible architecture of chaos and order, just waiting for human intellect to finally decipher the math.
It makes you look at the air around you completely differently.
It really does. So next time you turn on the faucet and watch the water flow smoothly, only to suddenly break into a chaotic splash at the bottom of the sink, remember the infinite complexity hidden in that simple stream. Thanks for joining us on this deep dive. Stay curious. Usually when we try to picture the shape of the universe, there's this profound instinct to want to step outside of it.
Oh, for sure. Yeah.
Like you're holding a snow globe, right?
Yeah.
You want to hold the cosmos in your hands, look at it from an external vantage point, and just like inspect its geometry to see if it's round or flat or saddle-shaped or whatever.
Right. Because we assume we need a God's eye view to actually understand the fabric of reality.
Exactly. But welcome to the deep dive, by the way. Today our mission is to untangle one of the most mind-bending ideas in physics, Einstein's concept of curved space-time. And we're doing this using chapter 42 of the legendary Feynman lectures on physics.
And, you know, that external snow globe perspective is really just a comforting illusion. Once you encounter Einstein, you realize you're permanently trapped inside the snow globe. I mean, there is no outside.
Which sounds terrifying, honestly.
It does, but Richard Feynman tackles this so brilliantly in Chapter 42. He strips away all the cosmic scale and the overwhelming mathematics, and he shows you that uncovering the hidden geometry of the universe doesn't require a spaceship that steps outside of reality.
Right. All you need to map the curvature of space-time is a ruler, a clock, and a pretty rigorous imagination.
Exactly. We are going to break this down exactly as the source material does, starting not with complex math, but with a blind bug.
Yeah, the blind bug. Feynman's approach is incredibly grounding here, because if a two-dimensional bug can prove its world is curved without ever looking up or stepping outside its surface, there is nothing stopping us from using the exact same logic in our 3D universe.
Right. We just have to understand what curvature actually means to someone trapped inside their own dimensions.
Okay, so let's unpack this. How does the bug do it?
Well, we define that curvature through geometric failure. So imagine this blind bug living on the surface of a sphere.
Okay, got it.
And it has no concept of up, down, or out, only the 2D plane it crawls on. If it decides to walk in what it perceives as a perfectly straight line, which is just the shortest physical distance between 2 points, it is unknowingly walking an arc of a great circle.
Right, because the surface itself curves. So to test its reality, the bug just needs to rely on the rules of flat Euclidean geometry, like drawing a square.
Yeah, exactly. If it tries to map out a square with 4 equal lines and strict 90-degree turns, those lines will never connect back at the starting point. The grid itself fails.
The breakdown gets even more severe with triangles, right?
Oh, totally. The bug could start at the North Pole, walk straight down to the equator, turn 90 degrees, walk along the equator, turn 90 degrees again, and head straight back to the North Pole.
And that triangle has 3 90-degree angles.
Exactly. 270 degrees in total. The rigid rule that a triangle must contain exactly 180 degrees just shatters completely.
It's like trying to wrap a flat piece of wrapping paper around a basketball perfectly smoothly.
That's a great way to picture it.
You physically can't do it without crinkling it, because the fundamental geometry of the 2D paper just doesn't match the 3D sphere.
Right. But there's a really important distinction here when we talk about what curved actually means in physics. Like, what if our bug lives on the surface of a cylinder?
Oh yeah, the cylinder is the perfect counterexample.
Right, because to our eyes, looking from the outside, a cylinder appears curved. But for the bug living on it, standard geometry works perfectly fine.
Because if it draws a triangle on that cylinder, the angles still add up to exactly 180 degrees.
Exactly. A square closes perfectly. And the reason is that a cylinder can be unrolled into a flat rectangle without any stretching or tearing.
So physicists call the cylinder extrinsically curved, right? Like curved only relative to a higher dimension.
Right, but intrinsically flat. Feynman's definition of a truly curved space requires intrinsic curvature, a place where the local measurable geometry breaks down.
Which brings us to one of the most powerful analogies in the source material, figure 42-3, the hot plate.
Yes, because we don't even need a physical sphere to warp geometry. We just need a flat disk where the temperature is incredibly cold at the center and gets progressively hotter toward the edges.
And the crucial physical mechanism in this thought experiment is thermal expansion.
Exactly. The bug, its measuring rods, everything in its universe is made of a material that expands when heated and shrinks when cooled.
So when the bug walks toward the hot perimeter, it physically stretches out.
Yeah.
But its ruler stretches by the exact same proportion.
Right, so to the bug, the ruler appears to be a constant, unchanging length, doesn't know it's getting bigger.
So let's track what happens when the bug tries to measure a circle around that cold center.
Right, so to find the radius, it lays its cold, shrunken ruler down repeatedly from the center to the edge. And because the ruler is contracted in the cold, it takes a massive number of ruler lengths to cover that distance.
But when the bug walks the circumference out on the hot edge, its ruler is fully expanded. So it takes far fewer ruler lengths to measure the perimeter.
Exactly. And then the math just crumbles. In a flat universe, if you divide the measured circumference by 2 pi, you should get the exact radius.
But the bug does this calculation, looks at the actual number of ruler lengths accounted for the radius, and finds a huge discrepancy.
Right. The physically measured radius is unexpectedly longer than the circumference dictates. It discovers what Feynman calls an excess radius.
So the bug has proven its space is curved without ever leaving it.
Without a single spaceship.
Yeah. And if a 2D bug can detect curvature purely by documenting these geometric errors, we can just scale the experiment up.
Exactly. We build a massive three-dimensional version of that circle, a giant sphere drawn in the vacuum of space.
So we execute the exact same procedure. We measure the entire surface area of this giant sphere meticulously. And using standard Euclidean geometry, we calculate what the radius should be.
Right. And then we perform the physical measurement. We dig a tunnel straight to the center of the sphere, laying down a physical ruler all the way to the core.
Now, empty space would yield a perfect match. But the universe isn't empty.
No, it's full of matter. And Einstein's field equations state that matter itself is the source of this intrinsic curvature.
So matter acts like the temperature gradient on the hot plate, just warping the measuring rods of reality.
That is exactly what it does. The presence of mass guarantees a discrepancy. The difference between our physically measured radius and the mathematically predicted radius is directly proportional to the amount of mass inside the sphere.
Okay, let's ground this with a real example, the Earth. If we measure the Earth's surface area, calculate the predicted radius, and then literally dig a tunnel to the planet's core with our measuring rods.
The physically measured radius of the Earth is 1.5 millimeters longer than flat geometry allows.
Wait, 1.5 millimeters. We have to pause and frame that scale.
It's tiny, I know.
The radius of the Earth is nearly 6,400 kilometers. Out of that massive distance, the mathematical discrepancy is literally the width of a grain of rice.
Yeah, it is staggeringly tiny, but the philosophical implication is seismic. I mean, it means there is literally more physical space inside the Earth than its surface area can account for.
Oh, wow. And what about something bigger?
Well, for a mass the size of our sun, that radius excess grows to roughly half a kilometer.
So wherever you have a concentration of matter, it creates a localized pocket where the geometry bulges outward.
Wait, so if there's a discrepancy, does that mean every planet or star is basically a three-dimensional pimple in the fabric of space?
Yes, that is a highly accurate way to visualize local curvature. The mass literally stretches the internal volume.
That is wild. But the theory of relativity doesn't isolate space from time. They are woven together.
Right, space-time.
Exactly. So to understand how a 3D pimple in space alters the flow of time, we first have to isolate what gravity physically feels like.
And this is where we pivot to Einstein's principle of equivalence.
Right.
Picture a windowless rocket ship. Coasting in deep space and free fall, the occupants are totally weightless. Objects float. There's absolutely no sensory experience of gravity. Okay, but now the rocket fires its thrusters, accelerating upward at exactly 1g, which is the identical acceleration to Earth's gravity.
Exactly. And what happens? The floor of the rocket rushes up to meet your feet.
Right. So if I let go of an apple, it doesn't actually fall. The floor accelerates upward and smacks into the apple.
Yes. And inside that windowless box, the physical sensation of accelerating through a vacuum is indistinguishable from standing on the surface of the Earth.
So there is no mechanical experiment you can perform inside that room to tell the difference between acceleration and gravity.
None. They are physically identical states. And Einstein realized they aren't just similar, they are completely identical situations from the inside. And Feynman leverages this exact equivalence to prove that gravity manipulates time.
Okay, let's walk through figures 4216 and 4217. The rocket clock experiment.
Right. So we set up an experiment inside this accelerating rocket. We mount a highly precise clock at the front of the rocket. We'll call that clock A.
Okay.
And we mount another at the tail, clock B.
So I'm sitting at the tail with clock B. The rocket is constantly accelerating forward, and clock A at the front is programmed to emit a flash of light exactly once every second.
Exactly. Now track the journey of that light pulse. The flash leaves clock A and travels down the length of the ship toward you at the tail.
But the rocket is not stationary.
Right, it is continuously accelerating. So by the time that light pulse is in transit, the back of the ship has gained speed.
So the tail is physically rushing forward to intercept the incoming light.
Yes. The distance the light has to travel is dynamically shrinking while the photon is in flight.
Okay, so the first flash hits me, then the second flash is emitted 1 second later.
But because the rocket's velocity is constantly increasing due to that steady 1g acceleration, the tail is moving even faster when it intercepts the second flash.
Right, so the tail rushes to meet the second pulse more aggressively than the first one.
Exactly. The gap between the flashes is being compressed by your own acceleration.
So to my eyes, sitting at the tail, those flashes are arriving less than a second apart. I look at my wristwatch, and I conclude that the clock at the front of the rocket is running fast.
The geometry of the accelerating frame mandates it. And if the principle of equivalence holds absolute meaning, if sitting in an accelerating rocket is physically identical to sitting in a gravitational field on Earth, then the conclusion transfers perfectly to our planet.
So what does this all mean? If the accelerating rocket is exactly the same as sitting on Earth, then a clock placed high up on a shelf on Earth must tick faster than a clock on the floor.
Exactly. Gravity alters the literal rate at which time passes.
That just challenges basic human intuition so much. The idea that your head is aging slightly faster than your feet sounds like pure science fiction.
It really does, but physics demands a rigorously closed loop. We have to prove why this isn't just an illusion, but a fundamental reality.
Right, and we can prove this temporal shift is a reality without relying solely on rockets, just by using the inviolable law of conservation of energy.
Right, the atom thought experiment. Let's trace the mechanics of that energy proof.
Okay, so we start with a single atom resting on the floor in a low energy state.
Right, and we physically lift it up to a specific height. Let's call it height h. By lifting it against the gravitational field, you inject potential energy into the system. You perform physical work.
And thanks to E=mc², we know we aren't just moving mass, we are altering it.
Exactly. By adding potential energy to the atom, by holding it at a higher altitude, its relativistic mass literally increases. It actually becomes heavier.
Okay, so while holding this heavier atom at height h, we trigger it to emit a photon of light.
Right. The atom releases energy, dropping back down to its original lower energy state. It sheds that extra relativistic mass.
So we carry the newly lightened atom back down to the floor. Wait, so I lifted a heavy object up, but I'm carrying a lighter object down.
Exactly. The work you expended lifting it was greater than the work you recovered bringing it back down.
So we have a net deficit of energy in our system. But the universe doesn't allow energy to vanish.
It doesn't. The missing energy is carried by the photon. When that photon travels down from height h to the floor, it must arrive with slightly more energy than it intrinsically had when it was emitted at the top.
Just to account for the work we did lifting the atom's extra mass.
Right. It has absorbed the energy deficit created by our lifting and lowering cycle.
But a photon can't speed up to express that extra energy, right? It's already traveling at the speed of light.
Exactly. Its only mechanism for expressing higher energy is to increase its frequency. The light waves oscillate faster.
And a vibrating atom emitting light is fundamentally a clock.
Yes. Because the photon gains energy falling down the gravitational potential, its frequency shifts higher, meaning the ticks of the light wave arrive faster at the bottom.
Which perfectly corroborates the rocket experiment.
It perfectly matches the math. The atom at the top is acting as a faster clock. Time actually runs at different rates depending on altitude.
Here's where it gets really interesting. This is exactly like the bug on the hot plate. But instead of physical rulers stretching out because of temperature gradients, it's our literal clocks running faster because of gravitational gradients.
Yes.
We aren't just navigating a spatial pimple, we are living on a temporal hot plate.
That is a brilliant way to phrase it, and the experimental validation for this is stunning. Using the Mussbauer effect, physicists have measured this frequency shift in atomic emissions over an altitude difference of barely 20 meters.
Wait, just 20 meters?
Just 20 meters. Move a clock 20 meters higher, and the shift in its ticking rate perfectly aligns with Einstein's equations. 2 parts in 10 to the 15th. Time genuinely runs faster the further you move from a center of mass. Einstein was perfectly correct.
So we have established 2 profound pillars here. First, mass creates spatial curvature, that radius excess. And second, mass creates a temporal gradient, where clocks run faster at higher altitudes. So if space-time is warped like this, how do objects decide which path to take when they move? Like, how does a thrown baseball know which path to take through the air?
Oh, this requires a total abandonment of Newtonian physics.
Because Newton envisioned an invisible tether, right? A force of gravity actively pulling the baseball down to the dirt.
Right, but Einstein erases the tether entirely. To understand the object's path, we have to define a term. Proper time.
Proper time, what does that mean?
Proper time is the duration measured by a clock that is physically moving along with the object.
So like the wristwatch on the baseball.
Exactly. Let's analyze this puzzle of the thrown clock. You have stopwatch on the ground. You will wait exactly 100 seconds. Your objective is to launch a second clock into the air and catch it exactly 100 ground seconds later with one strict condition.
Let me guess. The thrown clock must record the absolute maximum possible time on its own display.
You got it. You want to maximize its proper time.
Okay, well, if I just hold it in my hand, it registers exactly 100 seconds, matching my ground clock.
Right.
But we know clocks tick faster at higher altitudes. So the strategy should be to shoot the clock straight up as high as the atmosphere allows. It spends the vast majority of its journey in weaker gravity, ticking incredibly fast.
But that strategy ignores the velocity required to execute it.
Wow.
To shoot the clock incredibly high and still catch it within the 100-second window, it must travel at extreme speeds. And special relativity dictates time dilation.
Right. The faster an object moves through space, the slower its internal clock ticks relative to a stationary observer.
Exactly. So the two effects are at war. The altitude is trying to speed the clock up, but the velocity required to reach that altitude is forcibly slowing the clock down.
So I need the mathematical sweet spot. A path that gains enough altitude to benefit from the faster ticking, but maintains a slow enough velocity to avoid extreme time dilation.
And when you perform the rigorous calculus to integrate these competing effects, finding the specific trajectory that yields the maximum possible proper time, the mathematical solution is a parabola.
Which is the exact arc of a thrown baseball.
It is the precise ballistic trajectory of an object in freefall. The baseball is not being pulled by the Earth. The baseball is simply navigating the curved geometry of space-time along the path that maximizes its own internal clock.
It is following the natural contours of the temporal hot plate.
Yes. Objects don't feel a pull of gravity. Particles are just following the path that maximizes their proper time in curved space-time. This entirely replaces Newton's laws of motion.
So particles are essentially lazy or maybe time greedy.
Time greedy, I like that.
They aren't being dragged down by invisible Newton strings. They're completely blind, just like the bug, naturally following the path of least resistance through warped geometry to experience the most time possible.
The paradigm shift is just absolute. Mass curves the space-time continuum, and objects dictate their motion purely by seeking the maximal proper time through that altered geometry. The illusion of a gravitational pull is just our observation of objects slipping down the temporal gradient.
So to summarize all this for you listening, we've covered 2 great pillars of Einstein's theory of gravitation today. 1, matter dictates how space-time curves, giving us the radius excess.
Right.
And 2, objects move by simply trying to maximize their proper time through that curved spacetime.
Exactly. So the listener takeaway here is that every time you drop your keys or throw a ball, you aren't watching them fall. You are watching an object aggressively navigate the invisible, curved geometry of the universe.
It forces a complete rewiring of how you look at the physical world around you.
It really does. The elegance of Feynman's Chapter 42 is how seamlessly it scales from a bug realizing its ruler doesn't fit to the fundamental mechanics governing planetary orbits and falling apples. It all stems from internal geometry.
It's incredible. We want to leave you with a final provocative thought to ponder on your own. We know that the mass of the Earth creates a 1.5 millimeter geometric bulge and a slight acceleration of time at higher altitudes.
Right.
So ponder the extreme limit of this mechanism. Imagine a black hole, a concentration of mass so dense that the mathematical curvature trends toward infinity.
Oh, wow. Yeah.
If you were that blind bug crawling toward the event horizon, what happens to the geometry? Does the radius excess stretch out infinitely before you?
That's a terrifying thought.
Right. Does the temporal hot plate freeze entirely, bringing the wristwatch on the baseball to a dead stop? The math that governs a falling apple is the exact same math that breaks down at the edge of infinity. Just something to consider the next time you look up at the stars.